Good morning and good afternoon to all of you. So, Honorable Professor Jayanto Mukhopadhyay, Dean Outreach, IIT, Professor Francesco Piccioni, University of Groningen, Netherlands, Professor Shantanu Chattopadhyay, Head, Rubber Technology Center, distinguished guests, invited speakers from India and abroad, technical experts, participants from various universities, companies, and organizations from different parts of India and abroad, my faculty colleagues, staffs, students, research scholars, ladies and gentlemen, a very good morning or good afternoon to all of you. So welcome everyone to this international webinar on rubber products for a green future. And we have focused over here towards recycling and sustainability. In short, our program is known as RPGF 2021. This webinar is also a part of the 40th anniversary celebration of our Rubber Technology Center of IIT Kharagpur, which was established in 1981, and formerly it was a part of Applied Chemistry Department of IIT Kharagpur. The target audience of today's international webinar is students, research scholars, scientists, and industry personnel worldwide. The webinar has been organized jointly by the Rubber Technology Center of IIT Kharagpur, India, and the Chemical Engineering Department of University of Groningen, the Netherlands, under the aegis of SPARC program, MHRD, India. I'm also glad to inform you that TechnoBiz, Thailand, and Indian Rubber Institute, IRI, are the strategic and media partners of this webinar for the global
We lost a voice.
I believe that could you hear me?
Yeah, go ahead.
I believe that we will make this event interactive and successful. So first of all, let me give you a brief overview of the entire program of RPGF 2021 International Webinar today. So to begin with,
this is a disaster.
Nikos Hadjichristidis from Saudi Arabia, from KAUST. He will be speaking on novel thermoplastic elastomer based on nonlinear architectures and dynamic covalent bonding. After that, Professor Norbert Vennemann, retired professor from Osnabrück University, Germany, he will deliver his lecture on TPEs, process, properties, and recent applications. After him, Professor Julian Obedise from France, he will be speaking on nanoparticle assembly and polymer interfacial gradients in rubber composites, with special reference to SAX, small angle excess scattering. In technical session 2, we'll be having 2 lectures, one from Peram, from TechnoBiz activities for rubbers and tire industries, and then by Mr. Basudeva Rao, Honorary Secretary of Indian Rubber Institute. He will be speaking on the activities of Indian Rubber Institutes. In technical session 3, we have 2 speakers.
Kinshuk, we lost your voice.
First on recent studies on natural rubber-based nanocomposites. And finally, the last session, also we have 3 speakers. The first one is from Kraton Polymers by Dr. Leonard Clark from Netherlands. He will be speaking on Kraton Polymers boosting circular plastic solutions, which will be followed by Professor Shantanu Chakrabarty. He will be speaking on damage modeling of silica carbon black filled elastomer composite with special reference to finite element analysis and its experimental analysis. And finally, Michel Cognet from Michelin Group France, Michelin Tire. He will be speaking on recycling in principle, the entire program for today. Okay, now I hope that Professor Jayanta Mukhopadhyay has joined. Are you there, sir? Professor Jayanta Mukhopadhyay? Okay, maybe he'll be joining later. Then I'll request now Professor Chakrabarty to speak on this Rubber Technology Center. Professor Chakrabarty, please.
Yeah, am I audible?
Yes.
Yeah. Very good morning and good afternoon to esteemed delegates, Professor Francisco, Professor Noskar, and Professor Jayanta Mukhopadhyay, all dignitaries and delegates and speakers, chairpersons, attendees over here. Welcome to Rubber Technology Center. Welcome to this webinar. Rubber Technology Center, actually, the name Rubber Technology is very unique in an IIT, which is the flag bearer of all Indian Institute of Technology system. Now it is 23 members. Out of that, Rubber Technology is only there in IIT Kharagpur. And interestingly, and this is the 40th anniversary celebration for RTC, we have been established as an independent center in 1981, although our institute was established back in 1951. And another interesting thing is that the first PhD degree obtained from this institute was a person, Professor Sahadev Bandyopadhyay, working on rubber technology. So you can understand this rubber technology is as old as the institute is, 1951. Okay. So the center was actually established in 1981 with the aid of the Ministry of Education under the Colombo Plan, UK government, and the Technical Collaborative Mission of US government. Since the inception, Rubber Technology Center has rendered as excellent service to the rubber and polymer industries as well as the academia through our country. A couple of years back, Rubber Technology Center was awarded as topmost institute in education and research in rubber in Asia. We offer 2 years MTech degree and PhD degree. We also offer breadth courses to the BTech students in both the semester, which have been very popular among the students studying engineering as well as the basic sciences of different disciplines. Apart from these activities, we regularly organize short-term courses, nowadays webinars and international conferences, of course. And Professor Noskar has been very active, organizing regular conferences and webinars. And this time in pandemic also, this is not exception actually. So the major focuses of our center in terms of research, the design and development of different rubber products with predictable life cycles with tire, conveyor belts, seals, and in fact tire on which the entire civilization runs basically. The green and sustainable technology like green tires, green approaches in rubber, polymer processing, green solvent in polymer processes, recycling, reuse of plastics, and of course today's slogan is the sustainability. Smart polymer and rubber composites having interesting application in self-healing materials, safe memory polymers, smart and stimuli responsive polymers, composites, super hydrophobic materials, smart multifunctional paints, coatings, smart textiles, magnetically active composites, conducting polymers as energy material, TPEs, TPEs, block copolymer, graph copolymer, rubbers, polymers for biomedical application and whatnot. So you can understand by name we are rubber technology, but in research we do the wide gamut of polymer and rubber technology, inclusive of coatings and textiles. The center is one of the most vibrant, although we have now 1 faculty is going to join soon. So 7 faculty members going to be all together maybe next couple of months. And we have about 55 PhD students working in the small center. And we have about 42, 43 MTech students counting first and second years. And in terms of, our inputs, it's 400 plus journal papers, I mean, more than 10 patents, last 5 years achievement I'm talking about. And this is going to be the 3rd webinar within a couple of months span we are going to organize here. So we have a collaborative project with different industries like major petrochemical industries in India, abroad, different tire industries, different rubbers and polymer manufacturing industries. Of course, all are India and abroad, and coating and plastic industries. Our center also have many different public sectors and funding projects like DST, CSIR, ACRB, ISRO, DRDO, DAE, IRMRA, etc. We have several mega projects like UI, Imprint, SPARC. Like this is one of the projects, SPARC with Professor Francisco there in Gronningen. So we have several such SPARC programs here, projects. And this is recently, of course, initiated by the government of India to increase the collaborative research, indeed to have a concrete foundation in terms of collaboration, in terms of exchange of faculties and students. And sorry, if it would have been normal time, we would have seen Professor Francisco to be here in this green campus and maybe deliver some of the lectures to our students here. But we miss you, sir. And the next time, definitely you are very welcome over here. So this webinar will be great platform to renew and re-establish and reinitiate relationships and collaboration with different industries, academia in India and abroad. And this webinar surely also be beneficial and moral booster to the participating students in particular. Okay, so they will able to see the eminent scientists, established scientists in their field, how they're deliberating, how they're discussing, dissecting the research and their new knowledges with everyone. So, only thing is that most of the students are out of campus for a long time. They're missing the green campus. Okay, and once again, welcome to the webinar. I feel this webinar is going to fetch a great success to us. But again, alas, had it been like a normal time, we would have you all in a place here, and after that we would have broken for for the particular session, and then had a discussion, dissection, bisection, whatnot. And with that, thank you very much. Welcome to IIT Kharagpur. Welcome to webinar. And again, as a remembrance, IIT Kharagpur is the flag bearer of all IIT system you can see today. 23 sister IITs we have. Thank you very much. And once again, welcome. Professor Mukhopadhyay is already there. Over to Professor Mukhopadhyay, please.
Thank you, Professor Chattopadhyay, for your very nice address. And welcome, Professor Mukhopadhyay. Professor Mukhopadhyay is a professor of computer science and engineering of IIT Kharagpur, and he is also our Dean Outreach. So we are curious to hear from him. And Professor Mukhopadhyay, you can address the audience. Yes.
Am I audible now?
Yes. Yes.
Okay. Sorry. So it's my pleasure and also privilege to welcome all the international participants to this webinar of rubber products for a green future. And as a Dean Outreach, I extend my heartiest welcome to all the participants. And as Professor Chattopadhyay was mentioning, that our institute is a flag bearer of the IIT system, because we are the first IIT, and we take pride of this fact. And we have also, as you can see, that we are largest IIT also. We have a sprawling campus of about 2,200 acres, and there are various disciplines. It is an IIT which has so many different other disciplines, not only the technology, but also we have law school, we have management school, and we have grown over the years and made a system which has become very unique in particularly in our country. So just to mention about about my office, this Dean, I am the Dean Outreach, and this is a new office in our system. It is just introduced, I should say this year itself, because I am the first office bearer, and we have reorganized. And under this office, we have several verticals. One is, of course, Alumni Connects. The other one is International Relations, and the other vertical is Continuing Education. So I will just briefly speak about some of our international programs, because I have very distinguished speakers from different countries, and also participants, and it's an international webinar. So maybe it is very appropriate. I would take this opportunity to speak something about our international programs. That many of us colleagues, faculty colleagues, the departments, and particularly the Rubber Technology Center, I should also mention. So they have very strong international collaborations with their peer groups. They are participating in different programs, international programs, either national programs or international research programs, and they have these collaborations. And institute-wise, we have some programs also, like we have International Students Program, where we offer admissions to our international students in the postgraduate programs. You know that in IIT system, it was a bit restrictive, but with the changing vision and the changing time, we are also adapting, and particularly this National Education Policy 2020, which has been outlined, it has given us a mandate that our international outreach needs to be expanded, and we are planning for that. We are having few MOUs with top-ranking reputed institutes. Like we have 6 institutes with whom we have joint degree program in the master's and PhD level, like University of Manchester, University of Melbourne, to name a few, and only 6, of course. But we are trying to build up such a relation and such a program with as many as institutes possible, because we have also, our strength is also, bandwidth also is limited at this stage. We are trying to expand, and we hope that we would be also reaching many of the institutes, top-ranking institutes of different countries, and particularly also in the South Asian regions, where also we would like to see that, because they are neighboring countries and they are top-ranking institutes, we would like to seek collaborations. We like to have student exchange, faculty exchange with them. We run also few international visitors program, because some of our alumni, they are generous enough to give in certain fund. That is, at this point, we run a few programs like Sri Rajgadiya International Exchange Program, and we support student exchange, faculty exchange. So with this few words, let me conclude, and let me wish the success of this webinar, and once again extending a very hearty welcome to all of you. Thank you very much for your attention. Thanks.
Thank you very much. Yeah, thank you very much, Professor Mukhopadhyay, for your nice words.
So I will be leaving Kinshuk because I have a meeting now. So with your permission,
sure, please. Okay. Thank you.
Thank you.
Thanks.
Now it is time for Professor Francesco Picquini from University of Gronningen to share a few words, and I believe he is having some presentation, so I can show this. Is it visible to all of you? I believe.
Yeah, it's visible.
Yes.
Make it full screen, please.
Yes, I'll do that. Just, and I'll give you also. Yes, and Francesco, I give you also access for your mouse, right?
We'll try. Well, probably the system is a little bit slow in responding, but if not, then I will ask you very kindly if you can switch slides. Anyway,
sure.
Welcome everybody. My name is Francesco Picquini. I'm a professor at the University of Gronningen. Professor Chattopadhyay, indeed, I would have liked very much to be there actually, and not to do this online exercise. I do love India. The only problem that I have is that every time I come there, I actually gain weight. I love too much Indian food. But I hope there will be actually opportunity in the future for a visit, for a personal visit. As I said, I'm a professor at the University of Groningen. Let me see if I can change the slide. It seems not to be responding, so, oh yeah, wait a second, yeah. Oops, yeah. So for those of you who are not well aware, Groningen is the last city in the Netherlands before the North Sea. It's a typical, actually, student city. The university, well, there is 170,000 people living here, among which actually 40,000 are students. Typical university city, very cozy and very nice, actually, with a good, actually, also student life. Although I'm too old for that, to enjoy that. In Groningen, I'm responsible for the chemical product engineering group, which is one of the two groups that we have. So that's me. I'm the full professor. There is an associate professor, and there are 4 assistant professors. One of them started actually yesterday. It's a rather big group. We started this group in 2003, and we started from scratch. It was just me and a professor at that time. At the moment, we have roughly 12 postdocs and 30 PhDs. Since the university went international, all our programs are in English from the first year, both in the bachelor and in the master. We have been experiencing a very big growth in the number of students. We do have in chemical engineering at the moment, roughly in our group only, 60 master and bachelor projects per year, because of the rules that do not allow young people actually to do too much in education. Well, older people like me, they have to sacrifice a little bit ourselves. So last year, 54 people did their thesis with me, both bachelor and master, which makes my life very interesting, and my wife not so happy because I have to work a lot. But good, that's life. We design chemical products for industry, which means actually that besides publication, we do also have patents. 8 at the moment, mostly for me actually. 3 more are on the way. One of these patents is already a commercial product. It is water swelling rubber actually for sealing applications. We do have an extensive industrial network. Yeah, here are some of the companies we cooperate with. Some of them are probably very much known also outside the boundaries of the Netherlands. Yeah, what do we do is actually in rubber. One of the things that we do is actually the bio-based side. So we tried, for example, if we take an EPDM, which is a very well-known rubber, we try, for example, actually to make it bio-based. So we take ethylene not from oil sources, but from biomass, from ethanol, which comes from corn. We take carbon black actually from pyrolysis of car tires, and we can take also oil from other natural sources, and you can make a formulation which at the end actually has, well, is 85% bio-based. It's still a rubber. It has the same properties of the one that you would expect actually, but it's bio-based. I always say going green is not enough, which doesn't mean actually that besides this, you don't have to look only at the origin of your product. You have to look also at the end of life. And when you talk about recycling, for many years, we started this actually in 2000, my first PhD in Groningen in 2004. We thought actually that the reversible cross-linking was a good idea actually. The general idea, and I use here the example very typical of the Netherlands, of the bridge which open and close on commands to let the ships go or the bikes. But the general idea is that actually you have a system which at high temperature is decoupled, is decross-linked, and when you cool it down, it cross-links, giving the typical properties of a rubber. And then this actually can be controlled simply by temperature. So it's a reversible cross-link system. Good. We did that actually not to the Vitrimer approach, which I think we will hear something about today, but we did that actually with Diazalde. So we took a rubber which has was functionalized with maleic anhydride. We attached the rubber furan groups, which are these heterocyclic 5-member compounds. And then actually, if you use a bismaleimide, you can reversibly cross-link this system. You can do that in solution, but you can do that also in the solid state. This reaction is called the Diazalde reaction, is an equilibrium reaction, which means actually that indeed low temperature, the system closes down, cross-links, and at high temperature decouples and becomes processable like an elastomer, like a thermoplastic. So for example, if you take an EPDM, which has been cross-linked actually via peroxide, you can make bars, you can measure mechanical properties, of course, but if you try to reprocess it, it will not be able to do that because it's a cross-link system. But if we use our chemistry for cross-linking, then it's possible to make a bar, it's possible to measure the properties, but then when you shred it to pieces, you are able to remold it, simply because at high temperature, the system is not cross-linked anymore. The Diazalde goes back actually, so it decouples again, and then you can make a new bar without any problem whatsoever. So this is in a way a cradle to cradle material. Of course, this is not enough. We work with industrial sponsor. You want to show also that the rubber that you make has the same properties of a normal rubber. So what you see here actually are mechanical properties of what you see on the left side, the initial EPDM that we use. Afterwards, the EPDM modified with furan. And of course, the last bars are about the crosslink system. And you see the typical behavior of a rubber, of course. When you crosslink it, the tensile strength and the modulus will increase. The elongation of break, of course, will decrease a little bit. Of course, when you recycle, then is the question, you are able to keep those properties? Well, if you look actually at the third and fourth group of bars, these are actually the properties before and after recycling. So what you see is that within the experimental error, actually, we are able to maintain all the properties that we wanted. But what is even more interesting is that if you compare this rubber that we made together with respect to other rubbers, which are cross-linked either by sulfur or peroxide, you see very clearly actually that we are able to, in any way, approximate the properties of a sulfur cross-linked rubber. So this system is reversible, but it gives you, in terms of performance, roughly the same performance at room temperature of the normal crosslink one, at least sulfur one. I say specifically room temperature because if you increase the temperature, of course, then the behavior starts being different. So you have a recyclable system, but you pay a price for that, which is the properties at relatively high temperature. This was very nice, published, but I always tell my students, this is for my children. You cannot convince the rubber industry to change entirely the cross-linking system within, let's say, my generation. That I don't think that will be possible. But what about now? Well, in the Netherlands, we have a lot of actually motivation actually to go into recycling. So we do have projects in Groningen about recycling of polyethylene, polypropylene, and PVC, which together is 75% of all the plastic worldwide. So there is no talking about recycling if you don't tackle these three. So you have to do something about there. We do have projects about the polypropylene degradation, which we almost solved, or at least we have outside now technology which could solve the problem. We do have we have set together a consortium about PVC recycling and about one of the main issues, which is HCl elimination. We do have a new technology for rubber recycling, which is not the vulcanization technology. This is actually a patent which has recently granted, and as a matter of fact, already transferred to an industrial partner of ours. So we hope actually that we will be able to come on the market with the first product. We are working on it. We should be able to come actually before the end of this year. We made out of recycled rubber, we made a foldable basket for the bikes, which in the Netherlands is a very big issue, of course. And last but not least, together with my old professor, I did my study in Italy, Professor Ciardelli, who was not there at university anymore. He has his own spin-off company. We are actually editing, we are special guest editor for a special issue on recycling. So if you have work that would you like to be published, unfortunately the deadline is quite close, it's the end of this month. But please feel free actually to contact me, and we certainly can include your paper in this special issue, which is on an open access journal. And that's it. Thank you very much for your attention. I would like to stress in just 30 seconds, I'm very grateful actually to Professor Naskar for involving us in a joint project collaboration. Unfortunately, Corona avoided any personal contact and maybe even further collaboration. I do hope that in the future we will be able actually to do even more than what we are doing now. Thank you very much.
Thank you very much, Francesco, for your nice overview of Groningen University and this your Department of Chemical Engineering. And I must say one thing that also one of our students, Dr. Tuhin Chatterjee, he did his PhD with us at our center, Rubber Technology Center, and he did his postdoctoral studies with Francesco, and I think he did well, and he got very recently a job as well. Yeah, that is good. Well, yeah, thank you once again. This is all about our introductory, our inaugural session. And now I think we move to the first technical session, and we are right on time. So for this first session, we have 3 speakers, as I mentioned before. So Professor Nikos, Professor Vennemann, and Julian, and Professor Francesco Piccioni. I'll be requesting you to chair this session and introduce the speakers.
Thank you, Professor Naskar. It's a pleasure and it's an honor actually to be the chairman of this first session. Since we are rightly on time, I would suggest that we start immediately with the first speaker. It is actually, I could not be more pleased to introduce to you Professor Hadjichristidis from the University of Saudi Arabia. The reason why I'm so pleased is actually Nikos is one of my heroes. For people of my generation, when you talk about anionic polymerization, you talk about Professor Hadjichristidis. And there is no way around it. As I said, actually, he's originally from Greece, but he's now a professor of chemical sciences at the King Abdullah University of Science and Technology, Saudi Arabia. We know each other very well. When he was editor of the European Polymer Journal, I was asked many times by him to act as a reviewer for some of the papers. If we have to go through his scientific careers, I suppose the webinar will take 8 hours, only talking about that. So I will be shortly about that. He's the author of more of 550 scientific papers, 35 patents, editor of 3 books, and he received a very high number of awards all over the world, some from Greece, but also some from the USA, and international one. I would say then, without any further ado, Professor Hadjichristidis, I think it's a real pleasure for me to give you this virtual floor and to start with your presentation.
Thank you very much, Francesco. Do you hear me very well? Do you hear me okay? Yeah, okay. Thank you very much, Francesco, for your kind words. Also, I would like to thank the organizer and in particular Professor Naskar, my good friend Kinsu, and giving me the opportunity to discuss with you about thermoplastic elastomer and about a new direction of not only of thermoplastic elastomer but of polymers in general. The structure, they are based on dynamic covalent bond. I have only one complaint, that because Kinsup knows that I am more handsome than him, he took out my picture from this presentation. So what I have your photo here, I have to take, Francesco. What I'm going to discuss with you today is novel thermoplastic elastomers based on non-linear architectures, because you know that almost all the industrial thermoplastic elastomers are linear, with an exception of a few star triblock polymers. And because I believe, and you know, that the heart of the properties of all materials, and in particular of polymers, is situated at the molecular level. So if you are able to play with to control the molecular level, you are able to control the properties of the material. So what we are doing, what I was doing in Greece, what I am doing at the University of KAUST, that macromolecular architecture. So, but lately I'm using all kinds of polymerization, not only anionic polymerization, but also new kind of polymerization like polyhomologation, etc. So let me go through. Okay, so first of all, because in the audience there are many students, I'm going to say a few words about thermoplastic elastomers. So the thermoplastic elastomers, they combine two contradictory properties, and thermoplasticity and elasticity, because they are completely different in molecular level, and this is in one molecule. So here you can see a molecular spring, because really a chain is a molecular spring, and you can see here that I have 4 carbons, and you see the 3 more stable conformation of each carbon, which is trans, which is extended, and 214 cos plus or cos minus. So when you apply a force on this molecular spring, the chain is extended through this mechanism. It means that you give more energy, so the conformation goes and and plus or minus, they can overcome the energetical barrier between gauze and trans, and so the chain is folded. Now, but if you have, for example, the polyisoprene 1,4-cis, no, the trans, the polyisoprene 1,4-cis, and you apply a force on the spring, so there is nothing, there is no any elasticity. There is thermoplasticity because it's a linear structure, is not a cross-link structure, but the chain or the spring is moving from one position P0 to P1. Now, if you vulcanize the polyisoprene cis-1,4, you create the cross-link. So what happened? It happens the following: you apply the force, the spring becomes longer, and if the force is released, the spring is coming back. It's like I usually say, the material has a primitive memory, remembers the first dimension. So in order to do that, you have to have cross links, and the cross links represent the fixing point of the chain. So in order to have elasticity, you have to have a cross-link structure, cross-linking, but the cross-linking should not be very high, because otherwise it will be hard, your material. You remember ebonite should be the density of the cross-links should be not very big. Also, you have to have the flexibility. For example, if you have polystyrene, you cannot have the elasticity. And also, like I said, the molecular weight between the cross links should be the density should not be so high. So again, you have here the vulcanized rubber, which is elastic because it's cross-linked, and the polyisoprene, which is linear, is thermoplastic. So we can use the chemist, the polymer chemist, many years ago, they found another way to create the cross links. And this is the physical way to create the cross links. So you have there a tri-block polymer, which is a polystyrene block, the polyisoprene cis-1,4 in the middle, and polystyrene again at the end. So because the polystyrene and the polyisoprene, they are not mix each other, they form microdomains, and these microdomains, they act like cross links. So at room temperature, because the Tg of the polyisoprene, of the flexible chain, is below the room temperature, is flexible. The Tg of PS is above, is 100. So creates these microdomains that they act like crosslink. So at high temperature behaves like thermoplastic, and at low temperature behaves like elastic. So you have in the same molecule the two properties. So here is again, this is the polyisoprene matrix, and please see what I put a tri-block polymer, and in order to clarify how this is going to the materials, you see that the two blue are going to the blue microdomains, and the other is the elastic part. So if you have the inverse tri-block polymer, for example, if you have the polyisoprene outside, the polystyrene inside, is not a thermoplastic elastomer, because the matrix of polyisoprene is broken. So see again the molecule, how it's going, and you can see that the matrix is broken. So let me say a few things about brocopolymer microphase separation, because it's very important for thermoplastic elastomer. You have the phase diagram on the axis of X. You have the interaction parameter chi. This is a Greek letter. I don't know why it's pronounced like as chi. It's chi multiplied by the overall degree of polymerization. And here you have the volume fraction. And you can see that depending on the volume fraction, you have different microphase separation. You go from spheres to lamella, and when the minority component becomes bigger, you have the mirror image of the first morphologies. So let me show you here how a lamella morphology, for example, here how a lamella morphology is formed, and you see that this is in molecular level. So it's very logical, and it has been proven that the shape is fixed by composition and the dimension fixed by molecular weight, meaning that if you have the same molecular weight, the same composition, you have the same microstructure, but if the molecular weight is double or triple, the dimensions are bigger. Now, most of the commercial thermoplastic elastomers, there are linear, or I told you that there are a few star-shaped block of polymers. So, but I think that I gave these numbers, but Professor Clerk, I think that Dr. Clerk of Creighton can have more accurate numbers. So how we prepare? We prepare that in the lab, and the industry is preparing is by anionic polymerization. Is one of the few few materials that they are formed by anionic polymerization, because anionic polymerization is very difficult to carry out, but there is no any other way to produce this polystyrene, polyisoprene, polystyrene triblock copolymer by another method. Okay, so here is very important also. You have a triblock copolymer that has the same molecular weight, but because of different morphology, you have different morphology. You have different stress strain diagram. You see here the sphere has a very low stress, and the best is this is a gyroid morphology, where two interpenetrating but not touch polystyrene network is in a matrix of polyisoprene. So here is this Creighton thermoplastic elastomer with 30%, for example, is a perfect, has a perfect cylindrical structure, because here you have the hexagonal you have the hexagonal fingerprint of this morphology. Now, the commercial is the linear Creighton Styroflex. Now, we thought that if you have only linear polymer, you cannot change a lot the properties of the thermoplastic elastomer. So we design and we have prepared this kind of complex macromolecular architecture. Here you have the Creighton, but the PI is a polyisoprene homopolymer. Here you have the three linear, you have combs, and here in the middle you have, instead of having homopolymer, you have a diblock copolymer, for example, polyisoprene and polystyrene. Also, we have prepared the regular craft copolymers, which I mean by regular craft copolymers that the distance between the branch point, the junction point, is exactly the same. So we know exactly what is going on, because in this case, in the case of the comb or graft, we don't know exactly where is the position of the branches. We can arrange the molecular weight of the backbone, we can arrange the molecular weight of the branches, the number of the branches, but we cannot arrange the position of we cannot control the position of the branches. And here are some more complex macromolecular architecture. I'm going to talk today about these regular graft copolymers. We are using the high vacuum technique. It's a very difficult technique, but in my opinion, it's the only technique to prepare well-defined polymers. We are using the break seal and the breakers in order to liberate the different compounds. And here, this is constrictions to remove by heat sealing this part of the reactor, because this part is only for rinsing the reactor, for purify the reactor in order to be sure that the reactor is very clean. Of course, this technique cannot be applied in the industry, but this technique is guiding industry through the right product for a certain application, because here you have model polymers. You don't have the influence of the polydispersity. You don't have the influence of the composition dispersity or of the structural dispersity, and you can study very well the structure properties relationship, and you can find an appropriate material for a certain application. Of course, after the industry has to find industrial feasible method to make these polymers. Maybe the polymers are not so perfect, but they instead of 100%, they take advantage of this structure 80%. But at the end, even this 80% or 70% is very important for industrial application. So what we are doing, I'm not going to say many things about chemistry, because it's much better to talk about properties. So we are making the two molecule that has two chlorine, chlorosilane, and two polystyrene, and after a difunctional polyisoprene. So we do polycondensation. This is like an ester and diester and diol. So we obtain this regularly spaced tetrafractional, in this case, branch point. So, but as you know, the polydispersity from the polycondensation is 2 or a little bit higher. Theoretically it's 2, but a few times it's higher, and we have to fractionate. Okay, that's why I say that this method is not good for industry. We have to fractionate. So we fractionate, and finally we have, for example, the polystyrene arm here, a few examples, the polyisoprene connector, and after the fractionation we have very low molecular weight distribution. And here is, in order to understand how good are the polymers, this is the multi-top of one of the branches of this polystyrene branch, and you see that this is very symmetric and low polydispersity. So how we prepare the others? The others, we can have the corresponding dichlorosilane compounds. Here is the dichloromethyl polystyrene, the silane, and we make the trifractional. And here is the tetrafractional with 2 chlorines. So all of this at the end is the polycondensation, and we have to fractionate. So you can see here many many polymers we have prepared, and the first number is the number of the number of branch at each junction point. The second is how many branches we have, and third is how much % of polystyrene we have in this molecule. So we have 9%, 21%, 36, and 67. All of these are situated at the strong segregation limit, because we prove that the morphology of this complex macromolecular architecture copolymer is the same as the morphology of the constituting block of the copolymer unit. I mean, if you cut this tetrafractional graft copolymer between the branches, and you obtain this, which is a star polymer, polystyrene dipolyisoprene tetrafractional copolymer. The morphology is exactly like the morphology of the star, corresponding, of course, to the graphs. And you can see here, I'm not going to go through that almost all, and I will show you in a few minutes, all of them is almost very close to what the theory predicts. Here you have 67%, 10 branches. This is four branches. I mean, it's up and down, but the point is tetrafractional. Cylinders, sacs, and this is the theory predict that this is between cylindrical and bicontinuous structure, but that's okay because the bicontinuous structure area is so the window is so small that it's okay. This is, and here we have 3 linear, and you can see here that by ZAX and by TM, of course, we stain the polyisoprene by osmium tetroxide. You can see that there are all lamella. So there is another observation one can do here is that as the number of junction points per molecule increases, the ability to form well-ordered morphology is hindered. So first of all, these are the same initial polymer, but after fractionation, we obtain 5 or 9 or 12 branches. So according to the theory, and is proved by that, is lamella. But the lamella, the order of the lamella is going down as the number of branches is increasing, and this is logical because it's very difficult to be separated because the macromolecular architecture is much more complex. If the molecular weight, the degree of polymerization is higher. So it means that maybe if we live for 1 month, will be the same. So here is a hexafractional graft copolymer, and you can see the lamella, the theory predict lamella, but you can see again the same thing, that when the number of branches are going up, this is are going up, the order is hidden. Now here is the stress strain diagrams, and you can see here the styroflex, which is triblock copolymer, but the middle block is a styrene butadiene radon copolymer with 58% polystyrene, the craton of cell 22%, and you can see here that 22%, but you see that has almost the same stress, but the 2 times the strain. So what the message is that by playing with the architecture, and the architecture is a factor that we have to consider in order to change the properties. Here is the craton, excellent morphology, and here is disorder, cylinders. And despite this fact, they have much better properties. And the reason is the following, that if you have a linear copolymer here, this bridges only 2 cylinders of the polystyrene. The black is the polyisoprene. But if you have a graft copolymer, in addition to this bridging, you have a chemical bond between the individual triblock copolymer. So that's why it's much stronger than the linear one. Now here you can see better tensile strength and number of junction point. When it's going up, the tensile strength is going up. Here is the strain the same. Here what you have 3 you have three polymers. Here is the same number of arms, the same functionality, and the same number of arms, but you see that there is a big difference. The higher the number of arms here, the higher the polyisoprene. Of course, you have much higher strain. So here, while strain at break is less influenced by functionality, the tensile strength of the cylindrical forming tetrafractional multigraph is about twice that of the trifractional material. So you see here the influence of the functionality on the properties of the polymer. And here you see also that we separate the influence of molecular architecture from the junction point. Different morphology, and you can see here that you have different strain and stress. So again, the tensile strength in function of the number of junction, and you see that the hexafractional has much higher tensile strength. Anyway, because I don't have a lot of time, I have 5 or 7 minutes in order to leave the audience to ask questions. My conclusions are the following: that anionic polymerization, high vacuum techniques lead to well-defined thermoplastic elastomer with complex macromolecular architecture. Functionality of graft copolymer influences the morphology and thus the mechanical properties of these materials. And with increasing the number of junction points, the grain size, the order of the microphase separated morphology decreases, and strain at break and the size increases. So tetrafractional multigraph copolymer, so high super strain at break, far bigger than in the case of the linear thermoplastic elastomers. So this work is mainly done at the University of Athens when I was there as professor. So let's talk about the novel thermoplastic elastomer based on dynamic covalent bonding. And this is preliminary results. And there are a few patents going, so I cannot show a lot of these results. These are unpublished results, but I would like to share with you. So this, a big part of my group in Saudi Arabia is dealing with this dynamic covalent bonding, but what I'm going to present is the work of Dr. Saibal Braunik and Dr. Kostas Datsikas. Saibal is a postdoc now for 4 years, and Kostas is a research scientist. So elastomers are cross-linked, okay, but the thermoplastic are non-cross-linked. Now, Francesco was speaking about the thermo-reversible bonds, about the disalter bonds. These are not thermo-reversible. These dynamic covalent bonds at a certain temperature, Vitrimer temperature, they change partner, and the system start to be a little bit mobile. So you can change the shape of this material. It's like you have 10 couple and they are dancing, and during the dancing they change partners. The number of the bonds stay the same. They are not reversible. Okay, this is exactly like glass. That's why the name is vitrimers, and this is from vitrum, which is in Latin is the glass. And they have areneous behavior. So here is polyisoprene. Both ends, they have the aldehyde, and we are using triamine. So we create the network. And this is a vitrimer with elastic properties. But this thermoset, or this cross-link material, you can reform, you can recycle. Okay, and you can see here the creation of the network. And this is liquid. This 12,000 molecular weight of polyisoprene, 1,4, 6,1,4. We have made many, 2, 4, 6, and you can see that is thermo healing, and you can see that this is solid. And here there are a few stress relaxation measurements at different temperature in order to show you, these are the results of SciBal, to show you that this is areneous behavior. So let's go now to the thermoplastic elastomer. Okay, so I don't know, maybe people in industry, they can help me to find other application. I thought that for scientific point and for industrial point, because these bonds exchange partners, that will be a very good to prepare a triblock copolymer based on this dynamic covalent bond. And we use the imine dynamic covalent bond because it does not need any catalyst. So here is self-healing. But let me show you that you have here, here is the diblock copolymer, 4,000 polystyrene, 12K, because we are going to create a triblock. This is highly viscous, but after the reaction with the diamine, you obtain the solid. You can prove, of course, by FTIR and GPC, and you have to have an excess of the amine terminated polymer, otherwise you don't have any exchange. Okay, so this is NMR. I'm not going to go through. This is another polymer with different molecular weight, and here you can see that this is like the normal triblock copolymer at this composition. Another one here also you can see that these are cylindrical. Now this is the interesting about self-healing. Okay, here you have the dynamic polystyrene, okay, the dynamic triblock thermoplastic elastomer. Here you have the diblock, here is the stress strain. Diblock is very weak, and after you have the real triblock copolymer, and you can see that almost this dynamic covalent bonding triblock copolymer behaves the same. And here is the self-healing in 3 hours, in 2 hours, 3 and 6 hours. And you see that the blue recovers the initial mechanical properties of the thermoplastic this thermoplastic elastomer. And here you compare the covalent bonding thermoplastic elastomer, and here is the dynamic thermoplastic elastomer, and see at 6 hours after healing, this is much stronger, or recover much more of the initial properties, the dynamic covalent bonding TPE. Now let me take my conclusion and give you time for question that these are exploratory results on dynamic covalent bonding. These are very promising, I think. Vitrimers are not still in industry. I know a few companies, Mared, for example, and they try to sell these vitrimers. And so the properties that we found until now is better self-healing. It has better self-healing properties, but also by acidic hydrolysis, you can go to the precursor. So with that, I would like to thank you very much for your attention, and I will be pleased to take any question. And also, I would like to add that it's the first time I am speaking to my computer. I don't see any face. I see only my slides, and it was very hard for me to speak like that. Okay. Thank you very much.
Thank you very much, Professor Hadjichristidis. Thank you very much, Nikos. Evaristo. Indeed, it's hard to talk to your computer.
Now I see you.
Now you see me. Well, it's a feeling we all have been having actually in the last couple of years, let's say. I would suggest that I actually don't know whether it's possible for the audience to ask questions, or it's just restricted actually to the speakers and other organizers.
Francesco, I think it is possible for the audience to write the question in the question box. In the question box, they can write, and then if there is any question, you can read it out.
You can see and you can tell me the question.
Yeah.
Yes. Otherwise, Francesco, you can also ask questions if you like.
Yeah. Okay. No, I see the questions now. So I'm just going to read it for you, Nikos. I think chronologically. We know that materials and the recycling of these materials is becoming a major challenge in the industry. My question is, what is the cost of the recycling operation? How much would it recycle these polymers?
Yeah, but for the moment, I tell you that I don't know exactly the numbers, but this is the initial step. So, in my opinion, he has a long way to go in order to be commercial products. Okay.
Okay.
Because
this one which is very interesting. Do you think that these defunctionalized TPEs could lead to 3D printed products like tires? Can you 3D print these materials?
Right, but the thing is that, for example, the good thing about the vitamins is that you can recycle to the monomer. You can get the monomers. So zero waste. You can go to the monomer precursor. You can go to the precursor of the network. There are many possibilities. But I think for the moment we are. I mean, I am a professor at the university. Okay, I think that industry has to think to find a way to, in collaboration, of course, with us, the way to diminish the price of this of the recycling.
I think we have time for a last question, which was also my question. So somebody else actually anticipated me. I think it's a very interesting one. Is it possible to use this graph, the SBS, as a shape memory polymer?
Yes, of course. This company, they are using that for that, and also for the previous. He was asking about 3D printing. They are using that for 3D printing. Okay. Yes.
Okay.
There are industry that is using that already.
We are rightly on time, which is very peculiar for two South European, but still we are precisely on time. So I would suggest to thank you again, Professor Hadjichristidis, for the nice presentation. Thank you very much. And I would like then to move to the next speaker. Yeah. So that's two in a row. It's also a very great pleasure for me to introduce to you Professor Norbert Vennemann from Germany. Yeah, we see his presentation. Just a few words about him. Actually, he did all his studies in Osnabrück, which is in Germany, obtaining a diploma in physics in 1983 and actually a PhD in 1987. He has a very long career, full actually of very nice publication, patents, and everything. He started actually in Continental in Hanover as head department for R&D or coordination of material testing. I'm not going through all of this, but he was also later on head of laboratory polymer testing and rubber technology. the Dean Study of Affairs of the Faculty of Engineering, also at the University of Osnabrück, honorary professor actually of rubber technology in Thailand. And if I understand correctly, in 2019 he retired, but he says here in his CV that since that moment he's an independent consultant on rubber technology, which I think is well, probably keeping him busy even after his retirement. And he's here today to talk about thermoplastic elastomers, process properties, and recent applications. So, Professor Vennemann, it's a pleasure having you here. Please take over the virtual floor, and we're waiting for your presentation.
Thank you very much for the nice introduction. I hope you can see me and hear me. I only see my computer.
Yes, we can.
Okay, that's fine. So welcome to everybody. Good morning or good afternoon, wherever you are. And yes, my presentation is about process properties and recent applications of TPEs, thermoplastic elastomers. And I think it's more focused as an overview of the, I think, big class of thermoplastic elastomers. We heard a lot of special details of some special kind of thermoplastic elastomer, and my talk is more an overview of, yeah, let's say also commercial products, and I would like to give you an overview of this class of polymers. This is the outline of my talk. After a short introduction, I would talk a little bit about structure principle of thermoplastic elastomer. Classification is necessary because there are so many different kinds of thermoplastic elastomers. And after that, I will briefly summarize structure and properties of most important TPE classes. And then I will focus more or less on thermoplastic vulcanizates and recent developments. And finally, I will give a short outlook. So I think most of you know that thermoplastic elastomers cover a wide range of applications, starting with automotive, construction, cable and wire, sports and leisure, a lot of consumer products, medical application, electronics, footwear. I think I could say that thermoplastic elastomers are part of our daily life. And I think maybe the world would not be so nice today without thermoplastic elastomers. So the usage of thermoplastic elastomer is because TPE offer a lot of advantages. At first, one advantage is that TPEs can be processed like other thermoplastic materials, which is a very big advantage. And the products produced in this way exhibit rubber elastic use properties, so they can replace, substitute rubber products, but even a lot of new products and applications can be realized with this nice materials. And last but not least, these materials can be recycled. They are recyclable, which is also very important today. Yeah, summarizing some more details of TPEs in comparison to conventional elastomers. The producer of products obtain granules ready to use. They can be in a melt processable production. They don't need vulcanization, and the cycle times to produce products is very short. That means these materials are very cost efficient. Then another point is TPEs are very innovative. They are easy to combine with hard plastics. You can produce 2-component or 3-component injection molding and co-extrusion parts. They are easy to color. And last but not least, TPEs are sustainable. You can recycle production scrap, and even you can recycle the products after end of use. Apart from these advantages, of course, there are some disadvantages of TPEs, and they have to be considered. One big disadvantage is that TPEs exhibit permanent set after high elongations, as you can see here in this diagram, where tensile stress is displayed over strain after intermittent tensile tests. So if you increase the strain and release the sample, the original length is not recovered fully, but there is a permanent set, and this permanent set is increasing by increasing the maximum strain. So that the behavior of thermoplastic elastomer is not fully the same as conventional elastomers. This has to be considered. Also, creep and stress relaxation is an issue. Creep and stress relaxation are normally higher than in case of conventional elastomers. Another point is that the heat resistance of TPEs is much more limited than conventional elastomers, and also the oil and fuel resistance of TPEs is often not as good as special elastomers. The differences of TPE and rubber become quite obvious in this test, temperature scanning stress relaxation. This is a very simple test. The sample is stretched at a constant strain of about 50% and then heated up linearly. In case of a conventional rubber, the stress is increasing as a function of temperature slightly, and this is caused by the entropy effect. The polymer chains are oriented in strain direction, and they want to come back to the original form, and therefore the stress is increasing. At very high temperature of about 170 or 180 centigrade, the network becomes degraded, and then the stress is going down. In case of TPE, the entropy effect is only obvious in the initial part, and at about 50 degrees, depending on the TPE, the stress is going down rapidly, much stronger than in case of conventional elastomers. So this is a big difference of TPE and rubber, the stress relaxation behavior and the creep behavior, and this is due to the physical crosslinks in case of TPE and the chemical covalent bonds in case of rubber. So the weak points of TPE are summarized in the slide. I think one very big weak point is the dynamic behavior. So I think it's not possible in the near future to produce tires from TPE. because the dynamic behavior of TPE is not as good as conventional rubber. The elasticity is not as good, the damping is higher, plastic deformation is higher, creep, stress, and so on is higher. And the surface temperature range is limited, as I told before, because of the thermo-reversible cross-linking. And that means also that the fail-safe behavior is more critical. So if you think about an conventional elastomer is heated up slightly above the maximum temperature, then okay, the conventional rubber will not fail immediately. But if you do this with a thermoplastic elastomer, if you increase the temperature too high over a certain limit, then the TPE will fail immediately, and it is not reversible. Oil and fuel resistance is also a little bit poorer than conventional elastomers. And finally, in most cases, the material costs of TPE are slightly higher than conventional elastomers. To understand the behavior of TPEs, we have to compare the structure of TPE with the structure of rubber and elastomers. So in this simple slide, I've drawn a picture about the amorphous morphology of the raw rubber, let's say made from polybutadiene. It's a flexible polymer chain, and all raw rubbers are based on amorphous polymers, polybutadiene, SBR, EPDM, NBR, and of course natural rubber. All these raw rubber have a very high molecular weight, and per definition, the glass transition temperature should be lower than 0 degrees centigrade. The raw rubber is not cross-linked, and the raw rubber turns to the elastomers by cross-linking the raw rubber, and therefore you need additional ingredients like curatives, and in most cases we have fillers, plasticizers, antioxidants, and other additives. So the elastomer compound is a very complex system. And finally, we obtain cross-linked polymer chain, and in combination with filler and other ingredients. Thermoplastic elastomers have a structure which is a little bit different from this, and the structure principle of the TPEs is shown here on this slide schematically. In each case, TPE are generated by a combination of thermoplastic hard phase and a rubbery soft phase. And this can be done in two different ways. On the left side, you see a continuous soft phase and dispersed hard phase. This is realized by microphase separated block copolymers with crystalline or glassy hard blocks. So in this case, the matrix is a soft phase and the hard phase is dispersed in this soft phase. Another way is shown on the right side of the slide, a continuous hard phase and a dispersed soft phase. So in this case, the matrix is a hard phase, and inside the hard phase we have some islands made of soft material, and this can be done by heterogeneous polymer blends with island matrix or co-continuous phase morphology. Two different ways to produce thermoplastic elastomers, and therefore we have a lot of different materials on the market which can be named as thermoplastic elastomer. So it is necessary to classify these group of polymers, and this is done in the standard EN ISO 18064. And here you can see the abbreviation. It's, for instance, for thermoplastic polyamides, TPA, or thermoplastic copolyesters, TPC, and so on. And some extensions are also useful to describe the structure of the TPE in more detail. Generally, the TPEs can be divided into three major groups. One big group are formed by the block copolymers, and the other group is made of a simple polymer blends, and at least the third group is made of reactive polymer blends. So in the last presentation, we heard a lot of tri-block copolymers commercially available. A lot of others, multi-block copolymers, thermoplastic polyamides, thermoplastic copolyesters, thermoplastic polyurethanes, and of course TPEs, the styrene block copolymers. These styrene block copolymers are a special group of copolymers because they are often combined with another thermoplastic component. So they are tri-block copolymers, but also belong to the group of simple blends, as I will show later. The next group, the polymer, the simple polymer blends, consists of thermoplastic polyolefin blends, and a lot of other polymer blends are also called polymer alloys, and the abbreviation for this is TPZ. And in my presentation, I will a little bit focus on the reactive polymer blends, especially on the TPV, the thermoplastic vulcanizate. I will briefly try to explain the differences between this different types of TPEs. And here I would like to explain first the structure and properties of multi-block copolymers. The general structure is a combination of hard segments and elastomeric soft segments. The hard segments, H, are formed by a regular polymer chain, or here by the monomer A, and these hard segments are able to crystallize. And these crystallites are the physical crosslinks inside of the material. The soft segments are irregular and amorphous, and therefore build the matrix of this material. The different types I already explained are polyamides, polyesters, polyurethanes. These are most important commercial products, and this can be realized by very different combinations of monomers. The simple blends are made of at least two different polymers, and there are three possible phase morphologies, and the first is here the rubber first phase dispersed in the thermoplastic hard matrix. If you produce materials like this, you will obtain impact modified thermoplastic. So the rubber phase is nicely dispersed into the hard matrix, and this will lead to toughness, higher toughness of the material. But this is not a thermoplastic elastomers. In the second case, the hard phase is dispersed in the soft rubber phase. And I think this materials is not useful to produce because the mechanical properties are not very good. Interesting for the thermoplastic elastomers is only the lower part. And here the co-continuous phase morphology of the thermoplastic hard phase and the rubber soft phase is realized. So we have two phases interpenetrating each other, and this is the structure of the TPEs made from simple polymer blends. To obtain this morphology, we have to consider two conditions. The first condition is that the viscosity ratio of the blend polymers have to be in a certain range. If the viscosity ratio is too high or too low, then we obtain a dispersed phase B or dispersed phase A only in a certain range. A co-continuous phase morphology is possible. And second, the thermodynamic conditions of miscibility have to be fulfilled. Coming now to the reactive polymer blends. So polymer blends can be divided into simple blends, as I have shown before. These are physical mixtures, and we can obtain different morphologies depending on the interaction parameters. And the reactive blends are made by special production processes where chemical modifications may occur. For example, Raff reaction, cyanidization, and in particular dynamic vulcanization, as in the case of thermoplastic vulcanizates. And I will briefly focus on this type of thermoplastic elastomers, so-called thermoplastic vulcanizates, because these are very interesting materials with a very high growth rates in the last decades. So the composition and structure of the thermoplastic vulcanizates are shown in this slide. The main components of such materials are the thermoplastic polymer, mostly in commercial products polypropylene, the rubber, mostly EPDM in commercial products, mostly these compounds contain filler, for instance, calcium carbonate, some plasticizer, especially paraffinic mineral oil, and finally curatives to perform the dynamic vulcanization, in many cases phenolic resin. And then we should obtain such a morphology where we have a continuous hard phase formed by the polypropylene and a dispersed soft phase, in this case EPDM This soft phase consists of cross-linked rubber particles, and the size of the domains is in the range of about 1 to 5 micrometer. So the TPV consists of two different polymers, a thermoplastic polymer A and a rubber B. It is necessary that the polymers A and B are partially miscible with each other, so that microphase separation occurs during mixing. Then the formation of hard to soft phase occurs, and the thermoplastic matrix and a finely dispersed rubber phase is obtained. The formation of the morphology occurs during the mixing process, and therefore it is very important to optimize the process parameters. And during the mixing process, a reaction occurs, and this reaction is a dynamic vulcanization. And the production of the TPVs is performed by means of twin screw extruders or an internal mixer. So, composition and structure of thermoplastic vulcanizates are very complex. We have a lot of parameters which influence the final properties, as they are hardness, stiffness, tensile strength, compression set, and other properties. And here I tried to show the main parameters of influence. So we can influence the structure and properties of the TPV by the recipe. Very important, the blend proportion, the plasticizer content, the filler content, and the curative system. But also, and very important, are the rheological properties of the polymers used for this compound, the shear viscosity, elongational viscosity, viscosity ratio of A and B, the elasticity of this, and capillary number have an influence on the morphology and the structure of the final product. And of course, we have to consider the thermodynamics. So the free enthalpy has to be lower than 0, and we have to consider the interaction parameters of the blend partners. And finally, the mixing process itself has a big influence on the properties of the material. For instance, the screw geometry, rotational speed, the temperature in the extruder or mixer, and the throughput. And all these parameters have a big influence on the morphology and have to be controlled. And only if a very good combination of these main parameters are used, then we can obtain materials with the desired properties. What is possible to produce TPV? So there are, in principle, many combinations are possible. Natural rubber with HDPE, nitrile rubber with PVC, nitrile rubber combined with polypropylene, epoxidized natural rubber with propylene, polypropylene, etc. A lot of combinations are possible, but until now, only few combinations are useful and commercialized. Most important are TPV based on EPDM PP, most important for industry. And the first product introduced into the market by Monsanto in 1980 under trade name Santoprene. Until now, a strong growth of this group of TPE has occurred, and a lot of additional producers are on the market nowadays. And also new developments of high oil and high temperature resistance TPV are on the market. For example, TPSIV. This is a silicon-based TPE in combination with TPU. And another type is Theotherm from Xeon Chemicals based on ACM and polyamide 6. So, as I shown before, thermodynamic conditions have to be considered, and the miscibility of polymers is only fulfilled if free entropy is lower than 0. And from this thermodynamic equation, the Flory-Huggins equation has been developed, and in this equation, the Flory-Huggins interaction parameter is very important, and miscibility is only possible if the interaction parameter is lower than a critical value. But for TPO and TPV, a single-phase mixture is not desired because we want to have microphase separation and not a single-phase mixture. So the aim is to produce a mixture with a co-continuously microphase separated blend morphology. Under thermodynamic view, different cases of mixture may occur. A single phase mixture is only possible if the interaction parameter is smaller than the critical value. But for TPE or TPV, we don't want to have this case. We want to have phase separation. But the phase separation should not lead to very coarse morphology, but to a very fine, finely dispersed soft phase. And therefore, the interaction parameter has to be in a certain range. A little bit higher than the critical parameter, but not too high, because then the blend turns into an incompatible blend with a very, very high domain size. So that's not wanted. We want to have a very small domain sizes, and this can be controlled by the solution parameters of the two blend components. So if the interaction parameter is close to the critical parameter, then the thickness of the phase boundary layer is thick, and the adhesion between the two phases is good, and we obtain good mechanical strength and good creep and relaxation behavior. If the interaction parameter is too high, then the interfacial tension is high, the thickness of the phase boundary layer is thin, and the adhesion between the two phases is poor, so we obtain poor mechanical properties. Apart from the thermodynamic conditions, the rheological conditions have to be considered. As in the case of simple blends. And the co-continuous phase morphology exists only under certain conditions. The viscosity ratio and the volume fracture are very determining parameters, and only in a small range we obtain the desired co-continuous phase morphology. And the picture of this co-continuous phase morphology is shown here in this micrograph for an EPDM PP blend. So the co-continuous phase morphology is a starting point for the dynamic vulcanization. So at first, the two polymers has to mix together and have to form the co-continuous phase morphology, and then the dynamic vulcanization, that means the selective cross-linking of the rubber phase occurs under high shear forces during the mixing process, and this leads to the phase inversion and to the dispersion of the rubber particles in the thermoplastic matrix. This process normally is performed in a twin screw extruder, which is shown here schematically. The flow direction is from right to left. At first, the thermoplastic polymer is feeded into the extruder. Then, per side stream extruder, the rubber is filled into the extruder by a gear pump. And in this part of the screw, the formation of the co-continuous phase morphology occurs. If this is done, the curatives are added into the screw, into the extruder. The curatives have to be nicely distributed in the blend. And finally, at the last part of the screw, the dynamic vulcanization and phase inversion occurs, and the final product is the dynamic vulcanization. To perform this in industrial process, it's necessary that the length to diameter ratio is very big. It's about greater than 54. This is because the residence time of the blend should be at least 40 to 80 seconds, because it's necessary for the dynamic vulcanization. If the residence time is too small, then the dynamic vulcanization is incomplete and the properties are not good. So, and here we have a contradiction. High rotational speed leads to a good dispersion, but also to a very high throughput and to a low residence time. So this could be a problem, because cross-linking and phase inversion can be incomplete, and that means this leads to poor mechanical properties. So I think it's necessary to have a lot of know-how to produce TPB in this process, which exhibit very good mechanical properties. But I think the industry is able to do this, but they have to consider all these complicated conditions.
Professor Vennemann, unfortunately, we are running a little bit out of time, so I'm wondering if you can start wrapping up your presentation.
Okay, maybe should I stop immediately, or do you give me some minutes?
We still have a couple of minutes, so
okay. Then I would come to some new developments, super TPV, which are a combination of silicone rubber and thermoplastic polyurethanes, or acrylate rubber and nylon 6. And rather new development from Freiburg TPE, this is Hypex. This is dynamic vulcanized ethylene vinyl acetate rubber in combination with thermoplastic copolyester. And let me please introduce a very new material, which is named Thermoplastic Elastomer Hybrid, TEH. What is the difference between TEH and TPV? As I showed before, TPV are based on a binary combination of two polymers, thermoplastic and rubber, and this TEH consists of at least 3 different polymers: a thermoplastic polymer, a TPE, which in this case is a multi-block copolymer, and an elastomer, a special elastomer. And this ternary blend, which is also dynamic vulcanized, leads to material properties very close to elastomers. So let me please summarize. New technology poses new challenges for TPE, and most important requirements result from electromobility, hydrogen and fuel cell technology, alternative synthetic fuels, autonomous driving technology, novel processing methods, for instance, additive manufacturing, and of course, sustainability and circular economy. And I think I could show that thermoplastic elastomers are fit for the future. They are versatile, sustainable, and innovative. And finally, I would like to thank you very much for your kind attention. And yeah, I would be pleased to answer some questions. Thank you very much.
Thank you very much, Professor Vennemann, and my apologies for having to interrupt you. Yes, we do have time for one question, which I see here on my screen, which is the following. Do you think that TPEs can replace natural rubber and SBR for grips application used in sports industry or other allied applications?
Well, sorry, I did not understand.
Do you think that thermoplastic elastomers can replace natural rubber and SBR for grips application, for example, for tennis or for shoes or other sports industry related application?
Yes, I think so. That should be possible. Yes.
But then
I would not say replace, but in addition, additionally, I think TPEs can be used for these applications, but they will not replace in each case these materials. Yeah.
Okay. But then on the top of that, when you say, of course, we cannot use TPEs for car tires because the dynamic behavior, of course, is not sufficient, especially at high temperature. And I can imagine that if you make the sole of a shoe out of a TPE, there, of course, the requirements are much less demanding than for a car tire.
But footwear is a big application area for made of TPU or TPC, which are also thermoplastic elastomers. So that I think this is already done.
Okay. Okay, thank you very much. Unfortunately, we don't have any time for further questions, but thank you very much again for your very nice presentation. And then I would like then with this to move to the next speaker, if possible. And I think he's online. So just a few words of introduction. Our next speaker is Professor Oberdis, and I apologize if I'm not pronouncing this in the right way.
Perfect.
Sorry for that. Yeah, well, I try.
Good try.
Professor Norbert is a trained soft matter physicist. He got actually his degree from the University of Karlsruhe in Germany, and then he proceeded actually at the École Normale Supérieure de Lyon in France, where he received his PhD in 1997. He then moved to the CNRS in France, where, if I'm not wrong, he still is, but now, of course, as a director. He spent also some time in Italy, where I guess he was able to enjoy very nice coffee because he was in Naples. So yes. I hope that was the case. He's now a group leader and head of department for more than 10 years. Again, his research interest is very broad. Well, I guess he will tell us a little bit about that in the coming 40 minutes. Apologies again, we are a little bit late with the schedule. That's my fault. But Professor Robertis, please, the floor is yours.
Thank you very much. Can you hear me?
Yes, we can hear you.
Yes, does this work? Yes, and you can see me now. I don't know if my screen is shared at the moment. Can you see the beginning of my talk?
A nice peninsula at the moment.
Yeah, that is my laptop. Now I was trying to switch on my PowerPoint.
And now
you don't see that?
Everything is all right now.
Okay, good. So thank you very much, Francesco, for the nice introduction. Thanks to all the organizers, in particular to Kinsuk, for inviting me. And thanks to all of you for being here. Now, strangely enough, I don't see anyone anymore, but well, I hope you can see me. You can also see my colleague, Anne-Caroline Genix, who's my closest co-worker. She's assistant professor in the same soft matter group in Montpellier. And today I'm going to talk about nanoparticles and polymers and nanocomposites, in particular studied by small angle scattering. So I hope this works. This is Montpellier. Some pictures of the city. Montpellier is in the south of France, in case you don't know. In the north of Montpellier is this kind of landscape. This is downtown Montpellier. And in the south, as you can imagine from where it is located, within 10 minutes, you're at the sea. And in spite of that, we do work from time to time. And in particular, we do work on polymer nanocomposites. So you have just had two excellent talks about this. So there's for me, only my duty to introduce you the type of polymers and nanocomposites we're working on. So it's basically a multi-phase material with a continuous polymer phase and then a continuous or not continuous hard phase, which are made by hard filler particles in the 10, 20, 30 nanometer range. We've worked with Michelin, for instance, so there's some industrial applications, but we are more on the fundamental side. So there's a bunch of publications coming out of the studies of yes, as you can see, these filler particles are rather ill-defined, and so this is why we call it an industrial system. And today I'm going to focus on a model system. So I don't know if you have the resolution, but if you look at these particles, they are nicely spherical and well-defined, and that makes the analysis a lot easier. So the papers in red here are the ones I'm going to talk about today. In case you want any of these PDFs and you can't find it, just send me an email. Of course, there's not only polymer and filler, there's maybe something else. And for instance, you may have different agents, small molecules grafting on your particles. You may have long chains, polymer chains, and short polymer chains. You may have grafted polymer chains. And so there's some chemical variety. And today I'm going to try to give you a kind of overview of these kind of samples. So the outline of my talk, I'm going to start with, I'm going to try to answer three questions. The first one will be, where are the nanoparticles? And I'll start with an introduction to nanoparticle scattering. So I was told there were many students, so I hope this is going to be didactical. And then there's going to be some results, in particular with small angle X-ray scattering, TEM and simulations. The second part, I will try to answer the question, where are the different polymer chains, if there are different ones? And so in this case, you need an introduction to chain scattering, and then you need small angle neutron scattering. There's an N and not an X anymore. And if I have time, and maybe I'll need only a few minutes in the end, I'll talk about BDS, which is a technique which we used recently to see where small molecules like coating agents are located. So before going into the first part, why would one be interested in investigating filler structure? So I'm taking this example, which results from a collaboration with Chris Robertson from the States. who one day he invited me and came up to me with these kind of experiments, rheologic experiments, which were really funny. It's about the pain effect, which of course all of you know very well. It's about the modulus being softened as you increase the amplitude. And this pain effect for carbon black and SPR, it depends strongly on the number of particles you put there, on the concentrations, the volume fractions. And it also depends to a lesser extent on temperature. Now, if you're familiar with this effect, the thing is that actually there are many explanations out there about what actually causes the effect. And some people say it's the particles, some people say it's the polymer building bridges and they are adsorbing or desorbing. And so Chris picked up an idea of the 1970s saying, well, if we want to really know if it's the polymer and how much of it is the polymer, one way of doing it is moving away the polymer and make a different sample which just doesn't have any polymer, and then look at it. So he made the same carbon black, he made samples, same carbon black in oil, and you can see there's the same type of effect. Now there's no temperature effect anymore, so apparently this is polymer related, but there's the same volume fraction effect and there's the same strain softening, which is called this pain effect. So we thought it was really funny to have these two samples. This is a paste and this is a hard material, and they basically have the same kind of rheological response. Now, if you can say this is not due to the polymer, the question is, do we actually have the same particles in there and are they organized in the same way? So there's a question of structure, and this is why one needs to have a look at the details of these structures. So what can you do? The first thing that comes to one's mind is to use electron microscopy. So this is an example of transmission. You need to cut slices, so you're mistreating your sample, and then you can see hard particles and soft polymer. The problem is, well, the advantage is, of course, that the analysis is intuitive and it is simple. You can see everything. And the problems are, of course, that you can see all the particles, but you don't see individual chains. It's 2D, it's not 3D unless you do tomography, which is very difficult. And of course, we are looking at a very, very tiny piece of sample, and you have no guarantee that actually this is representative of the whole sample. So this, you can imagine by the way I introduced this, that I'm a scattering guy. So the other method or family of methods is done in the following way. It's shining through light, some light, which may be X-rays or neutrons, through a sample with some nanostructure, and then the light or neutrons or X-rays are scattered. And you can then work your way back to the structure from what you measure on your detector and conclude on your structure. In this case, the advantage is that it's statistically relevant. You're averaging over an enormous sample, like typically a square centimeter. Once someone came and built the synchrotron or built the nuclear power plant, it's very fast and simple for you to go there and put your sample and measure it within minutes. And the big problems, of course, are that you do need contrast. You need contrast between the particles and the polymer, or between the different polymer chains if you want to see them. And the biggest problem is that the exact inversion, due to all this averaging and also some other mathematical reasons, it's impossible to do an exact mathematical inversion to calculate your way back from the scattering to this nanostructure. So the data analysis becomes rather involved. So the main advantage of the technique is that it's an average, and the main disadvantage is that it's an average. So you need to do something, in particular combined with other information, a priori knowledge of the system, for instance, something we're going to do today, and also use different techniques, in particular combined with imaging, dynamics, and so on. And I'm going to show you a bit of this today. So coming back to Chris Robertson, if we have these two samples or two types of samples here, two families, and we want to know if they have the same structure, we just put them in the beam. And these are the two intensities as a function of wave vector, which is basically the scattering angle. And you can see that the two curves virtually superimpose perfectly. So there's exactly, or more or less exactly, the same nanostructure in the two samples. And so this makes it a strong case to say that, well, we observe the same mechanical properties and we have the same nanostructure, and we don't have polymer in one and we have it in the other. So this is an interesting case in favor of the networks, filler networks, causing the Kane effect. There's another byproduct of this example is that actually you can do a detailed analysis of what you see and do many tedious calculations, but actually you don't need to do it here. It's not necessary to actually understand your data. You can just superimpose it and it tells you it has the same structure. So I thought that was nice, and we published that a couple of years ago. Yeah, sorry, this is French, but I didn't find any English equivalent. Every day I wash my brain with publicity. So this is just a bit of publicity for you. With Caroline, we wrote up a paper, a review paper about all these techniques of X-ray neutron scattering for polymer nanocomposites. In case you're interested, just have a look. So now let's go into real filler structure and real elastomer. So this is an electron microscopy. You see these aggregates sitting there in your sample. And one way of analyzing that is if you concentrate like in the sample on single aggregates. You can use a priori knowledge. You can say, I know what the particles are. I know how many I put, and then you can build aggregates in a computer. And of course, this aggregate will not produce the scattering you measure, but then you can iterate motions of this aggregate. So for instance, you can move this speed there and then this speed there and so on. And then after each motion, you check if the agreement with your data becomes better. And so your aggregate evolves, and in the end, you end up with something which vaguely resembles what you see on the screen. Okay, so this is a single aggregate analysis called reverse Monte Carlo. It was inspired by loads of work by Rob McGreevy, not working on colloids but working on molecules. And well, I did this colloid stuff some 15 years ago. Now, if we move to more complex samples, then there is no such thing as a single aggregate. You need many aggregates. They are touching, they are interpenetrating, they are interacting, and they are all over the place, and they have different sizes. They are polydispersed. So it all becomes a bit more complicated. And so what we proposed is to put many, many particles, tens of thousands, in a box, and then we rearrange them, and we do the same thing. We check if the agreement with the experimental scattering curve gets better or not. And in the end, you get this kind of intensity as a function of wave vector curve. You see the red curve is actually two curves. It's a theoretical model curve superimposed to the measurement. And so this tells you that this box is compatible with the real sample. Okay, and then you can create many of these boxes and do a statistical analysis. And then, for instance, what you can do is you can count all the small aggregates and all the big ones, and you can set up an aggregate distribution function telling you how many small aggregates there are and how many big aggregates there are. Okay, so in the end, this is a way of getting structural information, detailed structural information in your samples, published a few years ago. Now, here's an application of this method. We use exactly the same type of scattering experiments on different samples at higher and higher concentrations. So these are volume fractions of silica particles in your polymer, and the scattering evolves each time you set up your model, and so you get the boxes, which are families of boxes, and then you analyze them, and you get all the aggregate mass distributions. So what does it tell you? This tells you that, for instance, if you start at the low concentration, 3%, you get some curve, and then it stops at a given aggregate size. And if you increase the concentration, then you get slightly bigger aggregates, and then even at 10%, even bigger aggregates. And at 20%, it jumps to giant aggregates. Okay, so what has happened? Now here we are connecting all the 20,000 particles in the box. So we have one giant aggregate, so we are percolating the box. So if you look at some measure of the aggregation as a function of the volume fraction of your particles, you get this kind of curve. It goes up, it jumps to a saturation value, which is of course the entire box as an aggregate. And this is a log scale, so there's a very strong increase around 12%, which is very nice because in rheology, which is a dynamical method, there's also a jump around 12%. And the sample becomes stiffer and stiffer. And this is exactly connecting to what the previous speaker, Norbert Vennemann, just told us about co-continuous phases. Here we are percolating the sample and we are making hard samples, whereas here we are basically talking about the suspension. Okay. So as an output of all of this, and this first part is almost finished, we have a static identification of percolation in these systems by means of this, obtained by means of this new method, which has the advantage that we don't have to know in advance where the particles are, if they are aggregated and how they are aggregated. Okay, so it's a very general method. Now you might say, okay, I don't trust any computer simulation. So at least you want to have some reassurance about what this looks like. So this is a simulation box with 20,000 particles, and some are in red, so you just see the differences. This is an experimental result of TEM. for each concentration of a slice of 17 nanometer thickness. And this is the same slices, 17 nanometer thickness, cut in the simulation box. And so what you see is something which vaguely resembles your system. You see, for instance, all these voids here, and they are reproduced here. So it does look reassuring. And so this percolation stuff was published just last year in Nanoscale. So that brings me to the end of my first part here, and I come to the second part. I don't see anyone, so I hope you're still there. Francesco, can you say me you're still surviving?
Absolutely,
Anyone
we are
there?
still surviving, and we see your presentation, and we are clearly.
If internet breaks down, actually, I won't see it. I'll start talking to my screen. Okay, I continue talking to my screen. So thank you very much. So the second part, where are the different polymer chains? So you need an introduction to chain scattering and then small angle neutron scattering. Okay. As an introduction to this work, I want to highlight work done by Caroline. I was not involved. Caroline was an assistant, is an assistant professor in our lab, and she was an invited professor with Alexei Sokolov in the States. And together with Vera Bucharova, they worked on these mixtures of particles, okay, each time the same silica particle in very long polymer chains, very short, so 404K, very short ones, and mixtures of longs and short ones. And the nice finding of this article was that the mechanical properties depend on the concentration of chains in a non-monotonous way. There's a maximum there. So something is happening in these strange mixtures. They did some MD simulations. They did also BDS. There's a lot of work done. And we thought, well, we need to know where the different chains are. So this motivated the work I'm going to show you now after this first quick introduction to scattering of polymers in isotopic blends. So what you do is you make a polymer sample. So this is a piece of material. You shine neutrons through, and actually nothing is scattered. So if you measure the scatter intensity as a function of angle, well, there is no coherently scattered intensity. This is because there is no contrast. If you add label chains, typically you will add deuterated polymer chains in a melt here of hydrogenated polymer chains, then you will have different chains here, and so you will create some scattering. And so as a function of angle, this is a very famous curve called the Debye curve, and it tells you how big the chains are, so the radius of gyration. It tells you something about chain statistics. Okay, now we want to go one step further. We want to add nanoparticles. So if we stay in the gastronomical equivalent here, it's adding hard particle in a melt of two types of chains. Unfortunately, no one put a picture on the internet with blue and red chains, spaghetti and some meat anyway. Then the thing is, look at the sample. You now have three parts of which contribute to the scattering, and the scattering is a complete mess in the end. It's very difficult to analyze. And now what saves you is neutron scattering. It has a fantastic property which is related to the visibility of the different ingredients, which are characterized by a quantity called the scattering density, and you can have the H polymer on one side, the D polymer on the other side, and the silica right in the middle. And there's some theory telling you if you go to zero average contrast, which means that the average contrast of the two polymer is right exactly the silica contrast, which is because it's sitting in the middle, it's almost 50-50, then the silica is matched. So I'm very proud of my little animation here. So the silica is still there, but it becomes invisible, and then your scattering turns into a simple polymer scattering. Okay, so that was the school part. I apologize to all the people who already know this, but I was told they were students, so I was trying to introduce this in an easy way. So now let's really look at our samples. We mix short and long chains. Of course, if they are both H chains, then you don't see anything. You get spaghetti, so you need red and blue chains, so H and D, and so short H and long D, for instance, or short H and short D, or the inverse. And these are the three possibilities, H10, D40, and it shows you the nice Debye scattering. This is the symmetric part, and this is the inverse symmetry. And they are just shifted for clarity. Actually, the scattering is almost identical. You can describe it if you're interested in the modeling. I'm not going to go through the equations. What is important is that each chain is described by radius of gyration, which boils down to one parameter. And so now we know this parameter, and so we can describe every chain in the system. We know they are not interacting. There's an interaction parameter in this RPA equation, and there's only a weak upturn here, which is always the same. and weak with respect to what is coming next, where it's going to be a lot stronger. So all of this is just to say, to make sure that there's a miscibility on the molecular scale between the chains. Now, the next point is to put the particles in there. And as I just told you, the zero average contrast thing is saying that the nanoparticles don't have any contrast, and so they should not be visible. So this should be the sample, this should be the polymer, and this should be the invisible particle. So if you make it visible a second, you can look at the particle and it has these oscillations here. And if you now do the experiment of this sample with the particles, you don't see any of these oscillations. So this means your zero average contrast technique worked, okay? And so you don't see the particles, you only see the polymer. And what you see is actually that the polymer has a stronger increase with respect to the weak increase I just showed you. And now we know the particles, they are invisible. We know the particles cannot be modified. So the only thing that can happen in that sample is that somehow H and D chains segregate. They are unmixing, okay? So there's some weird zones which are have more H and more D, and all the rest, of course, the complementary part. And so this gives you an HT segregation. This is not so bad a model we set up. The difficulty is that you don't know the exact shape of your segregated zones. So this is an educated guess, and it's not bad. So it works rather well. Okay. So now you remember that this was for a symmetric polymer, small H chains and small D chains. And now we played this game with many different polymer chains up to 10 times longer. And so this is the H10D10, and we just described it. This is the H10D40, and it is a very similar curve. It's just higher, so a different degree of segregation. And if you go to the inverse, very surprisingly, you get something which is completely unexpected. You get a peak, which cannot be described by the segregation model we just set up. The segregation model is shown here. So these are the curves I already shown for one on the previous slide. And you can see this works very well, but there's no reason to present any peak there. So once you run into a peak like that, you're in trouble, because it takes months to set up a new model. So you kind of need to find a direction. So one thing to check is what does it depend on? So these are small silica particles, and so we also did exactly the same from the big silica particles. And so you see the two segregation models, they work very well for the short H and long D. And again, there's a peak, and the peak has moved. And it has moved exactly by the ratio of the silica size. Okay, so it is related to the silica. It is systematically found, you're going to see many examples, for long H chains. It moves with the silica, and the only thing we could invent, as the silica itself is a ball, it's not going to change anything. It must be polymer sitting at its interface, which is responsible for this peak. So we set up a slightly more complicated model, which combines interfacial enrichment on top around all the silica particles with some bulk segregation zones, which we already described. So basically, there are three ingredients to your equation. What we already had beforehand, the chain scattering, which is the bifactor I discussed in the beginning, and then there's this core shell. This is CS, PCS. It's the shape of this interface here. And getting this right was something like 6 months of work or so. But when you do it, finally, you're quite happy, because then you're really describing the scattering peak in great detail. And you can, once you have the scattering peak, actually, it means that you know exactly what the interfacial gradient looks like. This is for the big silica nanoparticles. It's exactly the same model, and it's nicely reproducing what we just had. So the only thing which is now missing is, what does it look like, the profile? So we are walking out of a silica particle up to its surface, and then we're inside the polymer. And this is what we're doing. We're walking up to the polymer interface. This is the radius coming out of the polymer, out of the silica, excuse me. And then we have a scattering length density, which basically tells you there's more D there, and then there's more H there, because everything in the end, the quantities must be conserved. What I didn't tell you is that actually neutrons are not sensitive to if it's more H or more D, so the exact inverse will also work. The solution is degenerate, and so it has this funny shape, and we thought, well, is this true? And so we took all our samples, and this is just a few of them. You're going to see more points on the next slides, and it always has this funny shape. So if you look at it like this, okay, it looks like some animal. I hope you see the same animal we see. So it looks like a fish, and yeah, we had this very strange interfacial gradient coming out, which has this fish shape if you take into account the two types of solutions. So we were happy to also find fish in science. In analogy, I've also been working on microemulsions in my life, and this is the Kalweit-Strei microemulsion cut. It's a fish diagram, very famous. So anyway, coming back to our fish here, we wanted to understand it, and in order to understand that, you need to understand halieutics. Halieutics is the art and practice of fishing. This is, of course, only a joke. I'm just trying to say that what you need to do is to look at your entire sample, and it's a superposition of your interfacial gradients and the segregated zones. And so they are kind of biting each other here. And all you need to do is set up a model and try to see if this can account for what you're observing. Now, I don't have time. I have the slide. But basically, this is the mathematical model trying to see how the superposition works. And if you do that, then you get a monotonic function. It's not a fish anymore. And it works for small particles, for big particles, and so on. It tells you the extension of your interface, and it tells you how quickly the interface decays towards the matrix. Yes, so this is just to summarize this part. This is a plot with all the samples we had put on one single plot. This is this as a function, excuse me, of the length ratio. So here's the short H, long D, and here's the inverse. And you can see that on the one side, you have only the segregated zones and matrix. And on the other side, you have, in addition, the shell setting showing you that there's an interfacial gradient. And it's all rather robust for all these samples, although there is some scattering. So to summarize this, the neutrons allow us to unravel this combination of interfacial and bulk segregation, which we thought was interesting. We still have the question, who is actually sitting at the interface? Is it more the H or the D? Who is the right solution out of the degeneracy? And actually, we do have thermodynamic arguments in favor of the long H sitting there. But I don't have the time to go into details. Now, what we're a bit frustrated about is what I didn't tell you is actually making these samples as a very time and in particular euro or dollar extensive activity. And so what we would like to do, but we need some big bucks for this kind of stuff. Now that we know the details of the interface, it would be really nice to see how the interfacial dynamics develops. Anyway, we have just published it this summer, if you're interested. And this brings me to the last part. I'm looking at the time. I should just work out a very short trip into where are the small molecules, the coating agents in particular, as seen by a dynamical method called broadband dielectric spectroscopy. The work I show you is work by a PhD, Italian PhD. I'm working with Caroline and myself, Daphne Musino. She worked with silanes. Of course, you all know these type of molecules. We took 3 of them with different lengths of this aliphatic chain here. And then Daphne set up a system with particles in suspension, adding the silane, grafting it, and then mixing it with polymer and getting a nice nanocomposite, completely transparent. L2C is the initials of our lab. Now, this is not the only way you can do it. In this case, you graft it. You can also add it later. If you add the silane here, then you absorb it. And if what is not absorbed goes into the matrix. And the question is, this is actually what is done in many, many industrial processes. You just add the thing and you're not going to take special care and you just hope it's going to the right place. So the question is, how much goes into the interface and how much goes into the matrix? So the answer is given by BDS. BDS is a technique looking at the dipole motion of your polymer, and one of the functions you get is the dielectric loss as a function of the frequency. So for instance, if you take a pure polymer, you got what is called the alpha transition, which is a maximum here, corresponds to a given frequency and a given time. If you now add this C18, for example, in different concentrations, so it's only a matrix and the coating agent, then you can see that the thing moves. And this is precisely the effect we're going to use, because the matrix is being plasticized. And so by measuring the matrix dynamics, we know how much plasticizer is there. And so we know how much C18 is sitting in the matrix. And by subtraction, we know, as we know how much we put, we know how much is sitting on the interface. Okay, so we set up a calibration curve. So this is the typical time as a function of the quantity of C18, C12, C8, and everything we added. And it's a nice calibration curve. And so if you have an unknown sample, you can directly read off from the time, you can read off how much is in the sample. Okay, In real samples, of course, there's going to be less effect. So take this non-grafted silane. Some of it is sitting at the interface with the silica, and some of it is wandering around in the matrix and plasticizing it. So the effect from going up here from this time where nothing happens, it's not as strong. You don't accelerate down to here. You accelerate only a part. The experimental result for one sample is shown here. And well, just by reading off, you're doing a geometrical method. You can say, well, this time is the same as if this quantity were in the matrix. So by determining this quantity, I can know how much is absorbed. And so I can construct an absorption isotherm. Just to reassure ourselves, if you graph the silanes, then nothing ever happens. You stay on the constant, okay? Because nothing goes into the matrix, and so the matrix dynamics does not change. Yep, and basically this is the final result. You have two possibilities. You can graph the silane, then it looks like this. You can absorb the silane, having some H bonding there, and of course you can have the free silanes in the matrix. And the grafting density is typically 1.1 per nanometer squared, whereas our adsorbed densities, they are very similar. There's a lot of error bar because the technique is difficult, but basically the key result of the study is that the adsorbed silane layers have actually the same density than the grafted layers. Yes, also published last year. So I'm done. I hope I'm approximately on time. Just to summarize this, all I told you in one slide. In the beginning, we were talking about filler structure, and SACS is the right technique to see these kind of aggregates, in particular if you use simulations. You can use full modeling with the full box, and then you can called reverse Monte Carlo modeling, and then you can get aggregate mass distributions and even percolations. I had this, what I thought intuitive example of the pain effect, and in our case, it was really due to the percolated filler network, which is breaking up, because we could show that in absence of polymer, the effect is there as well. In the second part, I focused on the small angle neutron scattering. So remember, we had small and short chains either segregated on the interface or segregated in the bulk. And so we had set up a complete model description of these cases. And now, of course, what remains to be investigated the day we earn a lot of money will be the interfacial dynamics. Now that we know exactly who is sitting close to the interface, it would be nice to know what is going on with the dynamics. And the very last part, I apologize, was a bit quick, but it's an in situ determination of where the coating agents were actually located in polymer nanocomposites. And the thing which really pleased us was that once you've measured the adsorption isotherm, it turns out that with the industrial quantities, you know, when you talk to industry people, they, in particular Michelin car tire industry, they always give you like a rule of thumb values of how much coating agent you put. And actually the industrial quantity, which is empirical, turns out to be exactly the quantity which saturates your interface. Yes, I would like to thank in particular Vera and Alexei for the collaborations, nice collaborations. Thomas Chausset from Solvay. Here is in San Sebastian. He's helping us a lot with BDS, and these are local contacts because we very heavily depend on instrumentations like RLL, ESRF, and Soleil, two synchrotrons, and this is neutrons, and these are instruments in the States. So I would like to thank them. I showed you this fish diagram, so I thought Douglas Adams would have said so long, and thanks for the fish. Now, being this the 40 years of the IIT Research Center, I'd say happy birthday and thanks for your attention. Thank you very much.
Thank you very much, Julian. Very nice presentation. You are not roughly on time, you're perfectly on time, I must say.
Okay, good.
We do have time for a couple of questions, so let me check that out if there are questions for you from the audience. Not yet that I see. So then I do have a question, which is the following. So you made a model for these chains at the interface. And you say, well, okay, we still miss the dynamics. But if you consider, let's say, very long chains, the dynamic probably will not be there so much. I mean, they will be probably absorbed at the interface and stay there. The reason I'm asking is that, and that's the real question, can you extend your model, for example, as to predict also the mechanical properties of your composite?
Well, this is a difficult question. Now, first about the long chains, what we look at is not reptation. Okay, we look at alpha relaxation. So the long chains will also display alpha relaxation. So we can look at that. In BDS, then you do have other types of dynamics which may show up, processes which may show up, and they may, for instance, MWS is related to ions wandering around a scaffold of particles. So you do get information on particle rearrangements in your system, and this could be related to the mechanical properties. There are many things related to the mechanical properties, also the local density of your polymer around the particles, and so we had a look at that, and there's a bit of effect of maybe 10% range of density around particles. We haven't tried to put that into equations to see how this would affect the mechanical properties. We are more on the structure dynamic part and less on the rheology part.
Okay, yeah.
But it's a good point.
About the bound rubber, eh? So when you have rubber products, usually you have a layer of rubber which is surrounding your filler, normally carbon black, but also silica, and then that bound rubber has an influence, of course, on the properties, but also for normal composites. So
absolutely,
yeah,
it's just very difficult to work your way from a knowledge of molecular conformations and densities to an overall mechanical property, because, for instance, the percolation of the particles is a very strong it's dominating your mechanical response. So then you might have it modified by what is happening in the close vicinity of the particles, but it's very difficult to disentangle actually all these contributions, which is why we try to measure them separately.
Yeah, I understand. Thank you also for the nice explanations. I'm not a student, but I must say, after your presentation, I think I understand a little bit more about all these kind of things.
Thank you very much.
Thank you.
Thank you both of you. Thanks, Kinzer.
Thank you very much, Julia. Yep, Francesco, you say something?
Also, my duties as a chairman, I think, are finished by now, so I give the word back to Professor Noskar.
Thank you very much, Francesco, for nicely conducting the first technical session. Thank you very much. So we move on to the next session, and I'll be sharing that session. So the first speaker of that session is Mr. Peram Prasada Rao, the CEO, the founder of TechnoBiz. So he has been managing this TechnoBiz in the position of CEO for last 16 years, which is recognized as an international resource center for polymer industries and process technologies. TechnoBiz has been offering global services of knowledge and educational as well as business consulting for rubber, polyurethanes, plastic industries, and process technologies, with training programs, conferences, exhibitions, webinars, publications, and consultation. Also, TechnoBiz has been specialized in publishing reference books for rubber and tire industries, and publishes a bi-monthly magazine called Rubber and Tire Digest in partnership with Rubber World magazine. Professional education is the foundation of TechnoBiz. Since 2020, Mr. Peram has been working on the Know-How Webinar project, which is an online platform for professional education with global and well-experienced experts as resource persons. Before starting TechnoBiz, he worked with rubber industries in Thailand for a few years as an engineer with focus on process improvement and waste minimization. His educational credentials include BTech in chemical engineering and Master Engineering in environmental technology and management. With this brief introduction, I welcome Peram on the screen now to have this, and then the floor is yours, Peram.
Oh, first of all, thank you very much, Professor Kinsuk, for giving me an opportunity to present about TechnoBiz. Welcome you all for this presentation. I have 15 minutes time for this presentation slot. I'm going to be very fast, but most of the information I have provided in my handout. You can download from it. TechnoBiz, established in 2005, it is recognized as International Resource Center for the Industries and Technologies. I welcome you all to join the journey of TechnoBiz. As Professor Kinsuk mentioned, we are in a variety of services, exhibitions, training, webinars, business network, publications, talent search, knowledge test, and we are not just on the polymer side, we're also non-polymer side. Of course, we are on the rubber, plastics, polyurethane, and environmental and energy, water and membrane technologies. Our emphasis is always a combination of professional education, business development, and also the networking opportunities. Okay. Just give you what we're doing for the rubber industries, rubber, latex, and tire industries. As you know, one of the main activities and exhibitions. So due to the COVID, we are into the exhibitions. We have stopped for a while. I'm hoping that we start the exhibitions next year onwards, and we have webinars. We have different types of webinars, know-how webinars, research webinars, technology webinars, even in-person webinars. You can check these website. You find information. I'll give you more information as explain more. Know-how is a pure education platform, and again, all the topics focus on polymers, process technologies. We have short webinars, masterclass, and the virtual forums and things like focus topics. I work with the world-renowned experts in different parts of the world. We have memberships out there, professional member, corporate member, and education members. Now you have some of the experts. You may know some of them already. I work with best in the education, best in the knowledge. So they're from the different parts of the world. I welcome more. We are also working with more new people, and anybody interested to work with us, welcome you all. Just give you a quick glimpse of the who are working with Professor Robert Suster. He has done so many webinars on the know-how webinars. Is a pure education, specialized topics. I'm going to quickly glimpse this one, so you can, if you need more details, you can check our website for more information on it. Okay? So this is Professor Robert Suster, and Dr. Gerard Neumann from Germany is also an extrusion expert. He's giving away talks on extrusion, okay, and mixing technology and silica compounds. Okay, so I'm clicking quickly, so because I have my time is short. Okay, so Terry Chapin is specialized on the rubber molding from US. He's on all the rubber molding topics. Okay, please have a look at our website. You find more information on each topic. Everything is specialized topics on molding. Okay. And here's Mr. R. Lakshminarayana. He's custom mixing and also the oil seals and belts. He did two specialized topics on for the benefit of the industry. Dr. Samar Mandopadhyaya is another expert on the material compounding, material selection. He has a huge number of topics available from us, know-how webinars, very specialized topics again on the compounding, material selection. So please check the website on the topics what we are offering and know-how. It's a pure education subjects and very specialized topics, and mostly aimed for the industry people, professionals, and practitioners in industry. So you can see compounding, tire compounding, various requirements on the tire compounding. So here is some more. Okay, Dr. Samar has contributed more than 20 plus know-how webinars. Okay, I'm going to click. So just give you the quick glimpse of it. Okay, David Hill is a latex guy from UK, and all these topics are on the latex. Okay. There you go. Okay, so Dr. Tapi Tamani is on the molded rubber part, compounding. So he has a couple of topics on the curing systems, oil seals, special purpose rubbers. Mr. Van Wolworth is a specialist on the molding. Okay, all these topics on the molding. So have a look at all the topics. Okay. And of course, here is Professor Kinsuk Naskar as well. He's also contributed a couple of webinars for us, and know-how webinars, compounding, vulcanization, TPE, TPV. So please check our website for these topics. Okay. Dr. CC Ho is on the latex. Okay. And so more topics on the latex technology. Mr. Bruno Milanese from Italy is an expert on the rubber mixing plant design. So you can check his details, and he has 10 different topics. His topics also available in Italian language as well. So we offer different languages. We start offering in different languages, but not just in English only. It depends on the speaker availability and the speaker comfort. Mr. Priyabrata Ghosh is another expert. He's on the footwear, conveyor belts. And also cost analysis of compounds. Dr. M.N. Aji is special in rubber mixing. His topics are the mixing. Okay. Dr. Han Jochen Graf is also a compound expert, injection and extrusion, and he has got a couple of webinars available through the know-how webinar. Mr. E. Palanathan, okay, he's also in the molding, compounding. His topics on the compounding, yeah. And Mr. Stephen Chong is a special in latex foams. He has a topic on latex foam. Dr. Samir Majumdar is no more, sadly. He has contributed to webinars for us. Dr. Dario Nicetti from Italy is coating, calendaring. Karthik Srinivas is a special on the testing and material characterization. He has a couple of topics on the material testing. And Dr. Raj Ganesh is on the rheology and characterization. Okay. And Mr. Kalyan Das is a specialist on the reclaim, so his topics on the reclaim. Mr. Henry Barhin is special on the rheology, so his topics, we have a couple of topics. He'll be adding more topics in the near future. Okay. Dr. Aparna Joshi is on the curing, molding, composites, so she has a couple of programs with us. Okay. Mr. Anil Skaria is a latex guy, latex expert. He has contributed latex industry processing issues. Dr. Brendan Rogers from US is special in the compounding and tire technology. He has a couple of topics, and more topics will be added in the near future. Okay. Mr. Yuka Prasad is specialist on the host technology. You can see all the topics on the host. And so let's, yeah. So please have, all these very specialized topics. I'm only wanted to have you look at these topics so that and Mr. Rai Chowdhury is also on the reverse engineering, product development, vulcanization, yeah. Okay, extruded product. Dr. Joseph Marcinko is on the polymer chemistry and polymer characterization. So yeah, all these, see, you have so many topics. And we also have for the master classes, we have for these master class, we have buffet package where you can choose a number of topics at one time to view. So when we have weekend program, you want to train your whole staff during the weekend time. We have premier package, unlimited access, and unlimited number of staff can join. We have a knowledge test to assess online assessment test for the professional skills and knowledge. It's called TKT. The upcoming program very soon is on focus on the rubber compounding and non-tire products. And you can see the details. Okay, now research webinars. We have other segment is so far I talk about know-how webinar that is purely focused on education. Research webinars is probably focused on promoting the research and what are the research is happening in the universities, to reach out to the industry. We're kind of creating platform. We like to also working with certain universities to organize events, support them as a partner as appropriate. But we are only interested in promote research development which are permitted to share in the public domain only. Okay. All these are topics. I know I had to thank Professor Kinsunaska. Some of his research students have contributed for these research webinars, and these are available through the research webinars. We have from the Mahidol University and also King Mongtu University here in Thailand too. Now the researcher, thankful to all these people who contributed for research webinars. And we have coming up the Sri Lanka Research Forum. We're working on the program on 2nd October, and we have Pakistan Polymer Research Forum. Various researchers from the University of Engineering and Technology Lahore, Pakistan, and a couple of industries people. These are the list of the topics available. You can see the handout. Okay. And currently working at the Calcutta University Polymer Research Forum, working together with Professor Deepankar Chattopadhyay and also Professor Abhijit, focusing on the polymer synthesis and properties and processing. A couple of presentations almost finalized, and we'll be adding more topics. It's scheduled on the 27th of November. We have technology webinar, which is focused on promoting, introducing commercial technologies and, the exploring the business opportunities. We have the platform called Rubber and Tire Tech Forum. It's a basically virtual forum to introduce the rubber and tire technologies. We have various regions: India, Middle East, Africa, Southeast Asia. And basically the focus is on the, what are the new technologies, what are the is for the commercial technology suppliers to promote their technologies. And it's a sponsorship base. We charge $250. Anybody interested, they can reach out to our firm. All the delegates who are industry people can join. It's free to join. And we have the schedule and this upcoming schedule, but we plan to organize the frequency on a regular basis, 2 times a year, 3 times a year for the different regions. Okay. We also offer the customized tailor-made programs as well. Who want to promote the technology to the target regions. We have a sponsorship which can start from the $850 plus. Okay. So you can reach out to me for information. And this is the Indian program. And just to give you some glimpse of the India Rubber and Tire Tech Forum. We have various sponsors. Thankful to all these sponsors supporting this event, and these top topics will be presented. Of course, they're all more on a commercial scale, but also techno-commercial presentations, beneficial to the industry to understand what is happening in the technological, commercial technologies. Okay. I asked the Professor Kinsuk also to talk about research trends in rubber science technology on this one. And so these are the topics are going to be presented in the India Rubber and Tech Forum. All are invited to join this, the India Rubber and Tire Tech Forum. And we have recently started eminent personality webinar, which is basically to focus on eminent persons who are well-respected, well-experienced people, and they want to know about their journey, because young people like us to learn from their experience. Everybody is 50 to 60 years working experience in the rubber industry. So we focus on in conversation with the eminent rubber industry professional. We have invited a couple of people already. We're working with others. So these are people with huge experience. We can learn a lot. And so please check our website, if you're interested to learn about the journey of these eminent people in the industry. We have publications, as Mr. Kansuk mentioned. Well, specialized books. We have printing business as well. So we have a couple of books. They're all available from our store. You can check it out. And as I mentioned, Dr. Samir Majumdar, he prepared for us as pocket books. Unfortunately, he's no more. I'm very much grateful to Dr. Samir Majumdar, who contributed all these pocket books for the benefit of the industry. This is a website, store.technobiz.org, for more information. We have a magazine, Rubber and Tire Digest magazine, which is jointly published by the Rubber World. It's in digital format. Currently, we have 6,000 plus global readers, and you can subscribe for free. So rubbertiredigest.com. And I probably may know, many of you know me through the Rubber Technologies Network. I operate a Facebook group. Currently, we have 3,600 members from 18 different countries. We promote various events, research, technology innovations, etc., etc. If you have a Facebook group, I invite you to join this Facebook group. And we have Polymer Research Network, just started. Basically, whoever wanted to work with us to promote the research work to the industry, welcome you all. And we have a rubber industry network, which is focusing on the, promoting the, it's a basic membership base, helping the companies to build their businesses, brand building, things like that. We just started about this used machinery rubber and tire industry virtual sales meet. Is basically, if your companies have any used machinery they want to sell to others, we provide a platform for industries to sell. And we just started talent search, and a lot of inquiries for me. People are looking for jobs, are looking for people. So TechnoBiz is also helping out for the companies who are looking for people, or for the people who are looking for a job. So you can reach out to us. Okay? And TechnoBiz Consulting, we have worked with a lot. We work with a lot of experts. These experts are offering a consulting service with through TechnoBiz, and you can design, development, troubleshooting various aspects of it. Whether it's rubber, whether it's latex, whether it's a tire, we can help you out. And also, we can help you to brand building and also marketing service if you want to expand your business, and also there's product launch and partner search. So these are specialized services, and so you can check out information. And we have this TechnoBiz channel recently started. Basically, all the activities which we are promoting through the TechnoBiz channel. So if you're interested, you can subscribe it and follow us. Okay, that's if any information you need from us, this is me. I've started 16 years ago. It's been a great journey. The journey is. I'm very much grateful to all the people support me over the years. I'm worked with the different parts of the world, experts, young and old, you name it. All I work with many types of people. All are very nice to us, and the progress of 16 years is credit to them only. I'm just only the person just heading or moving forward with their blessings and with their guidance. Okay, so you can reach out to me with this contact information. And finally, the TechnoBiz is a company, is independent private organization. There are some people have some skepticism about it. We're a private company, so whatever we do, we want to make sure the industry benefits out of it. And we work with the different partnerships. Of course, we have our own limitations, so we have worked with whatever available resources and partnership friendships. We are doing our jobs. The door is always open for anybody interested to to be part of the TechnoBiz journey. Okay. Just to give you, as you know, COVID gave us an important lesson to all of us to protect our nature, and so I'm encouraging you. You don't need to talk about big things. You don't need to complain about politicians. You don't complain people beyond your control. What we can do is plant more trees in your surroundings of your home and your workplace. Two things: work, home, and workplace, because this is a place we spend a lot of time. I think if you make it a green, that'd be nice. So please join me in supporting this agenda. Okay, thank you very much. I welcome you, all of you, to join the journey of TechnoBiz, and you can reach out to me technobiz.org. Thank you, Professor Kinsuk, for giving me an opportunity. Thank you. I appreciate the time.
Thank you very much, Peram, for your nice presentation. And as mentioned by Peram, that if you have to have any information, please visit their website or just drop an email to Peram. Okay. Thank you, Peram. So moving on, our next speaker will be Mr. Vasudeva Rao. Okay, and I'll very briefly introduce him. Mr. Vasudeva Rao has, he did his diploma in rubber technology in 1978, and he got his LPRI from London in 1982. He has 38 years of rich experience in JK tire industries, and he superannuated as head of bias technology in March 2016. and he has served as a member of Indian Technical Advisory Committee for about 11 years and awarded with fellow member of IRI by Indian Rubber Institute in 2015. And still he is very active. Presently he is serving as the Secretary General of Indian Rubber Institute, and also he is a faculty in Rubber Technology of IRI for diploma and postgraduate diploma students. Okay, with this brief introduction, I think the floor is yours, Mr. Vasudeva Rao, for the next 15 minutes.
Thank you, Professor Naskar. Can you see my slide?
Yes, please go on, please. Yes.
I am audible to you all?
Yes.
So first of all, let me thank this entire team of conference under the chairmanship of Professor Naskar, and with the background support with the GoToWebinar of Param Prasad Rao, who is our beloved friend from TechnoBiz. And right from morning, I am attending this program, that is from 12:30 onwards. Everything is going very smoothly and fantastic program. My compliments to entire team of IIT Kharagpur and as well as TechnoBiz. Now, this is an opportunity given to me about to explain about our Indian Rubber Institute as well as Dr. D. Banerjee Center of Excellence, which is already come up at JSS Science and Technology Institution campus. About IRI, most of the people know what is IRI. It is an education institute of rubber science and technology, and the education of rubber science and technology, which plays a very important role in developing the technical manpower for rubber, tire, and allied industries. Rubber technology education all over the world is very limited, and before independence, most of the people were going to National College of Rubber Technology, London, and even to have their diploma or graduation courses in rubber science and technology. After the independence, the education in India was initiated by Department of Applied Chemistry, IIT Kharagpur, for the masters and PhD level, which is already explained by Professor Shantanu Chattopadhyaya today morning in his introduction meeting. And subsequently, it was spread to the other universities. Now you can see the pioneers in spearheading the entire rubber university is none other than Rubber Technology Center, IIT Kharagpur, followed by rest of the 24 universities and institutes and offering polymer science and rubber technology course in India. PRI, that means Plastic and Rubber Institute UK, initiated the conducting licentiate and diploma examination in India through PRI Indian Section Rubber till 1987 with the support of consulate offices Bombay, Calcutta, Delhi, and Madras. Lot of our seniors, you can see, they all appeared this course and this consulate, and it is an examination. Then afterwards, they award the certificate those who are successful candidate. During 1987, the PRI UK underwent a further restructuring, liquidating and merging with Institute of Materials. Now it is called as IOM3 at UK. This prompted Indian section of PRI with the idea of forming a very strong institute to continue all functions of PRI in India in the name of Indian Rubber Institute, which started in the year 1987 at Kolkata. It was formally inaugurated by Mr. N.H. Godfrey, then chairman of Council PRI UK, on 17 September 1988 at New Delhi. The present IRI has 8 branches located at Kolkata, Chennai, Delhi, Gujarat, Karnataka, Kerala, Mumbai, Rajasthan, covering almost all the regions. And we have also one Center of Excellence, which is named as Dr. D. Banerjee Center of Excellence at Mysore, which I will be explaining later in my slides. IRI is a professional body working in the field of rubber and allied industries. IRI has more than 3,500 professional members in 8 branches all over India. IRI is a technical affiliate organization of American Chemical Society Rubber Division, and also it is a member of International Rubber Conference Organization, which is called as IRCO at UK. IRI is working very closely with Rubber Board of India, All India Rubber Industries Association, AIRIA, Automotive Tire Manufacturers, ATMA, Rubber Chemical Petrochemical Skill Development Council. Earlier it was called as RSDC, now it is called as RCPSDC under National Skill Development Corporation, Government of India, New Delhi, for training and development of people and also organizing various training courses, workshops, seminars, national and international conferences. So you can see International Rubber Conference Organization, the schedule and calendar of event is already released by UK IRCO Management Committee. You can see IRC 2021, which is 27th to 30th June 2022. Then IRC 2022 International Rubber Conference is coming up, which is sponsored, which has to be organized by IRI at Bangalore on 24th, 25th, 26th, 3 days in the month of November 2022. So we can see other events also coming, 2023, 2024, 2023 in China, 2024 in Turkey, 25. It's all, now you can see another conference called RubberCon. RubberCon parallelly, there will be two events, that is International Rubber Conference IRCO and another event is called RubberCon. RubberCon 2021 at Korea, RubberCon 2022 at Kuala Lumpur, Malaysia, RubberCon 2023 UK, and RubberCon 2024 is offered to India. Once again, IRA will be conducting, and RubberCon 2025 Sweden. So this is the calendar of event already agreed upon mutually between IRCO and the member countries. So about ACS membership, American Chemical Society has got a very big we can say a very big organization conducting technical symposia, rubber chemistry and technology journals, education workshops, webinars, online courses, technical publication, and a lot of students are enrolling themselves to get their knowledge in this ACS rubber division for the rubber technology. What are the benefits if you are becoming a member of IRA? If you are becoming a member of IRA, you have to pay only $25 US. Otherwise, if you go through their website, you have to pay $100 US to become ACS membership. So this is an opportunity for Indian professionals, those who are working in IRI and rubber industry as a member. They can definitely get enrolled themselves every year by paying. Roughly, it comes around 2,100 rupees per annum is a membership fee. So we have around 400 IRA members enrolled as a ACS member. And ACS member last 3 years back, 2017, the core committee visited, and they visited a lot of branches in India, and they have understood the activity of IRA. So this is a geographical picture of IRA located in various parts of India, Delhi and Kerala at Kochi. Karnataka branch is in Mysore, as well as Dr. D. Banerjee Center of Excellence. It is a 9th unit of IRA, which is also situated in Mysore, and IRA Chennai, IRA Kolkata, IRA Gujarat at Baroda, IRA Mumbai at, and IRA Rajasthan at Kamkroli, Udaipur. So total 3,500 members. So this is a vision of IRA to become a premier institute of global reputed rubber technology education, training and skill development in the Asia Pacific region. To support the growth of personnel associated with the tire, rubber and allied industries, providing them learning opportunities of knowledge and skill upgradation in association with the Institute of National Importance. To enhance the networking among the global rubber fraternity by organizing international and national conferences, seminars, workshops in association with national and international professional bodies. So if you see this, we can easily make out that to promote and disseminate the knowledge of all aspects of rubber science and technology by holding meetings. So we are very closely working with the National Research Rubber Institute, rubber organization, providing training and people working in the medium and small scale industries to enhance their knowledge and skill in the field of rubber processing. Very important thing is, since 1986 or 1987, we are tied up with the IIT Kharagpur Rubber Technology Center to provide diploma in rubber technology and postgraduate diploma in rubber technology. And in collaboration with IIT Kharagpur, they'll be our major controller of examination And last year, we have signed an agreement for further 5 more years. They'll be giving us all this assistance and help. Under their guidance, these examinations will be conducted. This is a well-recognized course all over the tire industry and rubber industry in India. This everybody in the resume, if they put DIRA pass or PGDRA pass, they are getting the separate weightage. So now you can see, I would like to remember in this occasion overall our past chairmen. Late Dr. D. Banerjee, late Dr. D. Bose, late Mr. Manu M. Patel. Manu Bhai Patel recently, just a week back, we have lost him. He's a great loss to the Indian fraternity. Dr. S.N. Chakravarti and late M. Jakaria Judge, he was our past area director of American Chemical Society. He was coordinating with the ACS. And Mr. P.K. Muhammad, who is the main brain of this IRA. This is a present office bearers. IRA will elect the office bearers every 3 years. This is for 2020 to 2023. The present office bearers are Dr. R. Mukhopadhyay, who is a director R&D of JK Tire and Industries Limited, who is also chief executive of Assetri, Harishankar Singhania Elastomer and Tire Research Institute, which is situated at Mysore as a global global testing center of JK, and he is our chairman of IRA Governing Council. Another icon is Sri V.K. Mishraji, he is our vice chairman IRA Governing Council, and myself is a secretary general, and P.K. Muhammad, who is another office bearer, who is the core committee, was our immediate past chairman. Now we have recently elected Mr. Mehul Patel as a American Chemical Society area director for India. We can say a mobile encyclopedia of our IRA in rubber technology is Dr. Samar Bandyopadhyay. Dr. Samar Bandyopadhyay is chairman of education committee. He has got a strong team of 36 to 40 faculties in our IRA who are all dedicatedly working for IRA. Memorandum of understanding we have signed with so many associations like ACS, Rubber Board, IIT Kharagpur, Mohanlal Sukhodiya University of Udaipur, Vidya Bhavan Udaipur, University of Calcutta, JSS Science and Technology University Mysore, Rubber Chemical and Petrochemical Skill Development, which is RCP SDC New Delhi. So our branch at Chennai is having an interaction with MIT, Madras, Delhi branch Textile Technology Department, IIT Delhi, Karnataka branch JSS Science and Technology University Mysore, Kerala branch Cochin University, Cochin, Calcutta branch University of Calcutta and Rubber Technology Center IIT Kharagpur, Mumbai branch Bandra Polytechnic, Mumbai, Rajasthan branch Mohanlal Sukhodiya University and Vidya Bhavan Polytechnic, Udaipur, and Gujarat branch is having collaboration with Maharaja Sayajirao University of Baroda. So role of skill development of IRA as per skill mission of India, the IRA chairman is a member of governing council, including the main committee, SPARC committee member who has developed NOS for rubber sector. IRA is actively involved in framing the NOS of rubber sector. IRA is affiliated training partner of rubber, chemical and petrochemical skill development. Recently, we have signed an agreement with RCP SDC, and we are planning to commence BO course in rubber technology at Dr. D. Banerjee Center of Excellence in collaboration with JSS Science and Technology University Mysore and also RCP SDC, NSDC, New Delhi. Recently, we have signed a tripartite agreement with these 3 parties. This is about the conferences we have conducted so far. You can see from 1993 onward, the conferences Delhi, 98 Chennai, and 2000 at once again Delhi, 2002 at Delhi, and 2004 at Mysore, 2006 at Cochin, 2007 at Udaipur, and 2010 at Mumbai, and RubberCon at Chennai, and 2015, and Asia RubTech in the year 2018, and now 2022 we are planning at Bangalore, IRCO at Bangalore, International Rubber Conference. This is a role of IRA in producing qualified rubber technologies in India. Since 1951 to 1986, LIRA London or LPRA London was there and GATPR London was there. around 1,000 qualified and professional rubber technologists were come into the platform. Since 1987 to 2020, in association with the Rubber Technology Center, IIT Kharagpur, as control of examination, we are holding LPRI, PGDRI, and DIRI qualification. So far, around 1,800 qualified and professional rubber technologists produced by these two institutes, IIT Kharagpur and IRI jointly. This credit goes to majorly to IIT Kharagpur, and we will be always grateful to IIT Kharagpur Rubber Technology Center.
So
Rao, now we are
sorry, Mr. Rao, can you make it short? This one within couple 2 minutes.
Just quickly, I'll finish it up within 2 minutes.
Yeah, please.
Dr. D. Banerjee Center of Excellence, and this is a unit number 9 of Indian Rubber Institute, which is situated at JSS Science and Technology University, Mysore. 10th of March 2026, there was a groundbreaking ceremony, and afterwards, this is the building came up with the approximately we have spent around 9.75 crores for this 35,650 square feet building. Almost half an acre land has been donated to us by JSS Science and Technology University. You can see the logo of JSS Science and Technology, Mahavidyapita logo, and IRI logo in this building. So, what is the activities of Dr. D. Banerjee Center of Excellence to fulfill the objective of IRI and upgrade the skill of workers and get the qualified people, and providing training, increase productivity, efficiency for the MSME sector, and testing, benchmarking, reverse engineering, product failure analysis, compound development. All these things will take place in this center. Technology development of MSME sector, creating new avenues for MSMEs in rubber industry. To create center of excellence with well integrated forward and backward linkages. And we also would like to have a latest information about technology and process marketing and customers, and to coordinate with all its very premier organization in India to continue to offer diploma and postgraduate diploma rubber technology in association with IIT Kharagpur, and we are going to start VO course, which I have already explained. After installation and commissioning of testing equipments, machineries, BAS certification, enabled certification will be there. We have placed the order for tire testing machines and rolling nation R&R testing machines. It will be expected by around January 2022, and we are also participating, which I have already explained, at Hotel Sheraton Bangalore, 24, 25, 26. There will be a very big event of 1,000 delegates expected for this conference with the 200 exhibition stalls, 23 country participation we are expecting. This is a glimpses of the photograph of the building. These are all the classrooms are ready, boardroom is ready, and this is one auditorium is coming up. This is the present construction of the auditorium, 225 seat, and after finishing it will look like that. This is the architect view. So in a nutshell, IRI is sharing knowledge, and we believe in sharing is learning. Thank you for your kind listening. Thank you, Professor. Over to Professor Naskar, and thank you very much for Param also.
Thank you very much, Mr. Rao, for your nice, giving nice overview on Indian Rubber Institute. Thank you very much.
Thank you.
Moving on, we will go to the next session, which will be chaired by Professor Robert Mukherjee. I hope he's here. Yeah. He is Professor of Chemical Engineering Department, and his field of research are polymer thin film instability, soft lithography, colloidal crystals, liquid crystal thin films. And
so we are already running late by time, so you can skip
okay.
that. My only introduction is I am a great friend of the Rubber Technology Center, IIT Kharagpur. So thanks Kinshuk and thanks other colleagues in the center. So it's a wonderful conference as usual. Kinshuk has put together rubber products for a green future. And it's my great pleasure to introduce the next speaker, Dr. Kanika Sahakaro from Thailand. Dr. Sahakaro, Thai names sound to be so familiar with Indian names. She is an associate. She's a associate professor and dean faculty of science and technology at the Prince Songkhla University, Patani campus in Thailand. Must be one of the most beautiful places in the world, as usual. And she is an associate editor of the Rubber Chemistry and Technology Division, Rubber Division of the ACS, board member of the Materials Research Society of Thailand, board member of the Polymer Society of Thailand, has a high H index of close to 20, close to 80 publications. I mean, all the usual stuff. She did her bachelor's in rubber technology from the same university where she is a faculty now in 1994, followed by a master's from University of Manchester in 1998 and a PhD from the University of Leeds in 2002. And ever since that, she is working in different capacities, and now she's a senior faculty member. So over to you, Professor Sakharov, for your presentation.
Thank you very much, Mr. Chairman, for your kind introduction. And first of all, I would like to thank the organizer, especially to Professor Nazca for his kind invitation. So I'm honored to be part of this webinar. Let me show my screen. Can everyone see my screen?
Yes, fine, visible and audible. You can go ahead.
Yes, perfect.
Okay. Because yeah, like previous speaker, that we can only see our screen and we cannot see the audience. Okay. Today I would like to present on the safe compounding ingredients for silica-reinforced natural rubber composite. And before moving into the research work, that I will show some example of our work on those compounding ingredients with focus on the utilization in natural rubber compound reinforced by silica. Let me introduce you about Prince of Songkhla University. As the chairman mentioned, that we are situated in Thailand, and Prince of Songkhla University have 5 campuses distributed in the southern part of Thailand, and I'm from Pattani campus, which is quite close to Malaysia border. And we have our main campus in Hat Yai. The university was established in 1967, and in terms of figure now, we have about 35,000 students and 2,500 of academic staff. And you can see this is from Pattani campus, a very nice and beautiful campus and the oldest one. And we have 8 faculty here where I work at the Faculty of Science and Technology. Faculty of Science and Technology established in 1985. As you can see from the Google Earth here, we are nicely located close to Pattani Bay. So we are here close to Pacific Ocean, and then we can see a beautiful sunset from the rooftop of our tall building here. I'm now taking a role of Dean of the faculty, and we have just about less than 800 students. And rubber is one of our research flagships here, as you can see. Our faculty have a multidisciplinary research covering from rubber, agriculture, aquaculture, food science, natural resource, and energy. And of course, rubber technology is one of our strong points here. Okay, let's move back to the topic of my talk today. I will start giving introduction about research and development for tires, and then introduce tire labeling. Some of you may already know, but there's some new development here. And then move to low rolling resistant tire by silica silane technology. And then also to comply with my title of the talk today, I will tell you about the safe rubber compounding ingredients with focus on process oil and alternative for diphenylguanidine or DPG. We are now moving toward more green and sustainable tire industry. So if we look at R&D for tire at the moment, we need more energy efficient and less CO2 emission tire. That means we are searching for lower rolling resistant tire. And now we discuss a lot about tire wear particles. So that means if we want to reduce the tire wear particle, we need a tire with better abrasion resistance, or it should have better durability. In terms of the safety, we need to look carefully on those ingredients that we added into the compound. Can we use the safer one? And shall we rely more on sustainable supply instead of petroleum-based raw material? So there are so many aspects to drive forward toward this green and sustainability in this industry. And importantly, nowadays we are talking about EV or electrical vehicles. There are some changes, requirement for the tires as well. By having battery to provide power instead of the combustion engine, that means the weight of the car will be also heavier and introduce higher torque. So if we are looking for tire for this EV passenger car or different type of vehicle, we are looking for lower, even lower loading resistant tire, because we need to drive for more distance before stopping to charge your battery. Because of the higher weight of vehicle, that means we will have longer braking distance. So we need to look carefully on the wet grip, and we should have better wet grip. And also, if possible, we should have also higher wear resistance. So if we look at this magic triangle, we need to extend to all three angles. I mean, we need lower rolling resistance, better weight grip, and higher wear resistance. And moreover, because of no combustion engine anymore, that means we can hear external noise more compared with the conventional car. So we are also need to talk about the low noise tire. So there will be quite a challenging time ahead for tire industry to meet all kinds of these requirements. And for those who are familiar with tire labeling already, you may be familiar with the EU label on the left side of this slide, which was issued in 2009 and applicable since 2012. But lately this year, EU introduced a new labeling system, changing classes given to rolling resistance and weight grip. So from 7 classes was reduced to 5 classes, and there will be more detail on the noise level. Also, there will be some additional symbol for snow grip and white and ice grip. Also, EU now discuss about the possibility to include wear resistance into this tire labeling, because as I mentioned earlier about the tire wear particles, and we want to reduce that because it's also contaminate the environment. However, we cannot do it now because the test method for the durability or wear resistance for tire are still under discussion and under development. Once we have this test method ready, I'm sure that the labeling system will be another kind of property introduced into that. And they plan also to extend to retread tire. And for this wear resistant, actually EU announced that they target for 2025. So there will be quite R&D moving into this area. And for labeling system, for the rest of the world, they have been introduced, like in Japan, in South Korea, in Brazil, in China, and recently also in Thailand, we have also introduced this type labeling by using a label from EU as a model. So mainly it covers rolling resistant, wet grip, and noise. when we talk about the low rolling resistant tires, so we need to move from carbon black filler to silica-silane technology. And on silica surface, we have numerous silanone groups that bring some difficulties from mixing. And this silanone group, there are 3 different forms of them. We have isolated, vicinal, and germinal silanone group, which are having different reactivity. So when we talk about reacting with silanone group with silane coupling agent, those different form of silanone group will also react at different octane. For coupling reaction between the silica and rubber, as you can see here, we have silane in the middle. By having silanization reaction that is driven during the mixing process, we will have the silane molecule attached or covalent bond to silica surface, leaving this polysulfide functional group to attach to polymer molecules during vulcanization. So the principle of low rolling resistant tire that we obtain from this silica silane, it can be simply described by the effect of double network, because once we do vulcanization, we have cross-link. So we have chemical cross-linking and we do coupling reaction. So you have also covalent bond between filler and rubber. And this double network lead to a lower hysteresis. That means we have less energy loss during dynamic deformation. And this silanization reaction efficiency is a key factor to success. So we are talking about 2 different steps that we need to look carefully when we use silica silane in rubber compounds. The silanization during mixing and coupling during vulcanization. When we study natural rubber, as you know, that Thailand is the biggest producer of natural rubber for many years, and it is sustainable resources because we can replant natural rubber in, and also EU declare natural rubber as a critical material for the 2nd time in a row. So it is important and has a unique properties with this quite amazing. I mean, we have more than 99, or we'll say 98%, almost 100% of cis structure. So it is stereoregularity is very high, and we have strain-induced crystallization that give a property of natural rubber differ from other type of synthetic rubber. And natural rubber go to tire industry mainly, so it take about 65% in Thai, and the rest we go to different type of application. So when we use rubber, we need to also formulate the compound well in order to achieve the required properties. If you look at the rubber compounding ingredients in compound preparation, in addition to rubber or elastomer, you have many types of additives. And today I will talk about process oil and accelerator in case of diphenylguanidine. And actually, we can also look for some other kind of ingredients as well later on. So for rubber process oil, this highly aromatic oil has been banned for many years, especially in tire industry, because of the presence of polycyclic aromatic hydrocarbon, or PAH. There are so many types of polycyclic aromatic in DAE, or highly aromatic oil. but so far 8 types of PAH have been classified as carcinogen, so that lead to a ban on this kind of material. But there are different kind of oil that you can use in replacement of DAE. The widely used replacement oil for DAE is TDAE. So we have treated distillate aromatic extract. These simply do the distillation to remove this PAH out of DAE. But you can also use naphthenic oil or mild extracted solvent. So there are alternative from petroleum-based oil for this highly aromatic one. And by changing type of oil from DAE to TDAE or MES, please aware that because of different composition, if we can see from the different ratio of aromatic carbon, naphthenic carbon, and paraffinic carbon, they are different. And this different composition and of course structure, this oil have different glass transition temperature. So when we add this kind of oil into rubber compounds, we also expect that our dynamic mechanical properties of those compounds will be also affected. And if we simply look at proton NMR spectra of this 3 type of oil, you can see that DAE contains amount of aromatic proton and show a trace of a proton in polycyclic aromatics, and it's already removed when we have the TDAE and MES. What else can we use in addition to petroleum-based process oil? And actually, this is quite a hot topic, I would say, because now we are talking plant-based rubber process oil. And based on our investigation previously, we look at epoxidized palm oil and also amine modified epoxidized palm oil. There are some work on epoxidized soybean oil. So this kind of oil, if we look at the structure, it composed of tricrystalline with some unsaturation there. So this will allow us for chemical modification, like what we do here. We change this double bond into epoxy ring, and this epoxy ring can be opened easily. That allow us to do some further chemical modification, like here we attach amine on epoxidized oil. I show you some of the work that report on this plant-based rubber process oil. If we follow the work from Goodyear, we may see that there is a big project launched by Goodyear recently on soybean sustainability framework, and by replacing some part of their rubber process oil by this soybean oil, aiming, I don't remember exactly by which year, but they aim to use soybean instead of petroleum oil in the future. And there are 2 more examples here. Use of epoxidized soybean oil in silica fuel solution SSBR, and the study on soybean oil for thread rubber. And this work published in 2019 and 2020 last year. So this proof that they are demanding now, because people are working toward this kind of green compounds. Look at the example of the work that we did on palm oil. So we took palm oil that's available in the market and do simple chemistry, the epoxidation by having hydrogen peroxide and formic acid. Under mild condition, you can convert this unsaturation site to epoxy ring. And we can prove by having NMR spectroscopy. By varying reaction time, we obtain different more percent of epoxy group, and this can characterize by also the titration technique. And we have 3 different levels of epoxy here. And we took one of the EPO and do some further modification by introducing phenylparaphenylene diamine or PPD here. So reaction was done at 100 degrees using zinc chloride as catalyst, and we obtained 2 different levels of PPD grafted on these oil molecules by having characterization by NMR. So it proves that we have done the reaction successfully. Then we use that modified oil into our rubber compound. Here we compare the modified palm oil with TDAE, and also we have the one without oil as the control. Mixing procedure follow this 2-step mixing. I show you some example of properties that we obtain by utilizing this modified oil. If you look at the kill characteristic, comparing with TDAE, now we want to see whether this plant-based oil can replace TDAE. So based on this kill curve, you can see that by using epoxidized palm oil, we can raise the cross-link density that is interpreted by the maximum kill torque. So we increase the maximum kill torque, especially for this case for EPO with about 3% more of epoxy, and we have higher kill reaction rate by having this modified oil. So what happened there? I should mention that even we have silane coupling agent with silica, and we do silanization reaction during mixing, there will be only about 25% of silane group that can react with silane coupling agent, because once some group of silanone has reacted, it will be a kind of steric effect or steric hindrance that prevent the incoming of new silane coupling agent molecules. So if 25% reacted, that means we still have plenty of silanone group on silica surface, and this silanone group can still interfere with vulcanization. So in the presence of oil, the absorption of these molecules of oil can introduce hydrophobicity on the silica surface. So we can see that we have better kill properties in the presence of this kind of oil. In terms of dynamic property, if we look at tan delta at 60 degrees, which has been used as indicator for tire rolling resistance, comparing with the one without oil and TDAE, by using this modified oil or even the palm oil, the original one, we see a reduction in tan delta, which means if we use this compound for tire tread, we expect to have a lower rolling resistance. Also, the tensile properties of those compounds, I can show you here that by having EPO with 2 and 3% more of epoxy, we end up with similar tensile strength of the property. So mechanical and dynamic property, we satisfy with the use of this modified oil. And if we modify further by having amine, then we take EPO also as a control, and we have 2 different of amine modified epoxidized palm oil. Also kill characteristic is improved. We can see a higher maximum torque here, and this maximum torque can be related to cross-link density in the vulcanized set. So by having better cure, we see lower tan delta at 60 degrees by using this amine modified EPO. So for tire application in terms of dynamic mechanical property, by having modified palm oil, we can see a better elastic response without a loss on mechanical properties. So to summarize, for EPO and amine modified EPO oil, by having this oil, the hydrophobicity is promoted, and then resulting in enhancement in processability, mechanical and dynamic properties. And we are confident that this kind of modified palm oil can be utilized in silica-reinforced compound in replacement of petroleum base. And actually now I think many big oil producing company, they are also producing this kind of oil. Okay, let's move to another topic on DPT and its alternative. Why we interested in DPT? Because we are working on silica-reinforced rubber. And for those who are familiar with silica silane technology, DPT is an essential ingredient for these compounds. If we look at the roles of DPT here, DPT accelerates the vulcanization reaction because DPT itself is a secondary accelerator. It promotes the silanization reaction. And as I said, only about 25% of silanone group reacted. So we have plenty of free silanone group. So this DPT can help to deactivate those free silanone group as well. But the problem is, once DPT is decomposed at high temperature, we have aniline, and aniline is a toxic substance. So can we have other additives in replacement for this? If we look at the rate of liberated aniline, we can see an increase of rate already at the temperature about 130 degrees Celsius, and increase remarkably at higher temperature. And this range of temperature is the discharge temperature for rubber compound mixing. So if we use DPT, you will have aniline. Let me show you about the influence of DPT on properties. As I mentioned, this is an important ingredient for silica compounds. There was a report many years ago showing the effect of DPT content on properties. So we can see an enhancement in care property in the presence of DPT, and improvement in pain effect. So we can see a lower pain effect here and higher chemically bound rubber when we increase the DPT content, and we can see a clear improvement in tensile property. So based on this work, and also the work on synthetic rubber, based on solution SBR and BR, we need about 2% by weight related to silica of DPT in this silica compound. So we took different kind of amines to investigate, having also aliphatic amine and cyclic amine having different molecular weight, and having DPT as the reference. Once we have the salinization reaction, we have byproduct of ethanol. So first of all, we study kinetic of those different amine on salinization reaction. And model compound study was based on a mixture of decane with silica and silane, and we have amine heated at 135, and then we follow this method or procedure. And we want to measure the concentration of ethanol. So we did that by using GC. So 1 molecule of TSPT releases 2 mole of ethanol. By using this equation, this primary salinization and secondary salinization, we can obtain the rate constant of those reactions. So if we see the concentration of ethanol per concentration of TSPT, by simply looking at this plot, we see already the effect of amine in the model compounds. By having amine, we have different concentration of ethanol generated from the reaction. And applying those relationship, we have a rate constant here. So we have much higher primary salinization reaction rate compared with the one without amine. And about among those different type of amine, different structure of amine effect on different rate. When we look at the compound, because we can see nice chemistry on model study, but we want to see whether it works in the real or practical compound. So we use those different amine type based on molar equivalent using this formulation following 2 mixing step as I show here. I show you here a plot of storage modulus versus strength. This is a kind of pain effect study. So we see that different type of amine give similar behavior. We see pretty close of those storage modulus that change according to strength. Only DIC with 2 cyclic structure, this is bicyclic structure, give higher pain effect. Once it vulcanized, we have a clear lower tan delta compared with the compound without amine. And if we look at the mechanical properties in terms of tensile strength and elongation at break, if we see DPT here and other type of amine, you can reach a similar level of tensile strength by utilizing this octadecilamine, cyclohexylamine, and also the EC. So a kind of different amine can be used in replacement of DPT, that we can still obtain similar mechanical and also dynamic properties. We investigated different compound property before and after vulcanization, but I select some results to show you here, just to give an idea that if we don't want DPT in compound, you have something else to be chosen. What happened when we have this amine? When we have silica particles, we have bound rubber, a layer, and on silica surface we have silicon group. And as I mentioned, that when we have this amine, it can interact with free silicon group, so it changed in terms of hydrophobicity, and also this long aliphatic tail of amine. This also can entangle with rubber molecules, and that help to achieve properties close to what we actually wanted. By comparing DPT and octadecilamine, here based on different property, we select octadecilamine as alternative, and we vary the quantity of octadecilamine in comparison with DPT in order to see whether we can see the optimized content. And based on various property and tan delta at 60 degrees is chosen as example here. We can see a drop in tan delta at 60 degrees, which we use to indicate for rolling resistance. We can have even lower tan delta compare with DPG. So if I summarize for this study, based on model compound study, linear aliphatic amine work better than cyclic aliphatic, so it gives higher rate constant of primary silanization reaction. And the use of octadecylamine amine provide the property of rubber close to the reference compound with DPG, and by having the optimum loading of octadecylamine, we can have even better mechanical properties and tan delta at 60 degrees compared to DPG. So what's next? Now we can overcome those process oil and alternative for DPG. We can use either safe petroleum-based process oil or the plant-based process oil. So we have choices. You can apply octadecylamine in replacement of diphenylguanidine. But there are some other ingredients that I show here. So if we want to have more safer and moving toward sustainability, I think we have something more to do in terms of tire industry. Like we can probably look at carbon black or even silane, which produce less ethanol, because ethanol also is a volatile product that we should also reduce, or we can look at different type of ingredients. Okay, I would like to thank this organization who support this work, and the work that I show here based on our collaboration with University of Twente in the Netherlands, with sponsorship from the Dutch Natural Rubber Foundation, also from Apollo Tire Global R&D, the Netherlands. And thank you for your kind attention, and I will be very happy to answer any question from the audience.
Thank you, Dr. Sahakaro, for sticking to time, though you started a little late, but I think you have finished in time. I think for the benefit of time, what I will do is I will invite the next speaker, Professor Thomas, and then collectively, if there are any questions, we can take up in the chat box. Kinshuk, is that okay? Yeah. So I thank again Dr. Sahakaro on behalf of the organizers. And we move on for your excellent presentation, actually. And since I worked on hydrophobic materials, so I was thoroughly enjoying the chemistry. Thanks again. It's now my
pleasure.
great pleasure.
My pleasure.
Pleasure is all ours. It's now my great pleasure to invite the next speaker, who is Professor Sabu Thomas. And first and foremost thing, he is our distinguished alumnus. So he obtained his PhD. He is, of course, an internationally famous polymer chemist with more than 61,000 citations and an H index which exceeds 110. But more than that, Professor Thomas obtained his PhD from the Rubber Technology Center of IIT Kharagpur a long time back, and he is one of the greatest success stories of the institute. He also recently is member of innumerable number of committees and received innumerable number of awards. If I start reading them, then I need to give a plenary session on that. So Professor Thomas, kindly excuse me for that. He is the rubber of the country. And it's my great pleasure to invite Professor Sabu Thomas to kindly deliver his lecture. Professor Sabu is presently the Vice Chancellor of the Mahatma Gandhi University at Kottayam in God's own country, Kerala. Just give us a moment. Inshu, can you locate Professor Thomas?
Piram, could you see that whether Professor Thomas has joined?
Yes, he is on. He's on. Actually, he's online, but he has to open his webcam and is a speaker. Okay. Yeah.
Okay, fine. We wait.
Professor Sabu, are you listening to us? Are there any technical issues?
Just wait for a couple of minutes.
Sorry, he has left from the panel.
I suggest to wait for a couple of minutes. I'll also try to call him.
Well, Kinshuk, I just had a word with Professor Sabu and he is having some difficulty in logging in.
Thank you. Thank you. Can you hear me?
Yeah. Can you turn on your camera, please, Professor Sabu? You have to share your camera here. Yes, now I can hear you. Good to see you.
Very good. Yeah. Excellent. Thank you. Thank you for the kind words of introduction. Thank you. Hello, Kinshuk.
Hi. Please.
So thank you. I'm really delighted to be part of you, and congratulations to Kinshuk and Vipastra for nice organization. You know, I have 40 minutes, right? Maybe 35 plus 5, right?
Yeah. Right. So can you share your screen now?
Yeah, I'm going to share my screen.
Yeah, sure.
Where is the option for sharing the screen? I was trying to look at the share screen. I'm sharing. I got it. Yeah. Yes.
Yeah. Yeah. We can see. We can see now. Professor Thomas. Just please go to your PPT. Yeah.
Yeah. First.
Yeah, now everything looks in order.
Yes, we can see.
Perfect. So, Professor Sabu, over to you.
Yeah. Thank you very much. Thank you very much. The title of my presentation is Advances in Rubber Nanocomposites. Extremely delighted to be with you, and you can see my campus. It's quite a green campus, and as an alumnus of Rubber Technology Center, I'm really excited to be part of you. Let me show you my first slide. You know, my group is pretty active on a variety of nanomaterials, nanotubes, graphitic platelets, nanotalc, metal oxides, different types of clays, biological nanomaterials, bio nanocellulose, nanochitin, a variety of nanomaterials we work. We all know that we can classify these nanomaterials into one-dimensional, two-dimensional, or three-dimensional materials. You know, by putting nanoparticles into rubber, you get lots of nice property profile.
very high degree of reinforcements without the loss of ductility. That's a very important point. Heat stability, flame resistance, you get attractive properties by putting nanoparticles into elastomers. But I wanted to tell you, dear friends, when you put this nano into elastomers or into polymers, the viscosity will go up. You have resistance to flow. And I have a beautiful slide how it affects the viscosity in terms of aspect ratio. If you have spherical particles, the viscosity buildup is low. If you have highly long fibers like graphene or carbon nanotube or nanocellulose with high aspect ratio, the viscosity buildup is very high. If you look at mechanical reinforcement, you will see the high aspect ratio fillers are superior to spherical fillers. In terms of barrier, you will find that the high aspect ratio filler is superior to spherical fillers. But the most important challenge, dear friends, the issue of dispersion. Carbon nanotube is very difficult to be dispersed. And graphene is also not that easy to disperse in elastomeric matrix. So please consider all this aspect when you put nano into elastomers or others. Let me first take the story of clay. We have been very active in clay. I had several PhD topics on clay, putting clay into elastomers, putting clay into polymer blends, putting clay into thermoplastics. Clay is a fantastic material. And you can see, if you look
I cannot hear the voice. Is it a problem with all?
Yes, we cannot hear.
Yeah. Professor Sabu, we cannot hear you.
Some connectivity issues.
Yeah.
Guys, so please stand by. I think there is a connection problem, so we're fixing it. I think Professor Mukherjee, I think you're reaching out to the Professor Sabudas.
Yeah. Okay, sure. So
Yeah.
Can you hear me?
No,
yeah.
okay.
Yes.
Now,
Yes, we can hear.
Can you all hear me?
Yes, we can.
Yes. And the
Yes.
mineral surface is hydrophilic. So we have different strategies. We make use of in situ reactive blending. We make use of different types of compatibilizers, surface active agents. So we have several strategies to make a strong interface between rubber and mineral surface. If you look at compatibilizing action, I would say the compatibilizing action is by the addition of a surfactant, which is very similar to the action of soap in oil water. You can have amino acids, alkylamines, polyetheramines, imidazolines, silanes to connect between hydrophobic rubber and hydrophilic clay surface. You can see a typical cartoon. If you're making use of alkylamines will interact with the clay And you can see sodium or potassium ions, they displace these ions and go and sit there comfortably. And then you have increased gallery spacing. This is, we always do, my PhD students always do with clay. Select a very good surfactant. You can see a very nice table. Look at the various surfactants being used.
Professor Thomas, sorry, Professor Thomas, we cannot see the slide transition. It is only still.
Hello, can you see me? Can you?
We cannot see your slides.
Pardon?
It is only the title slide, but we cannot see the other slides.
Oh,
the slides are not changing.
Only the slides. Title slide even now.
We are still in the title slide.
Even now the title slide.
Yeah.
Yes.
Oh, I see. Is it moving now?
No.
Is it
I
moving now?
suggest you stop. No, it's not. No. I suggest you kindly stop sharing.
Is it moving now?
No. I suggest you kindly stop sharing once.
Yeah, share. Share. Okay, share the link. Okay, we will. Oh, it's more. There could be some problem. Yes.
Professor Kinsuk, I think what we do is that we take back the screen and we request him to share the screen again. Huh?
Yes, please do so. Yeah, now we can see.
Okay, now it is. Yeah.
Now we can see. Yeah. Yeah.
Can you see my slide?
Yes.
Yes.
Is it moving? Is it moving now?
Yes.
Yes.
Okay. So I will quickly, tell you what I discussed so far very quickly. Can you see the slide? Is it moving?
Yes, it's moving.
These are the nanoparticles we use in my group, and general classification of nanoparticles. Then I spoke about the aspect ratio and the property profile. High aspect ratio fillets give rise to high viscosity buildup, and but very good properties. I was talking about clay. It has got a QT structure, 2 tetrahedral Houston octahedral. And then I spoke about the mixing protocol. This is unmixed, and this is intercalated, and this is exfoliated. Then I spoke about using different types of compatibilizing agents. So we wanted to make a very strong interface between rubber and clay surface. So amino acids, alkylamines, polyetheramines, silanes. You can see the action of alkylamines. Alkylamines displace sodium or potassium and sit inside the intergalleries and increase the gallery spacing. You can see a slide here, different types of surfactants. They're all alkylamines, but varying molecular weights. And look at this slide. This is the wax of MMT clay modified with a range of surfactants. This is neat chloride. If you use surfactants of varying molecular weight, you can see the peak is shifted to, progressively shifted to lower angles. What it implies? It implies that you have very high level of intercalation. That means the surfactants interact with the clay platelets, and the best surfactant is, chloride 28. That gives rise to maximum shift. So this is what we always do with clay. Treat the clay with a good surfactants. Let me now tell you a very important effect called pain effect in elastomers. When you put fillets, whether it is clay or carbon black or silica, they always form some sort of structure formation. You can see this has been first noticed by Payne, and this is theoretically analyzed by different people. Krauss gave a very nice empirical model. Meyer gave a very good empirical model. And if you look at the Payne effect, you have a filler-filler interaction, filler-rubber structure, hydrodynamic effect, polymer network effect due to Poisson density. You can see the factors contributing to Payne effect. And here you can see the weakly segregated and strongly aggregated structures. And if you look at the Payne effect, And you can see a beautiful picture here. This is tan delta as a function of temperature. This is a quite interesting slide. If you use silica, silica will give you very good traction. The tire companies now prefers to use silica because of traction, high traction. And look at the rolling resistance. Silica has less rolling resistance than carbon black. And if you look at this, again, G double prime as a function of strain, you can see carbon black and silica. See, rolling resistance of silica is much lower. So this is the magic triangle: air traction, resistance to aberration, rolling resistance. And I want to tell you, when you add small amount of filler, you don't have much of filler network. You can see a cartoon here. This is a low filler concentration. You can see the immobilized rubber, occluder rubber. This is high filler concentration. You can see the trapped rubber. Let me show you some work we did on natural rubber silica systems. If you look at the pure natural rubber, this is a pure natural rubber. You can see the pain effect. This may be a surprise to you. If you take pure natural rubber, we found some sort of pain effect. You know why? Pure natural rubber has some sort of gel. And when you add silica, you see 5, 10 nanosilica, 5, 10, and 15. They're very close, storage modulus. But when you put 20% of silica, there's a very strong pain effect. And you can see the corresponding E double prime. Because when you put 20% of silica, silica-silica interaction is very, very strong. You have a huge network of silica. That is why a sharp increase. You can see our AFM picture, 20 pH of nanosilica. You look at this in natural rubber matrix, very strong network. My PhD student showed a beautiful cartoon. We also wanted to understand the effect of temperature on pain effect. You can see this is the pain effect at 248 Kelvin. As you increase the temperature, the pain effect is decreased, because as you increase the temperature, you can definitely kill the filler interactions. So if you do mixing at high temperature, definitely the pain effect would be reduced. Let me also show you another important slide. We tried to fit the curve with Goris and Mayer model. It's a beautiful model, Goris and Mayer, where they have taken care of filler and filler polymer interactions. When you look at pain effect, there are two important aspects: the filler and filler polymer interactions. If you use Crowe's model is good at high filler loading, where Crowe considers basically filler interactions. Look at the beautiful fit we got. But this is at 248 Kelvin. Excellent fit with the Mayer model. This is at 263 Kelvin. So we could fit with Goris and Mayer model. So I would say that is one of the best models to predict the pain effect of elastomers. We also further introduced graphene oxide. Look at the work of graphene oxide. We introduced graphene oxide into elastomers, particularly polyurethane rubber. And look at the pain effect. You can see PU with 0.5. Graphene oxide 1.5, 3. And you can see the fitting with Goris and Mayer model. We got a beautiful fit. So we have tried this model in several elastomers. Goris model clearly explains both filler and filler polymer reactions. Let me now show you some of our work on ionic liquid modified is VR rubber. We had a big project with the Department of Electronics, where Department of Electronics wanted to make some composite materials where we could connect multi-volt carbon nanotube and SBR together, and we got excellent properties. Let me show you another important work we did with natural rubber and zinc oxide. We put zinc oxide natural rubber. Basically two aspects. One is reinforcement. Second is zinc oxide can act as a pure activator. So we made use of nano zinc oxide. I want to show you a very interesting slide. Look at this is neat natural rubber. Candle neat natural rubber. And we introduced 0.5, 1, 2, and 3 pHr of nano zinc oxide. And you can see the dramatic shift in the sensation of natural rubber. Additionally, the peak height is decreased because we found that the natural rubber is attached to the filler surface. There is strong filler zinc oxide natural rubber interaction. That is why the glass sunshine shifted to high temperature. The damping peak has been decreased because the natural rubber chains have been attached to filler surface. You can see some of the models we have given. So we have shown that very small amount of zinc oxide can have dual function. One is can act as an excellent reinforcing material, at the same time cure activator. We also did something interesting recently. We have mixed highly incompatible pairs, natural rubber and NBR. Natural rubber is non-polar, NBR is polar. You can see this is 30-70, 50-50. 30-70, you can see NBR is dispersed and natural rubber is continuous phase. This is a co-continuous phase. But when you add a little bit of clay, you have a dramatic change. You look at this. This is this is a co-continuous structure where natural rubber and NBR are sort of co-continuous. And if you put one part of clay, you see the co-continuous morphology is transformed. This is structure we have developed, and this is transformed into dispersed structure. This is NBR continuous, NR continuous, 50-50. But when you put clay into it, we found that the clay is predominantly localized interface, and you have a beautiful transformation of morphology. So we indicated that clay nanofillets have a very strong effect on reinforcements. Nanofiller has very strong effect on controlling the phase morphology of polymer blends. I also want to show you another interesting work, carbon black distribution in NRSBR blends. We are also looking at filler distribution using different techniques in a mass spectroscopy, dynamic mechanical analysis, high resolution transmission electron microscope. You can see this is SBR, SSBR, and natural rubber. And with carbon black, you see the whole carbon black is sort of located at the SSBR phase. And if you do the same thing by atomic force microscopy, you will see that carbon black is, if the ratio is 70 SBR and 30 NR, you will find that the carbon black is more located in the SBR phase. But if you change the composition 50:50, you look at there's a big change. So the distribution is controlled by several factors. The composition is also a dominant factor in controlling the distribution of fillers. Let me show you another work we have done with Apollo Tires. Apollo Tires, and we have very good cooperation. We have cooperation with MRF. With Apollo Tires, we did some very interesting work. We did a very good, nice patents. If you look at pure natural rubber is highly permeable to air. You can see this. This is pure natural rubber. If you put 1% of bentonite or fluoride, the compounding is by lattice stage compounding. You see there's dramatic reduction in the permeability of air. 5% of fluoride made the natural rubber highly impermeable to rubbers. You can see how we organize these platelets, beautifully organized the platelets. We also did something more. We have mixed chlorobutyl and natural rubber. You can see this is a permeability data. Neat chlorobutyl. This is 70. This is 100 CAR, 70 CAR, and you can see the amount of filler loading. To increase the filler loading, you can see the permeability decreases, because when you put clay, you have a decreased permeability. But something interesting I wanted to show you. If you take pure CAR, the permeability is 73.73. Neat NR is highly permeable to air. But if you put clay into CAR rubber, the best value we go to is 61.45 with 5% of chloride. But if you put 70-30 NR, 70 CAR and 30 NR, we got a very high synergistic effect. So this also led to a patent. So we found that if you mix natural rubber and CAR together, and when you put clay, you get beautiful synergistic effect. That led to a patent with Apollo tanks. Let me show you something on carbon nanotube. We are very active in carbon nanotube, putting carbon nanotube into natural rubber. You can see this is carbon nanotube, very small amount. Increasing amount of carbon nanotube forms a lot of connectivity. You can see this is a neat natural rubber. You see a beautiful linear viscoelastic effect. You put 1% of CNT into rubber, you get a linear viscoelastic effect. Put 5.4 weight points of carbon nanotube into natural rubber, you see a very strong non-linear viscoelastic effect. You know why? Because when you put 5.4%, a very strong network of carbon nanotube in natural rubber, and this network is progressively destroyed as you increase the strain. And this led to a beautiful work with a French company. We were making artificial skin for a French company. You can see the volume resistivity. We could make conductive rubbers. The resistivity decreases with increase of CNT. This again is latter stage compounding process. Let me now show you something interesting we have done with SBR rubber. If you take SBR rubber and if you put carbon nanotube, very difficult to be dispersed. But if you put a little bit of ionic liquid, you can have excellent dispersion of carbon nanotube in SBR rubber. And you can see the percolation we got. You see this SBR rubber, carbon nanotube with ionic liquid. You see the percolation process. And here, friends, we have a beautiful patent again with the Department of Electronics. Look at this, the EMI shielding. We made soft EMI shielders by combining natural rubber and CND using ionic liquid. Let me show you some of the work with biological nanofibers. We are extracting nanocellulose from different sources. These are some of the pictures on nanocellulose. This is some of the nanocellulose we have extracted from banana fiber. This is a wood flower, nanocellulose. This is from pineapple leaf fiber. I want to show you, look at a synthetic rubber, polystyrene with electrolyte. This is a neat rubber. If you put 6% of nanocellulose into these rubber latex, and if you do a latter stage compounding, look at the rubber is transformed into a high modulus material, very high increase in modulus. Similarly, if you look at the dynamic viscoelastic properties, look at this. This is a neat rubber. Neat rubber cannot sustain beyond 300. But if you put 10% of nanomaterial, this is a Tunisian whisker. Look at this. You get a real solid-like material. So, dear friends, rubbers can be transformed into a real solid if you put nanocellulose or nanochitin. They can form a beautiful network inside the elastomer. Let me also show you something we have done with the polyurethane rubber with my counterpart in Brazil. This is neat polyurethane. The modulus is 37.5. You put 5% of nanocellulose derived from pineapple leaf fiber, 992.4 modulus. And eventually we made lots of nice materials. Let me show you some of the work we have done with making sensors using rubber nanocomposites. We made use of natural rubber. We made use of IER rubber. The philosophy is very simple. You can see you put graphene platelets or CNT into rubber, soft rubber, lightly cross-linked, you tap on the rubber. Once you tap on the rubber, you generate a network. When you release the force, the network is destroyed. This is a philosophy. And that led to pressure sensing. Look at the pressure sensors we have made. You tap on the rubber, you make a network, you release the tapping force. You see, this is IIR rubber and expanded graphite. This is IIR rubber and reduced graphene oxide. So we made beautiful pressure sensors by putting nanomaterials into soft materials, soft elastomers. We can also make sensors, organic solvent sensors. Look at a rubber filled with CND or reduced graphene oxide. This is natural rubber. You put a solvent molecule, and the rubber takes a solvent. The rubber swells, it expands. When it expands, you know what happens? The network of CNT or RU is destroyed. That's the basic philosophy. And you can see we have made several constructions of organic solvent sensing with the CNT, CNT and graphene oxide alone. You can see when you put a solvent, you know, the rubber takes a solvent, and you can see the increase of resistance. After a while, the solvent goes out, and you see it goes back. Again, you expose to solvent, resistance decreases. So you can make beautiful sensors for sensing solvents. Dual phase sensing we can do. We can sense oil and water. What we have done is the rubber we have made use of is SIS rubber, styrene isoprene triblock polymer, and we made use of tiny as a filler. We have done in situ polymerization of tiny in an elastomeric matrix. And I will show you what we have done. If you put this sensor into oil, you can see the rubber takes the oil. Once rubber takes the oil, rubber expands. So you have a destruction of the network of tiny, and you can see the resistance increases. Look at this. And when you put in water, tiny likes water. Tiny takes the water molecule. Tiny is protonated, and you can see the resistance decreases. You have increased conductivity. You can also sense water and oil, dual sensing. If you put in the oil-water mixture, you know what happens? The water diffuses first, and tiny is getting protonated. The resistance decreases, and then oil enters. Resistance increases. So you can sense water, you can sense oil, you can sense oil-water mixture. Let me also show you something on hybrid structures. You can put hybrid fillers, CNT. That's a very fascinating field. We have made many hybrid constructions. CND and nanocellulose together. Latter stage compounding, and you mix the composite. Maybe with the lack of time, I'll show you a couple of slides. This is neat natural rubber with CND. You see the percolation here. You have to add more than 6 volume percent of CNT to get percolation. But if you combine CND and CNC together, look at the percolation process. When you combine CND and CNC, the percolation will be shifted to lower concentration of CNT. This is the same thing with reduced graphene oxide and nanocellulose together. You see, this is reduced graphene oxide and natural rubber. You get a percolation here. But if you combine reduced graphene oxide and nanocellulose together, look at the percolation shifted to lower concentration of RGO. So, dear friends, hybrid structures. I had a big program with the General Cables United States, hybrid structures, which I'm not showing today. Hybrid structures offer lots of possibilities. They can self-assemble, they can give increased dispersion and low percolation threshold. I'm going to conclude my lecture. Inclusion of nanoparticles into elastomers offer lots of possibilities. We have series of patents on barrier materials, putting nanofillers into elastomers, particularly clay. We also put nanomaterials, clay, into rubber blends. You could make excellent barrier material. We could make excellent EMI shielded, soft elastomeric shielding material, putting nanomaterials, particularly CND and graphene oxide. Very soft materials being made for EMI shielding. Mechanical reinforcements. we could increase the mechanical strength remarkably by putting nanofillers. But dear friends, you have to look at the chemistry. You have to use nice chemistry, nice surface active agents. We made electrically conductive rubbers for artificial skin with a French company. You stretch it, you can stretch it, but it's a conductive. This is also a wonderful material for biomedical application. For example, I showed you a work on, this is actually under patenting process. That's why I did not show much details of that. We put nanocellulose into polyurethane rubber. And my Brazilian counterpart made artificial, artwork using, polyurethane rubber and so inclusion of nanocellulose, nanomaterials offer lots of possibilities. Bioengineering, EMI shielding, conductive materials, bio applications, biomedical field, there are lots of possibilities. Let me thank all my co-workers, Lali, Vaishak, they're all abroad. Government funding, particularly, I'm thankful to Professor Sena Rao supporting us, huge funding from Nanovision, very close to 30 crores. You can see all funding agencies, international funding, PIX France, India, Sweden, India, Slovenia, TUAS funding, India, Brazil, DuPont, US, Gel Cables, US, Surface Street Czech, MRF and Apollo Tires. You can see my collaborators worldwide. My Indian friend, Nanda Kumar is my colleague now. You can see my group in chemistry. This is my group in chemistry. We did a lot of work with Yves Brockens, particularly on linear viscoelasticity of rubbers, pain effect. And this is my group in nanoscience and nanotechnology, a big group. We have students from abroad also in our group. And you're most welcome to Kerala after the pandemic. It's a beautiful part of India, so most welcome. These are some pictures of Kerala. We have, houseboats, very nice canals, Vokiniatam, Kathakali, old temples, backwaters. This is my university. I'm now sitting in this building where the Vice Chancellor's office, this is the entrance of the university. And we are organizing a international conference on macromolecules, and my good friend from Rubber Technology Center is giving a plenary talk on September 10, 11, and 12. We have a big meeting in the campus, online meeting. And I'm also editor of Nanostructures and Nano Optics. Right now, the site score is very close to 7.8. So those who work on nano, please submit your article. So thank you very much for your patient hearing. Thank you.
Thank you, Professor Thomas, for your extremely illuminating lecture and sharing the wonderful work that you have been doing. For the benefit of time, we are running slightly late, so I will not take any questions today. And I hand over the proceedings to Kinshuk to continue further. Thank you, Kinshuk.
Thank you, Professor Thomas, and thank you, Professor Mukherjee, for your very nicely conducting this session. So thank you very much, Professor Mukherjee. Moving on, we have the last session for today. We have 3 speakers. So speaker is on already. So this session will be chaired by Dr. Titas Mondal. Let me very briefly introduce Titas. Titas did his bachelor and master degree in chemistry from the University of Calcutta, MTech from this Rubber Technology Center, and well, he did his PhD with Professor Bhomik in IIT Patna, and then he joined industry, and he was in Momentive Performance Materials for about 4 years, and then he joined Rubber Technology Center as an assistant professor. So in this brief introduction, over to you, Titas, to conduct this session.
Thank you, Professor Naskar, for that brief introduction of mine. And just because we are running late by 7 minutes, I will directly jump to. So we have the next speaker with us, Dr. Lennart Clerk. He's from Kraton Polymers, Amsterdam, the Netherlands, and he's going to talk about the title of his paper is Kraton Polymers Boosting Circular Plastic Solutions. So Lennart got his MSc degree in both physics and chemistry from Utrecht University, the Netherlands, after which he did his PhD on imaging mass spectrometry of polymeric material. And after this, he moved into industries, and he worked into several industries like Akzo, DSM, in different positions over there. And he was like, you know, the leading force or driving force behind their imaging chemistry startup challenge. So since 2019, he leads the European R&D activities of Kraton Specialty Polymers business. So with that, I would like to invite Leonard for his talk. Leonard, you may continue, please. I think Leonard, you're muted. Yeah.
I should be unmuted now, and I was figuring out the slide. I think you should be able to see my slide full screen now.
Yes.
Is that correct?
Yes.
All right. Yeah, thank you very much, Mr. Chairman, and also especially the organizing committee. It's an honor to be here with so many renowned academics and also folks from industry. And I think actually I need to, because I think you see me now. I don't think you see my presentation now, right?
So we see you and your presentation both.
Both are visible.
Okay. Okay. Then it should be fine. You see my presentation full screen?
Yes.
Yes. Okay. Good. Figuring out how this sharing works. Anyway, so yeah, thanks for the organizers, Professor Naskar and Professor Piccioni. Sorry.
I think Leonard, you please continue.
Okay, good. Thanks for the invitation. So far, the lectures have certainly not disappointed me, and I hope I can provide a similar level of depth. Although, in fact, I would normally send one of the principal scientists from my team, but they couldn't make it because of holiday. So you'll need to do with the technical managers this time. So in my lecture, I'd like to highlight a couple of more or less recent developments through which Kraton contributes to circular plastics industry. Was nice to see a couple of things that I'm touching upon as well. For instance, Professor Hadjichristidis, he talked about the control of polymers at the molecular level. Of course, in a much more advanced manner through things that would maybe not work in industry at the moment, but maybe could work in future. But this is certainly something that we do as well in industry, but yeah, of course, at a more scalable approach. And then Professor Vennemann, he gave a nice overview of TPEs, their use and their technology and application. So I can skip a little bit of my introduction because of that. And actually, I would like to add that the world's largest tire manufacturer is actually using TPEs for their tire, but they're quite small because it's Lego. But I think that's a nice gimmick I always want to mention. It's the largest by number of tires, not by volume of tires, of course. Just a brief introduction on Kraton. We're a global specialty chemicals company. Kraton actually consists of two business divisions. One of them is focusing on pine chemicals, and you find those chemicals actually also in the rubber industry. For instance, we have some pretty nice thread enhancement additives based on pine chemistry. Much of that chemistry is bio-based. I'm from the polymer side, which is unfortunately not much bio-based yet, but that's of course something that we are working on. But we have our sustainability focused programs, and we do contribute to a more sustainable plastic and rubber industry, as I will show in my presentation. Revenue is a little bit less than 2 billion. So we're kind of a small multinational, but I think we're one of the more innovative ones in this field. We spend quite a bit on innovation, have a strong patent portfolio. We have in every region we have some R&D activity. So myself, I'm responsible for our activities for the specialty polymers business in Amsterdam. We have labs in Houston as well as in China, and some smaller R&D centers in India, Japan, and Brazil. We collaborate in the consortium of Together for Sustainability. That's a collaboration between various corporates to align on the sustainability objectives, as they were also defined by the United Nations. And actually, as part of our sustainability effort, we look at making our business more sustainable, and that was certified with an EcoVadis Platinum license. So we're actually in the top tier of sustainable companies. This APR logo and the Plastics Recycling Awards Europe refers to one of the things that I'll come to later. It's about recyclability of our polymers and about their use in upcycling of recycling streams. Just a brief introduction to styrenic block polymers. I think you have seen this image. It's just a little bit different, but I think it's important to maybe reiterate, because I'll come back to quite a few of these aspects throughout my talk. We make styrenic block polymers, which means that in this case it's a tri-block, and as you will see in a later slide, there's more designs possible. It's a block polymer consisting of a styrene block, a rubber block, which can be isoprene or butadiene based in our case, and another styrene block. And you have a physical cross-linking mechanism through the styrene blocks, which is driven by incompatibility, chemical incompatibility with the rubber, but also, of course, by a thermal effect of the styrenes having much higher TG, so they basically separate out also as a temperature effect. So they form amorphous domains, which give these physical crosslinks, which are of course reversible, because if you raise temperature, you take them apart at some point, and actually if you also put on shear, as you do in an extrusion process or in injection molding, you even take out more of that, and that is one of the key driving mechanisms in some of the situations where our polymers work so well. Then there's the other phase of the soft segment, so the rubber mid blocks. They are soft and flexible. They have low TGs depending on the chemical nature. So if you have a butadiene based mid block, it's like -90 degrees roughly. Isoprene based is about -60 degrees, and then you can hydrogenate them, and that's actually when we call our polymers specialty polymers. We have those are the hydrogenated styrenic block polymers. Of course, they have the benefit of higher stability, both thermal, UV, and some other aspects, but you also increase the TG a little bit. Those are also the parts of the polymer that are oilable. So in a typical TPEs compound, as you would call it, there's some oil added, and that is where the oil is and acts as a plasticizer. So that is typically a regular mineral oil. So as I said, we have in our production, so we can actually make our styrenic block polymers in various ways, and it's all done through anionic polymerization. That's, I think, why there's still a relatively low number of companies doing this, because it takes some quite significant safety measures. So you can start making a die block and then couple it to a tri-block, or you can make it sequentially. If you start making a die block, you can also couple it through various chemical coupling mechanisms and make radial polymers or even star polymers. So there's various design possibilities here. And of course, you can combine the different designs if you want to reach certain properties. One of the key things that I touched upon already a little bit is the rheology of styrenic block polymers. And the key thing here is that our polymers are very shear sensitive. So if you work at a certain temperature, so for instance, I'm showing the melt viscosity here at 200 degrees. If you increase shear, the effect of shear is much higher than for instance, a polystyrene homopolymer or a polypropylene homopolymer. You see a 5 MFR, so melt flow rate polyprop. We do actually give our polymers melt flow rates, but they can sometimes be misleading because if you put more shear, it flows actually a lot better. So sometimes you see some of our polymers which have a fairly low melt flow rate, and they actually, if you use them in an extrusion or an injection molding process, and you put on a shear of like 1,000 or even higher, you can actually process it, and it flows pretty well. So if you look at also the melt viscosity, depending on molding temperature, it's a fairly flat curve. So it also gives some processing robustness if you compare it to, for instance, just a polypropylene. Well, most of the styrenic block copolymers are not used as such. It's actually quite rare that people use a pure styrenic block copolymer. Typically, they're used in a compound, or they're used in well, as a modifier in a hard plastic, and then you're looking at impact modification. So a typical compound would consist of a styrenic block copolymer, an oil, and a polypropylene, and you can, of course, add all kinds of additional components like fillers or even some functional materials. We would actually, in our company, we always talk about a GOP compound, so it's a Kraton G oil polypropylene, and depending on the ratio of the different components, you get a different kind of morphology or micromorphology. So, and what you're often looking for is an interpenetrating network because it gives a good combination of the two properties. But sometimes, of course, you're also looking to be a bit on the extreme side and have one component in the other. If you would take out completely the polypropylene, you get an oil gel, and those are also, they're pretty solid materials. So you would have like 20% of styrenic block copolymer typically, and then the rest is mineral oil, and those are all kinds of gel cushionings. There's actually some examples in the US where there's gel mattresses being made out of this kind of material, but you can think of anything that looks and feels like a gel. You can make it from this. The nice thing of these phase structures is if you tune them correctly, they're pretty stable. So they're stable for weeks at 200 degrees. Once you have them and you don't put them in the shear, they're stable. And here you can see some micrographs, as I showed before as well, some transmission electron microscopy. You can visualize it quite nicely. If you take the right staining method, you can color the styrene domains, and the others, the rest will look lighter. Well, just briefly, how are styrenic block polymers applied? It's a pretty broad range of hardnesses. So you start with Shore 00, and that's more like the gel world. So shoe soles, toys, cushions, etc. Even if you take dye blocks, it's used in oil modification and in cosmetics, for instance. Also, tri-blocks are used in cosmetics, by the way, as for instance, depilatory waxes, because they give some strength to a wax, and you can basically, you have some more cohesive strength through the tri-block network. There's the soft touch world, and these are typically like handles of things, whatever tools, but also, for instance, toothbrushes, but it can also be, well, basically any grips or seals, but also hoses. And these hoses I'll come to as well as an example for PVC replacement. And you could also look at replacing silicones for recyclability reasons. And then there's plastic modification. You can add Kraton to various types of plastics, and circular plus is an example of that I'll cover that briefly as well. Well, first example is looking at high transparency flexible compounds for PVC replacement. This is work that was built up, I think, between 1 and 2 decades ago, but you still see quite a bit of traction from the market because PVC remains a material of concern in some applications. And in this example, I'm looking specifically for medical. For instance, there was this request from Swedish hospitals, and they are quite remote. They need to burn their hospital waste locally. And if you do it at too low temperature with PVCs, you get all kinds of compounds of substances of concern out. So they had to get rid of it. Moreover, PVC, there's some other issues as well. And then we're talking about specifically hoses in medical use, but also, for instance, blood bags or IV bags. Well, PVC is a brilliant material, right? Because it's you can make it transparent, you can make it very nice and soft and flexible if you add enough plasticizers. But there's some concerns. There's the concerns end of life. There's also the concerns of the plasticizers, although they've overcome quite some of the concerns around the phthalates. But anyway, as Kraton, we thought it would be worthwhile making an alternative for that. And we made one, and we did it actually through an enhanced rubber segment. So we redesigned the rubber segment of our styrenic block copolymers to meet better the requirements for transparent, flexible compounds. So the enhanced rubber segment, the key thing there is that we increase the amount of vinyl. So if it's a butadiene-based rubber polymer, and you can, as you probably know, you can polymerize that in a 1,4 way or in a 1,2 way. And in the latter case, you get more vinyls. And then, of course, you hydrogenate them in this case, but well, within the company, we call it high vinyl. So you have more branching, basically. It's like a short chain branching. And that gives a very soft material. So it also increases the melt flow of the polymer. So it helps processing. It helps processing, and it's getting softer. So you can do without plasticizers, which is of course good news if you want to look at medical applications where you don't want extractables. Moreover, the compatibility with polypropylene is better. And through this higher compatibility, you get clearer compounds. Of course, it's nice that it's thermoplastic and recyclable. That used to be a non-issue in medical because they would burn it anyway for biohazard reasons. But recently, there's also an uptake in the medical industry that they want to look at recycling their plastics. So there's all kinds of applications for this, but of course, well, this is more of a scientific audience, so you're more interested in looking at the transmission electron microscopy images. So these are two examples. So the top one is an G1650 with polypropylene, a 50-50 mix. And it's showing basically dark stained are the polystyrene domains. So it's showing the size of the domains of the polystyrene. So these are polystyrene rich domains. So you see that they are pretty coarse. Now, if you take a G1642, which is an ERS grade polymer, you see that there's a much finer network here, much finer interpenetrating network. This is, of course, good news. If you have a difference in refractive index between materials that you blend, you get all kinds of scatter effects. But if the domains are very small, those scatter effects are less. So the good news is that you can make very nice transparent compounds here. Why is this working? Well, there's actually two reasons why this is working. It's a matter of property matching. And on the left, you see an image showing the thermal properties of the rubber block as measured by DMA. And by increasing the vinyl percentage, or actually to be chemically correct, the butylene percentage, you bring together the rubber TG, which is on the lower side, and the amorphous phase TG of the mid block, and you bring it together to one TG, which actually matches the TG of polypropylene fairly well. So that's one reason for compatibility. Moreover, there's also chemical compatibility, and this was mentioned before as well. The matching in solubility parameter. The better the match in solubility parameter, the smaller the phase size. So that also helps. Now, getting smaller particles, that can of course be done by putting a lot of energy in. So through your increasing the shear of your processing, but you would get far less stable systems. So once you apply shear again, you may lose that kind of behavior because you have a basically kinetically frozen equilibrium, and it's not really the thermodynamically advantageous state. All right, another example, and this is a recent one that we're pretty proud of, and we are pretty proud of it because we put a lot of effort in it, and this one commercialized quite recently with actually the first commercial car driving around in China with our technology in. This was developed by Kraton with various partners over time in the last roughly 10 years. So it has cost a lot of effort and investment, but I think we achieved something really nice, and I think it's a landmark in the car industry in their lookout for lighter weight and better circularity. So IMSS, it's a trademarked name. It stands for injection molded soft skin. Some of the luxurious cars, they have this very nice soft touch instrument panel, and normally the current standard is PVC slush molding, or in some cases I think they also use EPDM, but it's mostly PVC. That's something the automotive industry is worried about because they want to get rid of it for recyclability and for also for reasons of weight, because PVC is heavier than a TPE compound. So we developed a technology that can produce such skins by ordinary injection molding machine. It's a huge panel, so actually the art of injection molding is really important here, and it's a very thin wall application, so it's quite unordinary for an injection molding application. So we started with basically, if you look at from polymer to car, what you start with is an HSBC polymer. You compound it. You take the compound. It's injection molded by a tier 1 supplier who makes the instrument panel skin. And then actually there's another tier 1 in some cases who add the backing of that skin, and then it goes to the automotive company. And you need to get all partners aligned. So that's one of the typical examples in industry, getting people aligned. We spend a lot of time talking to get people aligned, and much less time on the real science compared to what you're doing. Anyway, there are significant technical challenges. As you can imagine, having an instrument panel, and you know dashboards in cars, they're big. You need to have your polymer match those dimensions, and you need to make sure that there's enough flow, so you're reaching also the interestingly shaped corners of this instrument panel. And we put the requirement of that there's no special injection molding machine needed, because we didn't see tier 1s invest millions and millions into a new injection molding machine. As a matter of fact, and just the mold is already around $1 million investment, so that's already significant enough. So we had to develop high flow HSBC polymers, and that's what we did. And in the end, the result is basically, and I'm looking at sustainability here. We actually got nominated for an ERJ top 10 award. And actually, the outcome is that you can save weight on your vehicle. There's improved aging and fogging and VOC and odor performance because it's phthalate-free and low plasticizer. In some cases, we reached an improved abrasion and heat resistance, and it's thermoplastic, which is of course helping recyclability. Now, of course, you're curious about the technology behind this, and the technology is all in rheology, and we contribute part of this, and our compounding customers contribute the other part. So this is all about the rheology of the HSBC we're using, and these are two chemically comparable HSBCs in the dotted line. So G1643 is an ERS grade Kraton, and you see the curve here in orange. And if you redesign that polymer, and that's a combination of styrene block size, molecular weight, etc., you can significantly reduce the shear viscosity. So depending on shear, you get a much better flow. And this is of course helping injection molding in this region, which is the typical shear rate in injection molding. And now if you make a compound, and the green line is giving a classical Kraton G-based compound, and the blue one and a compound that was developed for IMSS, you can even reduce this a bit more. And by tuning this viscosity at a certain shear range, you can reach the long flow paths that are needed for such a large object and with such thin walls. Of course, there's an awful lot of other properties that you need to test, and we did all that: heat, aging, scuff, mar, weathering. There's well, you wouldn't think of it initially, at least I didn't, but one of the key aspects is airbag deployment. If an airbag deploys in an accident, you don't want pieces to be flying around, so things need to tear open properly, but still need to stay together. It's all that kind of properties that you need to think of. And there, the polymer design is key, but it's only it's still a fairly small part of the total picture. Last topic for today, Circular Plus. I'm not sure how much time I have. I think I have like 5 minutes left. Is that correct?
Yes, that's correct.
Okay, good. So you all know that circularity in the plastics industry is a key challenge, right? And we contribute our part to it. And this topic is actually about plastic modification rather than about thermoplastic rubbers. There are some key issues in especially mechanically recycled post-consumer recyclates, but also post-industrial. There's contamination. For instance, if you want a recycled polypropylene, quite often there will be small amounts of polyethylene in there because it's technically difficult and then also economically unfeasible to completely separate them. This leads, there is some incompatibility between those two different types of polymers, which is impacting the mechanical properties. Even worse, if you have contaminants of maybe some biological fibers, metals, etc., it can actually lead to defects. You can never get completely pure polymer streams out of a recyclate unless, of course, you do chemical recycling, which is one step further and is, well, in some cases, it's the only option. But of course, you want to stay as close as possible to the original polymer structure. So what we can do with our Circular Plus compatibilizers, and we developed them specifically for this market, it is actually based on styrenic block polymer technology, but they are focused on this market. We can stabilize the morphology, we can enhance the properties. That's something we did already because HSBCs are quite often used as an impact modifier in all kinds of plastics. And that balances, of course, with the recycling industry's drive towards pure PCR streams, but we can also actually, in some cases, improve processability. This is an example. Excuse me. This is an example, and we're comparing here with a polyolefin elastomer, because that's a solution we see quite often in the market as well. It's always good to compare with a competitor, and mind you, they're doing a fairly good job. But I think with a styrenic blocker polymer, you can do better. There's a much stronger balance between the modulus that you want to retain, because you don't want weak objects, you don't want things to bend too easily, and the impact improvement that you can reach. This chart is showing in yellow. It's showing the PCR polypropylene. I believe this was a 95 or maybe 98% pure one, so it's already a fairly pure one. But you see that the impact resistance at room temperature, and especially at low temperature, is not good enough. Now, adding about 9% of the circular plus additives increases that impact resistance, but keeps the modulus at a fairly good level. There's also a little bit of impact on the melt flow rate. Well, this is an overview of how our compatibilizers work, and this is actually an example of a soft phase being dispersed in a hard phase matrix, but there's also the compatibilization effect. I think Professor Vennemann showed a nice image of small rubber bits in a hard matrix. That's more or less what you have at 9% addition. You start to having those domains, but if you go to a much lower percentage addition, you do have the compatibilization effect. So you do already increase your impact strength quite a bit, but you don't have this significant loss in modulus that you often see when you add more. Depending on the processing conditions, you can choose between the different grades. The C3000 is an unhydrogenated styrenic blocker polymer. C2000 is hydrogenated. It's so that one is a bit more powerful if you, for instance, process polypropylene, because you can go also to a bit higher temperatures. There's another example. This is actually looking at two, well, pretty much completely incompatible streams. This is looking at the compatibilization series, so the C1000 series, and these polymers can actually make the incompatible compatible. So if you take a PCR polypropylene, a PCR PET, and a C1000, you can get pretty good properties, and even combine the two streams, which can be beneficial, and it's showing that you can sometimes live with some contaminants. Well, just very briefly to wrap up, a couple of other sustainable solutions, a little bit outside my direct working scope. We have the highly modified asphalt, which improves pavement performance and reduces maintenance. So it's a styrenic blocker polymer added to bitumen, and it's basically giving elasticity to a road. We have some Silver Road RP1000 performance additive that helps recycling of asphalt. In adhesives, we have our Revolution rosin ester, which has a very high bio-based content as a tackifier. You can enhance the performance through a styrenic blocker polymer technology. And I mentioned already briefly our Silvatrax strand enhancement additives in tire. They help with rolling resistance and grip balance. And there's some core rubber additives that we have as well as processing aids. So thank you very much for your attention. If there are any questions, I'm happy to answer them. If that doesn't work now, feel free to drop me a note. We're always on the outlook to new technologies, new ideas, even new collaborations. So yeah, I think I've given hopefully a nice industrial perspective. It's quite often that academic ideas take a long time to industrialize, but if you see some perspective to reducing cost of processes and things like that, then I think Kraton could be a partner to scale that up. Feel free to drop me a note. So thanks, everyone.
Thank you, Leonard. And we are just, we can take a couple of questions. There is already a question from one of the graduate students, like, can ACVS grades with enhanced rubber segment be compounded without using polypropylene?
Yes, in principle, you can compound anything without polypropylene. The question is, what else do you want to put in? Because in the end, ERS grades were designed to be compounded without processing oil. So quite often what you see is that you use some polypropylene still to get some of the benefits from that polymer. But in principle, yes, you can compound them as such.
Right. So there is a question from Professor Nikos. It's like, he would appreciate if you can comment on the difference in the properties in general between the linear and star-shaped structure and how they are made.
Oh, yeah, that goes quite deeply into the polymer technology, and that's one of the reasons I normally send my my principal scientists to such events. But anyway, I'm assuming that tri-block and di-block, that is probably known. I mean, tri-block gives strength, di-block gives no strength, but it sometimes helps compatibilizing things. And actually, sometimes you get some tech out of that. Now, these star polymers, of course, they enhance the network, so the whole thing gets a bit stiffer. In some cases, actually, these are used for oil modification rather than for rubbers. So these give some pretty nice features in viscosity improvement of oil.
Thank you very much. Thank you very much, Leonard. Excellent talk.
Thank you. Leonard, I have one question, perhaps this is the last question. I was curious about the IMSS technique, that the soft touch material which goes into the front part of the car. Like, how about the dirt pickup? Because many a times, especially in this part of the world, there are a lot of dirt accumulation in that particular area. Yeah. So that is one. And the second is, if you are exposing that vehicle for quite a long time in hot, humid condition, in the parking bay, so how is it going to impact the properties?
Yeah, so very good question, because I think that those were the key struggles, right, in this project. But we did meet at least for some OEMs the complete specs. For some, we're still struggling because it is a challenging technology. And then if you talk to them, they say, yeah, but yeah, actually this temperature, we know it's a bit high, but it works for PVC, so you guys should meet it as well. Then if they see all the other benefits, sometimes they can go down a little bit in temperature. But yes, this material was tested in like the Kalahari Desert kind of conditions. One of the key dirt pickup issues is like sunscreen, because people put their sunscreen on their dashboard for some reason, and then the bottle leaks and they don't want the stain. So you need to cope with that. I mean, it's an awful lot of tests. I don't think you even want to know how many tests you need to pass for automotive industry. And some of them don't make sense, and some of them really make a lot of sense. But in the end, it's the customer who decide, right? Yeah.
Thank you, Leonard, for your wonderful talk and introducing what Kraton is doing. And really appreciate your talk, and thank you so much.
You're welcome. Thanks for your time.
So with that, it's my pleasure inviting our next speaker, who is Professor Shantanu Chattopadhyay. He is currently the professor and head of the Rubber Technology Center at IIT Kharagpur. He has been serving here as a faculty since 2004. So Professor Chattopadhyay has pursued his postdoctoral research work at Georgia Tech and USA from the Chemical Engineering Department. And prior to that, he was also in Western Ontario, Canada. And he did his PhD from IIT Kharagpur and his master's from IIT Bombay. So he has published more than 140 papers in international journals and more than 100 conference proceedings. And currently, he has supervised 16 graduate students and 45 master students. And today he is going to talk about the application of FEA in rubber technology. With that, I would like to request Professor Chattopadhyay for his talk. Professor Chattopadhyay, you are muted.
Am I audible now?
Yes, you are.
Slide is visible, right? Full screen?
It is.
Right? Yeah. Professor Mondal, is the slide visible full screen?
Yes, it is visible full screen.
Perfect. Thank you. First of all, thank you very much for your nice introduction. And a very good morning and good afternoon to all of you. The more precisely, my today's title is Damage Modeling of Silica Carbon Black Filled Elastomeric Composite, Finite Element Analysis and Experimental Validation. Before I go into my work, let me quickly introduce you to IIT Kharagpur, although we have talked about IIT Kharagpur in the very introductory inauguration talk. But nonetheless, you can see we have about 19 departments, 14 centers, 12 schools, 30 plus R&D units. And altogether, it's a 2,200 acre. We are spread over there. And it's the largest and the first IIT. And in terms of disciplines, you can think of all basic sciences and engineering degree that is provided here, and inclusive of management, law, and medical school has recently come up. Soon after, we are going to offer MBBS degree also. So our total student strength is about 13,000 now. I mean, I'm sorry about the figure is a little old, and we have about 1,000 faculty members. And we have also outreaches in different parts of the country now, in Calcutta, in Odisha, as well as in Hyderabad, the south part of it. So the goal of not only the country, goal of this IIT also not to catch up. I mean, our goal is to lead from the front, actually, in terms of technology, which will rule for the future. About Rubber Technology Center, as I mentioned, it started its journey, I mean, right from the time of inception of the institute, but we become independent center in 1981. And we acquired mostly advanced processing and testing equipment under one roof. And in 2014, we have been awarded the top Asia's top institute for research and education in rubber in particular. So this is what about Rubber Technology Center. We are small in terms of number of faculties now. We have 6 faculty members. Me, Professor Sheena would there, second one, Professor Noskar, Professor Dash. We have Professor Mondal as well as Professor Somadip Chaudhary. And in addition to that, we have 4 non-teaching staffs, including the technical staffs. And we have about 42 now. The figure is a little old. MTech student, both first and second year. And we have about 55 PhD students. And in terms of our output, we offer 400 plus publication in international journals. I mean, on an average, it sometimes goes more. Patents, book chapters, international conferences and short-term courses are quite regular here. And some of the new faculties are also going to join soon. About my research areas, it's spread over like a 5 fingers. Basic rubber polymer, inclusive of thermoplastic elastomer. Indeed, it was my PhD topic. And it includes structure property relationship, alternative source of natural rubber, green technology. And then in simulation of rubber product that I am going to highlight today's lecture, high performance radiation resistant seals, insulators, cables, particularly for aerospace and automotive applications. In the smart material front, we do work on conductive EMI shielding material, also of course, bit on smart materials inclusive of textiles. The energy is the need of the day. In that front, we also explored the application of rubbery polymers as an energy material, particularly as a thermoelectric material as well as triboelectric material. And in the healthcare sector, we normally work in two different phases: use TPU or TPU modified TPU based polymer and block copolymers for bone tissue engineering and drug delivery, targeted drug delivery application. This is briefly about what my group does here. Coming to today's talk, I'll start with a prologue about talking about what is the importance of fracture mechanics, then introduction, materials method, characterization, and then subsequently I'll take you to the right methodology. If you go back in Boston molasses tank failure in 1919, it was a huge tank having 2 into 10 to the power 6 gallons of molasses, and you see the paper cutout in Boston what it happened. It was a almost 11 people died, 13 were injured, more than 50 were injured. They are badly stuck with the molasses basically. You can see the cartoon right over here. This is what is the tank, what it happened. So the reason was fatigue crack propagation from the near base of the tank was underestimated. Thermal shock was not taken care of. Day to night, winter to summer. And also the health monitoring was really poor for the structure. Similarly, one of the devastation that it happened in Liberty ships back during the Second World War time. Out of 27008 manufactured Liberty ships, almost half of them were damaged because of the accidents and because of the failure fracture. The reason was, once again, it was insufficient fracture toughness of the material that was used, particularly at low temperature. Welded joint was poor and crack growth was not taken care of. So if you see the figure right over here, the fracture toughness of the material with the temperature, there is a drastic transition from brittle to ductile transition. You can see it failed from the welded joint. That was the edge where the stress concentration was high. And not only that, the ship when was traveling, somewhere the temperature of water was really very low. The material of construction become really brittle by that time. So it's kind of a brittle fracture that culminated to catastrophic failure that way. Coming to our baby, like a tire on which the entire civilization is running. Okay, you may be recalling the Vennemann mining accident that happened in 2010 in Australia. Okay, that was a failure. It's simply a separation between the trade and sidewall of a tire. Okay, and that also culminated death of more than dozens of people. Okay, so it is once again fatigue crack propagation of the tire is very important that way. In fact, following that, in 1956, one of the very important journal in the domain of fracture, engineering fracture mechanics, was introduced, and two pioneering persons in that facets are English and Parrish. Although name sounds like English means British and Parrish means like France. It's ironically their name goes like that. You may be hearing about the Paris plot and all. Okay, I'm not going into that history part of it. But if you just analyze the failure of the tires that had happened, 73% of that it happens because of bursting of tires. Okay, once again fatigue crack propagation. Even you can see in the cartoon the small blemishes. Okay, if you underestimate it, if you don't monitor the health of the tire, it may culminate to once again like a Venn McDonald type of an accident. Okay, so today's tires are having some gadgets which will give you at least some automatic information about what is the roughly about the tire. Everybody is bothered about to having a very good polish, very good color, exterior, interior, etc. But how many of you really look every day what happens to the tire? And that is, after all, rolling us, giving us the safety driving across over hundreds of kilometers an hour. So that is very important that way. So not only that, coming to the context of today's webinar, you can see it's a sustainability and green revolution actually, okay, and recyclability. So now one of the things what is going to be a paradigm shift, it's going to be electric vehicle. So what it differs, I'm not going into the interior of the car, what it changes, I mean, dozens of existing, devices or material there were replaces new one. But looking at the tire alone, EV means longer braking distance, higher instant torque. So if you have to coin with the green revolution with that of the requirement here, you need to have a low friction tires for electric vehicle, optimum grip for shorter EV braking distance. Of course, the low noise in electric vehicle and robust compounds to withstand electric car and the torque in particular. If you see battery car is already estimated, it's going to capture 85% of the market share. If you see a projection from 2017 to 2025, you see it's going to be a tenfold rise in terms of market. Okay, so next step jump will be the hybrid, and of course it's going to be plug-in hybrid for sure in the years to come. So after all, everything will center around the same theme: green revolution and sustainability. So if I look at silica, one component I am talking about it. Many of my speakers before me talked about the sustainability, natural resources. Okay, one of that kind is a silica, because silica has certain definitive advantages in terms of rolling resistance and weight grip, and you can really match the wear resistance as well. So you have an edge in terms of magic triangle. But do I really bother about how the fracture happens? What is the factor that governs for the silane-treated silica compound as compared to carbon black? How much percentage really we can offer to replace without compromising its fracture toughness or fracture properties basically? So that's going to be the essence of the today's talk. So if you look at FEA for the beginner, FEA is a numerical method for the prediction how a part or assembly behaves under given conditions. So essentially what you do, you try to solve partial differential equation in each and every element. Okay, so there you finally you integrate, try to have a global solution to that. Okay, so what it does actually, if you do it, it not only reduces your several trials, but also in sooner or later it will give you a definitive method to reduce the scrap. So reduce the trial. So it is also a sustainable tool basically. In tire also, if you see a tire segment of the tire is modeled here to give you some sort of a stress concentration. Here is a vestibules that is collapsing. Okay, so you can see at the edges how the stress is getting concentrated. So in the design itself, you have to take care of, you have to predict what's going to be the life. For your information, as compared to plastic industries, rubber, if you look at the extruder, if you look at injection molding machines, rubber was the last man to take injection molding. Before that, prior to that, compression were everywhere there, even though we know that injection has several advantages. So similar front, rubber technology or rubber companies, they have taken up. I mean, seriously, the biggest giants are the biggest players are the tire industries. They have taken it up. Even in small sector, they are taking up. Suppose if you want to have a window sill you want to make for BMW car, unless otherwise you show with the simulation that your thing is going to perform that way, so you are not going to get the order from the OEM. So that it boils down there. So finite element becomes a very sustainable tool in the rubber industries, and of course to days to come it's going to come show its presence even more heavily. So now coming to the fracture mechanics, how do we implement it? We have to really see the course of initiation and propagation of crack, okay, and the real life how it is happening, and also we have to simulate. So there are three methodologies that is very much popular. One of those is contour integral method, that is by and large practiced, that divides region into different contours, and that those contours that actually your stress concentration you get it, and you try to integrate it. The second is extended FEM. It reduces the remeshing stuff, but it is useful for complex geometry, as it is shown the right side of the cartoon. And the last one is CZM. It's not very regularly practiced one, but that it is very important for intricate joints. If you have, suppose even in a tire, if you try to integrate the bead part with that of the sidewall, with those of the with the tread, and then the bales, the other components side by side, you really have to go for the final meshing, of course, and also find out the cohesive zone method basically. So here is the way we practice here. See, suppose if first of all you have to really figure out what hyperelastic constitutive model is working for you, and that you have to give it as a feed in your. By the way, before I forget, we try to use Abacus platform. You can use in your own code. You can go for any other platform, but basic methodology remains same. What we did, we have tried measured the properties of our rubber, both in tension and both as well as in compression. Okay, so what we generate end of the day is a nominal stress strain curve. Okay, and that you have to really do the constitutive modeling. You have to really figure out, there are different models. I'm coming to that. So you come up with a model and that you put it as a feed. Okay, then you try to implement in your particular device or whatever test you are going to do. So here we have tried to put in the boundary conditions, and based on the condition we try to mesh it and try to model it. Here we have implemented it for the for a diaphragm, say for example, used for aeronautical application for defense. We have been successful quite on that. But I'm not going to highlight on that how do you do the live prediction. That is that I'm for sure going to share with you in a different platform. About the materials, we have taken solution SBR. We have taken two types of carbon black, SIF and HAF. We have of course used HD silica and silen, and rest of the ingredients we have taken as per required. I'll show you the formulation, and all the components are of rubber gate, and it was used as such without any further purification. You can look it at the formulation starting from S0 to S5, S50. So what we have everywhere, we have tried to mimic some sort of a trade sort of a formulation, close to that, not trade, I'll say. So SIF we have given everywhere 10 pHr constant. So then what we did, we actually tried to vary HD silica and of course 10% with respect to that silent Si69 we have used. And we have made, I mean, 6 such composition altogether. Of course, S0 is the control, having no silica filler in it. And to have one-to-one comparison with S30, that is a silica loaded one, we made one with the HAF. So our silica size, primary particle size, the reinforcement point of view is it was very close to that of HAF. So we chose the H30 for the final comparison. I'll show you at the end. So about the machines, we are used very traditional machines for RPA for having a feel of the pine effect, DSC for the glass transition, field emission scanning electron microscope for initial assessment of the actually filler state of the dispersion of the filler, as well as FTIR. So we basically measured the tensile properties with a UTM, and compression also we did it with another UTM here. We have done nano indentation test as well to assess the the indentation hardness or low strain modulus of the components. So then we have showing you how we meshed it actually. So we have used a smooth sample as well as a notch sample where you have a pre-crack. Okay. So and also we have two types of notches. One is single edge notch and a double edge notch basically in tension. So we have two notches side by side, you can see, and we have put in boundary condition like it is encrusted here. That means it's immobilized there, and we are trying to put the Dirichlet boundary condition at the end where from your tension force is given, and you can see here the crack, and in course of crack propagation will be monitored eventually. So this is the nano indentation test. Okay, this is the indenter. Of course, it's like a Berkovich indenter having infinite modulus, we assume, and this is the angle, this is the point of contact. We tried to traverse it 1500 nanometer inside the rubber specimen back and forth. And this is the in symmetry in 2D representation of the same thing is like this only. This is the point where you have indenting, and this is the indenter. And if you have a 360-degree rotation, you get this same thing. So it shows you the finer meshing. Of course, it is so close to that those contours, we have a very finer meshing. So we have done mesh optimization study, and we have tried what number of meshes are good enough to capture those phenomena. Then its pure characteristic of it, as usual, we monitor with the ODR. You can see the delta torque is increasing incrementally with the increase of the filler, and same is the case. Of course, the Scott safety is decreasing. So this is all about S0 to S50 in terms of pure characteristics of the compounds. Then we assess the pine effect. You can see one thing for sure, up to 30 pHr of silica filler, your pine amplitude, okay, the reduction in actually ultimately you can normalize it also. So after 30 pHr is drastically high. So you can anticipate one thing, there must be some sort of aggregation. But in terms of glass transition, there is not much of difference. Of course, for S30 compound, the heat flow is a little bit more, I mean, in terms. And we monitor the 10990, that peak that represents the silica. For obvious reason, area under the peak will increase as expected. But most importantly, as I mentioned, from the pain effect that is reflected here. So if you monitor from S0 to S30, you see the distribution is getting better and better. But from S40 onwards, there are agglomeration and aggregation that is happening. Although I have TM picture to have a representative bulk morphology, but because of the paucity of time, I reduced number of slides. But this is what is happening. There is a smooth transition, sharp transition from S30 to S40, at least in terms of filler distribution into the rubber matrix. Then we try to capture tensile stress strain properties. As you can see, same is reflective. Up to 30 pHr, we got the maximum elongation, and of course the highest tensile strength, because silica is obviously better dispersed in that case. But also in compressive state, I mean stress strain property also, you can see the successive increase with the filler loading. And same is with the modulus and reinforcement index, which is nothing but the ratio of the modulus with that of the tensile strength. So everything is fine. I mean, what is expected from the very initial pain effect slide. So now we try to capture the nano indentation load versus depth. I mean, indentation depth, you can see obviously for the higher filler content, you have the highest hardness here, the peak load, and also the most importantly, the hysteresis is going to increase. Okay, obviously it says same thing, that you have a filler aggregation that breaks for sure. Now coming to the constitutive modeling, as you can see, you can really go to the several constitutive modeling. Okay, so based on the strain energy density function, and you have the strain invariants as well as compressive visibility factor and Jacobian here. So you can see the basic model is Mooney-Rivling. It's very elementary. It really cannot trace the whole length of the stress strain properties. So New-Hookean is the even simplified one that is derived from statistical theory of elasticity. But your model is basically, it takes care of the phenomenological model. It takes care of the deformation of the chain. You can see it has more polynomials actually. But most importantly, if you look at Ogden, Ogden is one of the most adored models, particularly in the fracture studies. So in our case, we tried to do the regression for all the models. You can see that although EO and Ogden, both of them showing at 0.99, but actually it is not the, I mean, only the R-square value doesn't really give you the absolute knowledge about that. If you do the tracker stability study, I mean, in terms of, you see here at the low strain, it is deviating, high strain, it is deviating, but in between it is merging, so you are getting 0.99, somehow it is balanced out. But in Ogden model, it's really going through and through from the origin to the up to that position. So we have taken up Ogden model for n equals to 4 as our constitutive hyperelastic model that we feed in the software. So you can see the FEA validation, we same thing, we try to feed in and mesh the system for a tensile dumbbell and try to see, and you can see the results, how beautifully it is tracking from S0 to S50, all the samples. And this is experimental vice versa, these results. So in Ogden constants, mu1, mu2, mu3, mu4, you can see we have measured across the silica loading. Okay, and for your information, if you go back to the Ogden model once again, so you can see you can really calculate out the modulus if you just add up this different several material constant mu1, mu2, mu3. So based on that, we calculate out the modulus of the material and try to calculate out the cross-link density. Okay, although we have done it by the solution, but from the modulus calculation gives you the big picture because it captures physical as well as chemical cross-link densities. So this is the PDEs. I'm not going into the details out of it, but the Jacobians looks like this, and these are the contours. I mean, we are first following the contour integral method. So these are the controls. This is the strain vector, basically how the crack propagates, and this is the 3D picture of it, and these are the partial differential equations that we are going to solve out. So by the way, we first tried to validate this single edge notch specimen. Single edge notch means at the edge you have the notch, and we have tried to see the crack mouth opening distance. Okay, so we tried to do it with the displacement, right? So if you look at that, this is the FEA results with the governing equation, constitutive equation. We got it. It's coming out 5.141. While the experimental one, same thing, we did the experiment with the same height to width ratio specimen, okay, and giving some so notch to width ratio. So we have figured out this crack tip opening is quite close, right? So our models, our methodology at least work for same specimen, okay, for across the whole specimen. For your information, this we have validated for S30 compound. S30 where you have the better dispersion, okay. But obviously I will show you what it happens. See, another way to validate whether our things are working fine or not, there is a methodology developed by Wing Dong in 2014. That is what it says. If you plot strain energy function, okay, with the pre-crack length, okay, different crack length is simulated, so we get these experimental results. So what Wing Dong's methodology says, if it fits in with the quadratic fit with R-square value close to 0.9, then your methodology works fine. So you can see we are trying to show you a linear fit, which is pretty much not a good fit, but with the quadratic fit, I'm getting a good fit. So our methodology of simulation working fine. So with the different pre-crack length, we have tried to simulate, we have tried to calculate out crack tip opening displacement. That is very important. Once a crack tip opens, okay, so what it says, as per this methodology, if it opens up to 0.1 millimeter in the front, that means it's continuously propagating. So this is what it's an indicator whether the fracture is leading to an immediate catastrophic failure or not. So in this, we are trying to show you the J integral value with the displacement. One interesting point to note that this A value, okay, the crack tip value, you can see after certain points, crack tip displacement, like say 0.48 millimeter pre-crack length, sorry. So you see it's a continuously increasing. Otherwise, there is a stability problem because your crack tip is so small compared to the sample. It's not readily undergoing sort of a fracture there. So this is what it says from the figure. The final figure, strain energy with the silica loading, you can see it is pretty much here. Whereas you can see the experiment, I mean, after 40 or beyond 40, 50, it's very vulnerable, susceptible for the crack initiation and propagation. So this is what it shows you in multi-axial representation, X, Y, and Z direction, how the stress is getting concentrated. You can see the maximal principal stress is concentrating at the crack tip everywhere, okay? And this is where I am talking about 0.1 millimeter. That's how it will propagate actually. Now this is very interesting. I mean, you see the crack path, we are trying to trace it, okay, with respect to principal, maximum principal stress with the true distance along the path. You can see for S50, the maximum principal stress is very high, and you can anticipate the tensile strength was very less. So you can understand the crack will be spontaneously happening from there. I mean, if you compare this stress with that of the tensile strength of the material, okay. So that is what it's showing. Whereas it's very nominal, its tensile strength was somewhere here. So you can understand it can pretty well, the 31 can arrest the crack. But another proof of it, I mean, if you just plot principal stress with the true distance along the path, 2 millimeter, if you go a little bit more in the transverse direction, I mean, widthwise, okay, up to 30, you have some sort of a trend, but 40 and 50 you have below. So 0 to below means what? It means compressive force is dominating. That means it's once again indicates it's leading to you a very spontaneous failure or fracture of the material, by the way. This is what it shows, the nano indentation, although it's out of the context, but we try to simulate with our Ogden model. We went inside about 1500 millimeter and tried to trace nano indentation curve that I already showed you experimentally how it looks like finite element way. So you can see the dotted lines is the finite element wave prediction. Although it is deviating, but at least you can see the relative position of those tip hardness, where you measure the hardness. It's pretty much doing well. But point is that if you ask me the question, why such deviation? Because remember one thing, nano indentation takes some time, so there is time factor involved. So in order to have a better fit, I need to have a visco hyperelastic model. That's what we are working now. So we'll have our own visco hyperelastic model that will plug in our simulation, and we'll try to see not only this sort of a time dependent phenomena, but also we'll try to trace the fatigue and other important properties that those are very, very critical for designing rubber products, by the way. So then the next stage, we try to quickly compare the silica with that of the carbon black field samples side by side, how it looks, and particularly for cent and dent specimen. Dent, once again, double notch. We put the notch length same. I mean, for that double edge notch, we have put distributed half. Anyway, so if you look at J integral with the displacement, you see the trend at different notch to width ratio. By the way, height to width ratio we have chosen here as 6. Now in this case it was 4. And then you can see we try to see the critical J integral. If you look at compare silica, this is the silica one, and this is the your carbon black one. You see carbon black gives you some sort of a over the notch to width ratio up to 0.7. You can see that it is giving you more sort of a critical crackliness over the wider way. So it's giving you some sort of a more stability in terms of resistance against the crack propagation. So similarly, maximum principal stress across the true distance of the notch from the root we have monitored for both 30. I mean, H30 means half loaded compound, vice versa, HD silica loaded compound. But one interesting thing, if you look at that, so we have varied here notch to width ratio. Unlike earlier, I was showing you a small number, 0.06 to 0.3. We varied here. We varied 0.3 to 0.8. But most importantly, you see up to 0.6, it was going up, then it comes down. And you can see the same is the trend over here. It really doesn't matter whether you have a silica or carbon black. Essentially the things are following the same thing. So we are trying to very, very cleverly plug in the effect of the geometry. I mean, we are talking about notch to width ratio, height to width ratio. It was actually rate of change of J integral divided by strain energy density. Then you have a geometric factor. We try to figure out so that we understand how the geometry is affecting and how the actual crack propagation event, I mean critical stress intensity factor is actually influencing. And if you can see the final comparison sent with the dense specimen, you see dense specimen, your factor of dense specimen, your factor of safety is more. Reason is simple. I mean, if you can see, this is all for the dense specimen. You can see the symmetry from both the ends. This is a specimen, by the way. So this, if you can look at that, you are safer. You have two cracks there actually across rather than a single and wider, deeper crack there. But what is important here, end of the day, we came up with our own formulation. This is crack keep opening displacement. Okay, this is notch to height ratio. This is the crack advancement. I mean, incremental advancement. By the way, our methodology was just to mesh it. And once one mesh, I mean, there is a failure, we delete that mesh and go to that. And we try to integrate it. I'm coming there, how we establish it with the newer subroutines that we did it. So this is the equation we proposed, and C and psi are the material constants basically. And this is giving at least 0.9 correlation factor for both carbon black as well as silica samples. But you may ask me the question, sir, I mean, what is the difference? The difference lies in the fact this material constant C and psi will be little different from silica and half samples that has a fundamental material sort of a correlation. How is the bound rubber? How is the separation between the filler and filler aggregates with that of the rubber? I'm not going into that material details right now. So similar way, we try to see in XYZ direction what is the maximum principal stress distribution. Okay, so both cent as well as dense specimen. So it again verifies the same thing what I briefly told you. The very last part of my presentation is about the maximum principal stress strain based damage model to characterize the effect of geometric configuration on fracture. That's what I was again insisting, because in your particular device, in your particular component you make, there is geometry. So unless otherwise you only go by the fundamental fracture toughness of the material, it will always mislead you. So what we try to do, we try to write our own subroutine. The subroutine is same, like I told you, you have to delete that and go, and in each event, each progression of the crack has to be monitored, how much it penetrates and what is the distance from the crack tip to that where the stress is getting concentrated. Okay, so that's what we did it with the two different 2D plane stress and 3D simulation models. Okay, so point is that if you go for 3D simulation, it will take time, computational time, but you can see at the end the error is only, I mean, it's a 5% in case of 2D plane stress, and if you go for 3D, it's 2.9, roughly about 3%. So I'll say it will comparable, and so I'll advise for a quick check. Why don't we go for 2D plane stress sort of a model here? So same way we are trying to realize the J integral factors with different here. By the way, we have used height to with ratio of 4, and we try to see at different pre-crack lengths, and we try to see how the geometric factor and J integral factors are varying basically. Okay, so geometric factor increasing most interestingly here up to 0.7, and then it decreases. So that is a strikingly little different observation from the one I talked about earlier. So in a similar basis, we try to generalize. We try to figure out the critical geometry factor eta c, which is seen to be decreasing with decreasing NWR and HW, for HWR equals to 2, HWR greater than 3. You get a critical geometric factor in increasing with increasing NWR. In a similar basis, we try to have a CTOD R curve. CTOD is the crack tip opening displacement with the crack advancement. Basically, that plot that is very important, and it is observed that this equation fits well that equation I showed you with obtaining the FEA with the R square value of 0.88. So this is where we landed up. So once again, just to show you the intensification of the stresses and compressive stress, how it is coming and when it is coming. Because as I mentioned, if width-wise, I mean, I am talking about width and crack tip, but if you try to examine in the thickness-wise, okay, so if you have a compressive stress, particularly thinner sample, that will culminate to a catastrophic failure for sure. So this is what, I mean, some of the results. I mean, I couldn't really come up to the conclusions because of the, some of the work is under publication. I really don't want to share at this stage, but for sure, in the next platform where we share our advancement of this particular work, I'll share with you what we got and how we usefully use it for a particular, structure, how we use that, our damage model predicting the life and assessment of the fracture. So at the end, I'm very grateful, first of all, to all my group member. Here is my PhD student, all of them. Of course, Sanjay is graduated. Mr. Mandali is about to graduate, and Sudeep has graduated already, and rest of the students are pursuing at different facets. I'm not going to mention each and every one. I'm sorry about that because of the paucity of time. I'm going into the details. These are the 16 students who have graduated working in my group, and at the end, I must thank my collaborator Nils Henrik, who is a senior scientist in DIK Hanover, as well as Professor Filippo Barto. He is from Norway, and their inputs were really remarkable, and we are progressing with jointly sharing our knowledge and developing our skill sets together. So thank you very much for giving a kind attention. I think so I could finish within the time. Thank you very much, Dr. Mondal. Am I in time, right?
Yes. Thank you, Professor Chattopadhyay, for enlightening us with FEA and how it can be important. So we will just take one question. Like the question is basically, what viscoelastic model is used for FEA studies?
We have not used viscoelastic model, by the way. So far, what I showed you is a hyperelastic Ogden model. So we initially tried combining with the Prony series, but once again, that's not a phenomenological model. Prony series is a rough estimation of stress relaxation using Maxwell model and several such components out there. But we are really trying to put in that aspect the molecular models. I mean, like one of the model about the relaxation is a reptation, say, for the flow. So in similar basis, we are trying to working on that, and we'll try to put a phenomenological model along with the another phenomenological hyperelastic model. Combining them together, we'll have our model of our own. So that's what we're trying hard working on that. But otherwise, by and large, normally people, what they do, they combine with the existing hyperelastic model with the Prony series to take care of the time dependency factor of it.
Thank you. Thank you, Professor Chattopadhyay, for your wonderful talk. With that, we will move ahead to the next speaker and the last speaker for the day. May I invite Mr. Michel Cohn for the talk. Hi, Michel. Am I audible?
Hello.
Michel, yeah, now we can hear you.
Can you hear me?
Yes, yes.
Super.
Right. So let me just quickly give
to host.
Yeah. Michel, I would like to introduce you actually. Michel Cohn is one of the senior managers in Michelin Tires R&D France and working closely on recycling and sustainable material. He studied at École Nationale Supérieure de Mécanique Aérotechnique during 1994-1996. After that, he joined Michelin Tire R&D and held various positions since 1997. Currently, he is the European Consortium Director, Black Cycle, and he's going to talk about recycling and sustainability of rubber products. So with that, I would like to invite Michel once again. And Michel, it's all yours now.
Thank you, and I'm very glad to be with you, and thank you for this introduction. I will try to describe you what is the strategy of Michelin as tire manufacturer in this domain of sustainability. And I will be very glad to answer your question after my introduction. So first of all, starting this introduction, I would like to describe more in details the global ambitions of Michelin Group as a global entity in terms of sustainability and development of this sustainability. For us, sustainability means to have a balance between three key domains, between environmental aspect on the planet, between development of the people that work in the company and where the company work for our customers, and last but not least, having a profitable company, enabling to have a high level of growth in the future. For having this ambition, Michelin has some key capabilities. Worldwide strong values shared by more than 100,000 people around the world. A strong brand with Michelin and the famous bibendum for this brand. A deep technical expertise in design, in mechanical design, in material design, in process design and process development and scale up of at industrial level, in innovations where we have a strong scorecard of key innovation during more than 100 years of development of our company. And last but not least, we go from the material to the customer, delivering our customer a different type of product, different type of tires, in aircraft business line, in agricultural tires, in personal car tires, and having a strong expertise in analyzing the satisfaction of our customer on the product, and having a good intimacy with these customers. And for going to this ambition, we will deliver. Our ambition is to deliver to our customers new and innovative products and services in a context of these different businesses. When we talk about sustainability, I think it's really important to define that holistically. That means we are in a context with a tire where the key part of the externalities, the environmental externalities, come from the performances of the product in itself, delivering a high level of endurance, delivering a high level of wear performance, of rolling resistance, is a key point for having a low impact on planet product. And our strategy, we define that with this 4R by recognizing that going from a linear to a circular economy is making both a good usage performance and a good and sustainable supply of the materials. When we talk about 4R, we think about reducing the impact during the life of the product, increasing the lifespan of the product, making some products that are recyclable or made with products that had a first life previously, and making our products with materials that are renewable. That means replenishable at a time of at a human time, not at a geological time. And when we talk about this 4R strategy, it's very concretely involving our practice of life cycle analysis for evaluating our solutions and being holistically and being able to compare them and make the good choice of technology. And we talk about 4R. When we talk about 4R, we recognize that it's not only a question of transformation technology, of choosing the right technology. It's a question of waste management, of transportation of this waste, of preparation of the waste to make a good feedstock for the technology that is involved in the recycling aspect. Not only technology, but the whole value chain has to be considered when you talk about circular economy and recycling strategy. For a company like Michelin, you have to keep in mind that sustainability is deeply involving sustainable raw materials. Because when we talk about delivering all the product to our customer, we talk about 4 million tons of raw material per year that are needed for our plants to deliver the product to the customers. And 4 million tons of product to go from that have to go from a linear to a circular business model is really something impactful for the company, and impactful for the planet too when we will succeed it. Today we are in a situation where about 28% of our material are considered as sustainable raw materials and are considered in our KPI, our key performance indicators that we call sustainable material rate, SMR. And our intent is to go to 40% in the next 10 years. This 40% will be delivered thanks to different technologies that I will try to describe you for giving you a global picture of what we are developing internally or with partnerships. And I put the strategy till 2050 because it's very important to consider that the tire will change. Our usage, our context, the vehicles, the type of motorization are changing. And I put here the vision tire for Michelin to explain that in the next years, probably the product in itself will change a lot being more respectful of the planet, being probably very different than the today tire we know on our cars or trucks and so on. To succeed in this roadmap, to be on the way to the 100% in 2050, we have started to launch different research and development activities in all the different domains of research of materials that are needed to make a tire. And keep in mind that a tire is really a rubber composite. We have rubbers, but we have a lot of other components like metal cords, like textile cords, like additives in the composition, including fillers to deliver for example, the wear performance to our customers. And that means that our research plan and research roadmap is involving a lot of different areas of research. And my proposition in the next minutes is to try to show you 5 examples of technology and research that we have launched in these different domains. First of all, I will start with this activity that is considering the obtention of micronized rubber powder. That's a very interesting technology that we have developed with, and we are on progress to develop it with IIT Technologies, that is an entity of Michelin Group since 2017, based in the US. And this technology is constituted by a cryo grinding of end-of-life tire rubber. That means after separating rubber from steel, from textile, we grind rubber in very thin powder, below 200 micrometers typical size. And with this type of micronized rubber powder, we observe that we are in a very good situation to integrate this thin powder in a lot of different applications, including tires, but including other potential areas of application like asphalts, construction materials, or other plastics for different type of benefit, sustainability, but sometimes additional benefits like noise absorption, for example. And it's really interesting to develop this technology based on a single cryo grinding process, but that is really under control in terms of size, in terms of quality of the materials, and give us a certain versatility and ability to be included in different products. Second example I would like to take is the example of the pyrolysis technology. Pyrolysis is a process without oxygen that considers a high temperature in a oven for end-of-life tire part, sub-component. And thanks to this pyrolysis, we go back to certain components, pyrolytic oils, gases, and recovered carbon black. And the ability to obtain recovered carbon black, we recognize that as very interesting and try to develop our strategy in this area of recovered carbon black. Screening the different solutions on the market, we identified that a Swedish company called Scandinavian Enviro had really an interesting proprietary technology that could give us very good performances in our formulas and receipt of rubber. And that's why we had, after identifying them, we create a partnership with them. And this year we were very proud to propose to the market for the tire championship in electric moto, first motorcycle, a first tire with including this solution of recovered carbon black. Recovered carbon black and our partnership with Enviro is constituted by 4 areas of partnership. The first one is to have a development agreement. That means when you have a recycling solution that has been developed at pilot scale, you will have to develop it at larger scale, a high level of investment resources to deploy to succeed in this scaling up. And we are engaged with them to develop this scale up. Secondly, we have a capital investment in the company. Thirdly, we have a very interesting project in Chile with them to develop a recycling plant dedicated to mine earth mover tires. It will be probably the first time at this volume that we develop a recycling facility based on this technology, and with the ability to use the earth mover tires locally arrived at their end of life, cut in different parts and integrated in this pyrolysis process. We target to start the production in 2023 in Chile with this technology. And globally, we have a supply agreement with Enviro to integrate recovered carbon black more and more in our different products, different tire ranges. Well, in the 2 first example I chose, we were in situation where it was our own waste end of life tires that is considered to create new secondary raw material. I choose here another example to show you that circular economy is very often involving a cross partnership between different value chains, because the waste of one value chain could become the raw material of another. And it's to show you how we need in this circular economy strategy at a worldwide level and to cooperate between value chains. Here we are in a situation where we developed with another startup based in Canada called PyroWave, a joint development agreement to accelerate the very interesting technology of microwave to depolymerize polystyrene and to go back to styrene monomer, obtaining this styrene monomer after we develop the ability to repolymerize this styrene monomer to reobtain our styrene butadiene rubber, that is a famous elastomer that we include in our tire composition. This very interesting project developed with this startup is really one of our high priority projects because we will be in a situation where a very important sustainable part of our tires will be in a situation to include this type of styrene in our composition. To complete the previous example I showed you with around pyrolysis, I would like to introduce you another project that we launched that is purely a research project based in Europe, and this project is called Black Cycle. Our intent here is based on a diagnosis put in this that we have done 3 years ago on pyrolysis. We have worldwide a lot of actors on pyrolysis, making a lot of development on recovered carbon black, but in a lot of cases they do not consider a global approach on all the co-products that are delivered during this pyrolysis. That means as I mentioned you have pyrolytic oils with different type of oils fraction, of mass fraction. You have recovered carbon black and you have gases. And what we try to develop in this project, that is a European project with different partners, we try to consider a project where we will transform all the end-of-life tire into secondary raw materials valuable for different high-tech product. And this is a challenge to ensure that in this transformation through pyrolysis, all the components are finally used in a product and not considered as waste or used for combustion. And to be able to achieve this goal of having 100 sustainable raw material from end-of-life tires, we observed that it was necessary to create a value chain and to gather other partners having key competencies at laboratory scales with research centers, at industrial scales with industrial. If I take example, for example, carbon black supplier Orion is part of the project, because to succeed in creating, because one part of the project is to be able to create new carbon black from pyrolytic oils. And here we have a strong partnership with them because they are able to modify their process to make this scale up of creating sustainable carbon black from pyrolytic oils. In this project, it's a partnership between industrial partners, research center, and technical organization. And we were very proud to be granted by European Commission by a very important grant that is about 12 million on a project that is at 16 million euro during 3-year project. In this project, our intent is to deploy that at European level, to consider 50% of the European end-of-life tire in this process and being able to transform them into secondary raw materials. SRM is secondary raw material. And if we succeed in that ambition, it will be a drastic cut of CO2 emission, going from decreasing from globally about 1 kg of CO2 per kg of raw material included in tires. And that's really a great challenge and a very enthusiastic project to succeed for decreasing this environmental impact of the tire production. And it's really a key project for going to a real circular economy in the tire industry. Now I choose another example that is on progress in our research plan on reinforcement, not in that case in the domain of rubbers, of mixes, but more in the domain of reinforcement technologies. We have a partnership with a French startup called Carbios in the domain of recovered PET. As you know, PET is in the constitution of tire carcasses for personal car tires. We use a lot in the tire industry. It's fossil based today. And with Carbios, we have a very interesting technology that is more in the domain of biotechnology, biotech. And this is very interesting to consider that biotech is really an enabler of accelerating circular economy. And we have this project in as example, but we are developing a strong strategy around that. And we consider here the ability to transform a bottle of PET it could be a clear bottle purely with PET, or a more complex, and that point is very interesting, a more complex multi-layer bottle with different type of material, or colored with different additives bottle. And in this case, the historical mechanical grinding and recovering PET into a new PET by just grinding mechanically the material is not a relevant technology when you are in multi-layer or a complex waste situation. And this technology is really interesting because enzymatic biotechnology has a sorting technology at very local state of the material, at very low temperature, at very low pressure, and that's really interesting for the economical efficiency and ecological efficiency of the technology. And we were very proud this year to obtain the first result at lab scale for the moment of all the technical characteristics of a PET dedicated to tires that probably you know is very specific to this application, and that is very demanding specifications. We are very proud to demonstrate that the feasibility at lab scale of the technology. And now our intent with this technology is to make the scale up of this interesting technology. And same thing that what I told you for the Black Cycle project example. Here we are deeply convinced that we will have to gather a consortium of actors to be successful in this domain, because the success of such a PET circular economy will not involve only the technology, but globally all the collection aspect, post-treatment of the waste, technology, and after integration in the final product. Here is my last slide, just to summarize you what I try to introduce. That means that for a tire manufacturer, sustainability is really something important, impactful, and that's the case for us, for Michelin, that involve a lot of technology, a lot of novelty for design aspect, industrial aspect, and that and involve in a lot of cases deep interaction with the different ecosystem, laboratory, other industrial in the value chain, and all the ecosystem, generally speaking. Thank you for your attention. I don't know if you have a question on my presentation.
Yeah, thank you, Michel. There is a question from Professor Shantanu Chattopadhyay, which he said he would like to ask. Professor Chattopadhyay. I think he's not there. Okay, so there is one more question, is basically, how do you see, like, if you use the recycled carbon black in any of your formulation, is it going to compromise with any of the properties over the, like, the pure carbon black, whatever you're using?
It's a very interesting question. In fact, when I showed you the example of the recovered carbon black, we consider, when we observe today, that it's this type of carbon black is not fully has not fully the same specifications, the same properties of an ASTM reference carbon black. So we observe that there is a difference, and we need to take that into consideration when we design the formulas around this type of carbon black. In this case, we will develop some specific design rules around this carbon black. In the second example I showed you in the domain of carbon black obtained by pyrolysis, like Black Cycle, our aim is really to obtain the same specifications, the same performances of carbon black than the ASTM witness. And in this case, our target is really to be in a drop-in situation where you can use your old design rules and apply them on the new sustainable raw material. It's really two different situations. One case you have to make a tailor-made design, and the other you make a drop-in design.
Right. Thank you, Michel, for your wonderful informations, and looking forward to the work of Michelin towards their role in sustainability. And I'm also very happy that we have closed this session 2 minutes before the scheduled time. So with that, thank you all the three speakers, and it was pleasure hosting you. And with that, I would like to request Professor Naskar to take it over. Thank you so much.
Thank you, Michel, and thank you, Titash, for nicely conducting this session. And if other speakers are there, I would like to invite you to switch on your camera so that we can see each other again at the end. Yes, Francesco, you are there. Okay, Professor Chakrabarty, yes. Good to see. Yeah, Julian also. Great. So it was a long day, I would say. And first of all, I would like to thank all the speakers. Okay, right from the morning, we had started with Nikos, and we ended up with this Michel from Michelin. And in between also, we had two short presentations, and one from Peram and the other one from Mr. Rao about their activities in TechnoBiz and in Indian Rubber Institute. And overall, I think we covered up many topics, and we gathered so much knowledge. And most interestingly, I really believe that it was really useful for all the audience. And I'm sure that they learned many things, and they have the food for their research for the next couple of years for sure. And of course, I also would like to thank all the audience for listening. Still, I could see that 90 attendees are still there listening to us. And what I wish that, special thanks to Peram. You really made my job easier, because he really put a lot of efforts for last 2 months, I would say. And he helped me a lot in organizing this event. Otherwise, it is difficult to accommodate more than 200 people on this, platform. If any of the speakers, Francesco, if you would like to add anything, you can, please.
Just few words on my side. It was a very interesting program, and I like the fact that it was broad. There are people from university and people from industry. Also, in the last talk, we hear the perspective actually not only from academic point of view. So I thought that was very nice. Of course, we do not have interaction with the audience, but I hope it was enough informative for the students and for the general audience in general. I think it's a very good idea. Again, it's a pity that we have to do it in this way. We cannot do it in person, but I hope it will be possible in the near future to organize these kind of things also physically. Thank you for everything, and thank you for the organization.
Okay, Julian, would you like to share a few words?
Yeah, there's not much to add. Can you hear me?
Yes.
Thank you very much for organizing this. It was indeed very interesting to have this broad overview of what is going on in the subject. And yes, so I can only thank you for spending all the time and energy in doing this. So great.
Just I'll add one thing, Professor Naskar. It was very great actually. Sustainability, there is no end to that. Next decade is going to be all on sustainability for sure. And I'll end up asking one. It's not a question. It's a clarification. It's regarding our existence. Michel, you have shown one 2050 projection of a tire. I've seen myself in Claremont, basically, in your exhibition in your museum. So that's going to be your projection with all polyurethane, spokeless. But where we stand as a rubber technologist, because there is no rubber, by the way, it's all of like polyurethane, if I'm right, actually, or type of structure like that. So what goes the rubber? I mean, if it is 2050 projection, is like a, tire is not there, traditional tread is not there. It's kind of a spokeless. It's going to be all polyurethane. I mean, can you comment on that, please, quickly?
Yeah, you're right. The structure, probably this product that you have seen is a long-term strategy inspired by nature. It's really based on biomimetism and considering a long shot. Probably the structure of the carcass, as you mentioned, that carries the load will evolve with probably new type of reinforcement. It could be a spoke in polyurethane, as you mentioned, but probably for the tread, that means the contact between the tire and the road. My perspective is that for a long time, rubber composition will stay something very.
So you are giving us some respite so that we can sleep tonight very well.
Yeah, Leonard, please, if you want to start. You are muted.
Sorry, I have two mute buttons. I have one on my speaker as well, so I'm forgetting to unmute my speaker. But not much to add from my side. It was a pleasure being here. I enjoyed the lectures. It was a long day on the other side, so that's yeah. I can imagine that some people stepped out on some occasions, but it was good quality, worth the day, and thanks for having me here. And I hope you liked the lecture. It gave a bit of the industry perspective, which I think indeed was a good mix of industry perspectives and academia input. So thanks.
Thank you. Kanika, please.
Okay, thanks everyone. I enjoy all the lectures today, and actually, yes, 9 p.m. here in Bangkok or in Thailand. Yes. So,
yes.
Yeah.
So, you have to have late dinner.
I think worth listening to every lecture till the end. So I enjoyed it. Thanks for the invitation.
Thanks for listening all the lectures. Yes. Thank you, everyone. I think we call it a day, and we really hope that after this pandemic era, we'll physically meet each other one day. Let us hope for the best.
Yes, you are all welcome here at Indian Institute of Technology. Please come by here. Stay sometimes out of your busy schedule. I understand, and we'll enjoy together here. Okay. Thank you very much.
Have a good day, everyone.
Thank you.
Bye-bye. Thank you. Bye-bye.
Bye-bye.
Bye.
Thank you, Kinsuk, and
thank you, Francesco.
For Santano, I would certainly love to come over there. So next time we try, and of course,
please come
as well.
Enjoy a couple of bad beer, bad wine with us.
Yeah.
Enjoy the Indian food, but that's
food. Yeah.
So, I'm sure. I mean, I will not frustrate you with that. I mean, you'll love it.
Yeah.
Have a nice day. Thanks for everything.
Have a nice day. Bye.
Take care.
Take care. Bye.
Okay, I'm closing down. Yeah. Okay.